Good morning, everyone. Welcome to the third games agents and incentives workshop. The second we're doing virtually. We hope that the next one will actually be in person, which and hopefully will involve many of you. We will start with Gabriel, slightly changing from the schedule. He'll start with his paper on graphical economics with Resale. We are recording everything. If you want not to record your talk, please tell me and I will stop the recording. But we do hope to allow people who can't attend on these particular hours to still hear the talks. So we do encourage you to, if it's all the same to you, we prefer to record it so people will be able to hear the talks later. So without further ado, thank you all for coming. And Gabriel, you have the floor. We have 15 minutes, by the way. You should get a chat from one of our helpers. I think it's Mumita right now. Our volunteers, that you will get like 5 minutes before your time expires. They will get a message from her, and 2 minutes before as well. If you want me to make some visual sign to you, let me know and I can do that.
Thanks. Should I get started or?
Go ahead.
Perfect. Well, thank you all for hosting this and having me here. I'm Gabriel, and I'll be telling you all about some work I've been doing on graphical economics with Resale. So to set the stage, I wanted to kind of remind everyone of the Arrow-Debreu exchange economy model, which is centralized. And so generally what we have is a set of M agents, let's say. They're selling L goods, or they're endowed with L goods. And each agent is an endowment vector of those goods and a utility function where they have a mapping of the goods and they know how happy they are at the end of it. And in this model, it was introduced in the seminal paper by Arrow-Debreu, and it's very well studied. The traditional equilibrium concept is the market equilibrium concept, which is defined by a price vector over those L goods and a consumption plan, or what's typically called an allocation, but because we're going to introduce Resale later, it becomes easier to call it a consumption plan. And essentially these agents, because they all come to a centralized market, they bring all their goods, they all have access to the same goods, and so there's a single price for any individual good out of that batch of L goods. For an equilibrium in this market, you need to have the market clear, meaning that what every agent buys to consume, the sum over all of those, is equal to the sum of all their endowments. No goods are lost or created in the process of this selling. Also, individual rationale needs to be enforced. So all agents, they buy this consumption plan of goods using the profits they made from selling their endowments, and they purchase a plan of goods which will maximize their utility. So those two conditions, if they're met, we have a Arrow-Debreu equilibrium. But a lot of times markets aren't necessarily centralized, and you might have some kind of locality, some kind of graph structure underlying it. So for example, if I don't have access to apples being sold in India, for example, that's not going to affect the price of apples where I am. So work by Kakade, Kearns, and Ortiz introduced a graphical model that's a graphical generalization of Arrow-Debreu in the early 2000s. And it's defined in a very similar way. You again have M agents, L goods. Each agent has an endowment vector and a utility function. But unlike Arrow-Debreu, there's now this underlying economy graph, where edges of this graph, so first the agents are embedded as nodes in the graph, and the edges represent who can trade with whom. And what happens now, though, is unlike before where we had this like global clearing constraint where just you sum over all the goods, now agents have local price vectors. So each agent has a price for their goods, for their version of the goods. And And now they also have a consumption plan, which they're purchasing from their neighbors. So unlike before, where it's just a consumption plan out of all the goods that are present, I have the consumption from some neighbor J over all those goods. And again, clearing looks very similar, but unlike before where we had to make sure that all the endowments are cleared, it's local in the sense of we only have to have the sum over the consumption plans to equal what others consume from me to equal my endowment, unlike before. But individual rationality looks the same. It's just you buy a consumption plan which maximizes your utility, subject to your budget from selling your endowments. There's a problem with this model, though, which is it's too local in some sense. So where if we look at something like this simple 3-node example with these endowments where you have basically complementary endowments at the ends, but the middle agent has no endowments, what we find is that no equilibrium can exist. And you can see this because the agent in the middle can't make any money from selling their endowments, so they can't buy anything. And so what ends up happening is the goods get stuck. They either have to be sold for 0 price, but when goods are at 0 price and someone has utility for it, here utility is a linear function, by the way, just linear utility. What happens is that you'd request, rationality dictates that you'd ask for infinite amount of that good. It's impossible for the market to clear. So no equilibrium exists in this example. So what we do to remedy this is we take this Arrow-Debreu, this Kakade, Kearns, Ortiz model, which I'm going to call KKO, and we just introduce this resale bound, BI, to each agent. And so once you introduce this resale bound, intuitively, it's still a one-shot process like in traditional general equilibrium theory, but it's intuitive to think about it as now a 2-step process, where first the agents use their resale to basically arbitrage prices in their neighborhood. And then they take that profit plus whatever they made from selling their own endowments, if they had some, and they then use that to buy goods for consumption. How equilibrium is defined now is very similar to the Kakade, Kearns, Ortiz model, but we have this additional condition, which is this optimal arbitrage condition. So now you still have local price vectors, you still have those local consumption plans, and you have also this local resale plan. But for the market to clear, you need to have the amount that's bought from you from both consumption and resale to equal your endowments and the amount that you bought from resale. And optimal arbitrage needs to be enforced, meaning that whatever resale plan you end up going with needs to maximize the profit you make from resale, subject to the budget constraint. And individual rationality, again, same thing, except now the only difference is your budget is a combination of what you made from your endowments with what you made from resale. And the asterisks in this resale Equilibria title is just because in the actual paper, we deal with a more general version of resale. But for simplicity and time constraints, we'll focus on what we call credit-bound resale, which is essentially the amount of money that you are spending on resale is the constraint. It's the amount of money you have available for using for resale. So when we go back to that broker example, we actually find some interesting things. So first of all, Equilibria now exists, even when there's these 0 endowments. And for we set all of the agents' resale budgets to this uniform B, but it doesn't quite matter for 1 and 3 because they have no one to arbitrage but themselves. And what we see is that as long as you set alpha equal to the square root of B over 2, this is an equilibrium. It's easy to check when you start to just sort of work out that agent 2 can only resell B over alpha, and then you start to work this out. It really is pretty straightforward. For time, I'll leave it in the paper or for questions afterwards. And sorry, one other thing I meant to mention is that when you have B greater than 2, you actually recover Arrow-Debreu, the equilibrium you'd have in a fully connected type of market, because goods can basically flow freely, and agent 2 essentially just sort of steps out and says, agent 1, meet agent 3, fun. And this generalizes for more complicated graph structures. And we have this existence theorem. So we show that these equilibria, these resale equilibria, they always exist as long as 5 assumptions are met. Basically, we need the typical Arrow-Debreu assumptions on utilities, which is just that for every agent, the utility is quasi-concave, continuous, strictly monotone or non-satiable, and some good. The second assumption is similar to what we see in production versions of Arrow-Debreu. So you basically just need that the set of plans that you have for resale is some closed convex set, and that when you don't have a resale capacity, you don't have any credit in the example we're running with, then you don't resell. If you're able to arbitrage prices, then you do, because that's rational. You make money and you can use it to consume goods for utility. And if there is a 0 price in your neighborhood when your price is not 0, then no resale plan exists, because you would be asking for infinite amounts for resale. The third assumption is just that for all agents, either they're able to resell or they have some endowment. So it's basically you can participate in the market. The fourth assumption is just that there exists some agent endowed with every good that we have present in our set of goods in the economy. So there's no good that exists but no one's endowed with. And the final assumption is essentially just, it's a little hard to give formally here without much more preamble, but essentially what you have is that for every agent and every good, if an agent is non-satiable in a good, then they are able to actually purchase that good, whether it be directly or through a chain of resale. If an agent is not endowed with any goods, they must be on basically one of these trade paths between 2 agents that are endowed. And finally, each connected component of the underlying graph is strongly connected on the endowed agents, on the graph induced by the endowed agents. And basically how the proof goes for showing this existence is the proof technique is first establish that there is a quasi-equilibrium. And then we basically show that the non-zero price of the quasi-equilibrium it guarantees us will propagate throughout the economy. And that gets us this equilibrium. So I mentioned it before, but some nice properties of this B resale equilibrium is that if you set B for, if B is sufficiently large, the resale bounds in the economy, then you recover Arrow-Debreu. If B is equal to 0, you recover the Kakade, Kearns, Ortiz model. And what's also interesting is that if you set B, take the limit as B goes to 0, you have something that's well defined and exists. And oftentimes, if it's a better replacement in a lot of the examples that we've worked out than taking the 0 endowments and setting them to epsilon like we would traditionally do in Arrow-Debreu, because now you don't get these wasteful equilibria. In the paper, we go through an example of what happens when you set these 0s to epsilons, and you see that basically goods get wasted. They don't get to move to the agents that actually need them in the economy. In addition to this existence result, we also provide an auction-based algorithm for approximating the equilibrium. The basic idea is just that the prices all start uniformly across the board as 1, the consumptions in resale at 0, and agents have a budget, which is just the sum of their utility. And what we do is we basically choose an agent. The order doesn't particularly matter. You can go round robin, do what you will, but you'll repeat this process over and over again. The agents take whatever surplus budget they have. They place bids on goods that will maximize their utility. Their neighbor then goes through this process where they check, do I still have some that's not been assigned to somebody? No one's placed a bid on it yet. If so, then they then check, oh, well, is this a better bid than before? If so, they renege on the previous bid. And if that's not possible, they try to acquire more of the good from resale. And if that's not possible, then finally they will go ahead and just raise their price by a fixed increment of basically multiplicative constant of 1 plus epsilon to the current price. And you'll just repeat this until either the market clears exactly, in which case it's actually not an approximate equilibrium, but an exact equilibrium, or you get a condition where the surplus budgets in the economy are basically vanishingly small based on some epsilon that's set at the beginning of the algorithm. So in conclusion, we've basically taken this Kakade, Kearns, Ortiz graphical economy model, and we've introduced this resale capacity to make it less local and more robust in some sense. We've shown that basically these unintuitive equilibrium outcomes or non-existence of equilibrium outcomes for that model go away. It also allows us to interpolate between the two models. We have existence in that mirrors Arrow-Debreu and is actually more general than the original KKO paper. And we have this auction-based algorithm for computing approximate equilibria. Going forward, we'd like to extend it to production settings, look at what kinds of graph theoretic metrics and what they correspond to for equilibrium outcomes. And finally, characterizing scenarios where this algorithm has a polynomial bound on the max price, which is what bounds the runtime, essentially, is the max price. Yeah, thank you so much.
Thanks so much, Gabriel. Ariel, you had a few questions. Do you want to ask them?
Yes, I would like to ask, can you get similar results in the original KKO model if you just add a good which is a loan, so that agents that have no goods for sale can still get loan and use it?
Yeah, so we tried some variations of this, and we couldn't quite get it working originally. The problem we were running into was, sorry, this was a first iteration of trying something like this. It's a little rusty on what the problem was, but I believe that basically what it comes down to is that the agents have utility for the good, like they would have to have utility base for this loan good. And this creates some problems where there's this conflict of interest, essentially. It's not used as a true loan.
So you have to specifically add the fact that they can buy, but they don't have a value for this specific loan. I see.
Yes.
Thanks.
Yeah, and another version that might be interesting is it's a commodity boundary, so instead of credit, where it's just a cap on the amount of the good that you can sell, or amount of goods that you can resell. And this requires some stronger assumptions for existence, but yeah.
Okay.
Thanks. By the way, is there a guarantee for the auction mechanism to reach the equilibrium, or is it just a approximation?
It's only an approximation. Yeah.
So it's not even guaranteed to converge, or it will converge, but not necessarily to equilibrium.
It'll always converge, just not to an equilibrium, only to an approximate equilibrium. That's all we can guarantee. Okay. Basically, it'll be within epsilon of market clearing and all these other conditions.
Great. Okay, thanks so much, Gabriel, for that talk. And our second speaker is, I don't see Mithun here, but either Ulrich or Warut. Who are you?
That's me.
Yeah. Great. So Warut, take it away.
Can you see my screen now?
Yes, we see your screen, and great.
Okay, great. So thanks, Omer. Thank you, everyone. Yeah.
We assume you want questions at the end. I would assume this for everyone. If you prefer people to, people can write in the chat during, but if you prefer that people actually chime in, you can ask them. But I'm assuming that questions should be at the end.
Yeah, I think that's good for me at the end. Yeah.
Great.
Okay, yeah. So this is joint work with Mithun Chakraborty from the University of Michigan and Ulrike Schmidt-Krepelin from Technical University of Berlin. So imagine the following situation. After a national election, the parties forming a coalition government need to decide how to divide the ministries among themselves. So between them, Party A won 60% of the votes, Party B 30%, and Party C 10%. So how should they allocate the ministries in a fair manner, taking into account both the votes that they won and their preferences? So the literature of fair division has proposed several fairness notions. Two commonly used ones are envy-freeness and proportionality. Envy-freeness says that, for example, Party A should find its bundle at least as good as Party B's bundle. And proportionality says that Party A should receive value at least 1/3 of its value for the whole set of ministries. Now, clearly, these notions do not work well in this setting, where the agents or parties have different weights representing their entitlements to the resource. And this is not just a problem for our party allocation or ministry allocation setting, but also when we allocate supplies to districts, organizations, university departments, and so on, which typically have different sizes. And so fortunately, both NB freeness and proportionality can be generalized to the weighted setting in a natural way. So weighted NB freeness says that, for example, party A should find its bundle at least twice as good as party B's bundle. And that's because that's the ratio between the weights of the two parties. Weighted proportionality says that party A should receive value at least 60% of its value for the entire set of ministries. So these are reasonable notions for the weighted setting. However, when we allocate indivisible items like ministries, we need to relax these notions, because otherwise it could be that all parties place all their value on the same important ministry, and these notions would not be satisfiable. And so that's the motivation for the notion of weighted NB freeness up to one item, which was proposed in a paper last year by Mithun, Ayumi Igarashi, myself, and our workshop organizer, Yara Zik, and also weighted proportionality up to one item, which was proposed also last year by our workshop organizer, Haris Aziz, Hervé Moulin, and Fedor Sandomierski. So I'll get to the definitions of these notions in a few slides, but these are the notions that we want to be going for. Now, what algorithms should we use to achieve these notions? Well, a particularly simple class of algorithms is that of picking sequences, where the agents just take turns picking the item that they like from the remaining items. And a very simple picking sequence, which many of you have probably used at some point in your life, is the round-robin algorithm, where the agents just take turns, A, B, C, and so on. And picking sequences have several benefits. They're intuitive, they can be implemented efficiently, and they help preserve privacy because the agents only need to reveal their picks as opposed to the entire preferences. And several apportionment methods can be formulated as picking sequences, where apportionment is a special case of our setting where all items are identical. So think of seats in a parliament. And an example of a picking sequence derived from an apportionment method is Adams' method, where the next pick goes to an agent who minimizes the ratio between the number of picks that an agent has made so far to the agent's weight. So in our example, Adams' method would assign the picks to parties A, B, C, A, B, A, B, B, C, and so on. And you can see that the frequencies of the picks are roughly proportional to the agent's party's weights. Now, the output allocation of Adams' method always satisfies weighted EF1, but not necessarily weighted problem. So we showed that in our previous paper. And interestingly, we also showed that no algorithm can simultaneously always satisfy both weighted EF1 and weighted prob1. Picking sequences have been used to allocate ministries in some countries, like Northern Ireland and Denmark. And a well-studied class of picking sequences, which generate, or well-studied class of apportionment methods, which generate picking sequences, is the class of divisor methods, which assigns the next pick to an agent who minimizes some function, f, of the number of times the agent has picked to the agent's weight. So Adams' method has f of t equals t, Jefferson has f of t equals t plus 1, and so on. Now, okay, so the fairness notions. So weighted EF1 says that for all pairs of agents I and j, the weighted NB of I towards j can be eliminated by removing at most one item from j's bundle. There's a weak version of weighted EF1, which says that in order to eliminate NB from I to j, instead of removing an item from j's bundle, we could alternatively copy an item from j's bundle into i's bundle. And weighted prob1 says that if an agent misses weighted proportionality, then that should not be by too much. That should be by no more than the agent's value of some item outside the agent's bundle. So our first contribution in this paper is that for each of these fairness notions, we give characterizations of picking sequences whose output always satisfies that notion. And using these characterizations, we can determine which of the 5 traditional divisor methods shown in the previous slide satisfies which notion. So in particular, all 5 of them satisfy weak weighted EF1, And that's already quite interesting because that gives a concrete way in which all these picking sequences provide fairness in the weighted item allocation setting. For the stronger notion of weighted EF1, Adams' method is the only one among the 5 to satisfy it, and Jefferson is the only one to satisfy weighted prop 1. Okay, so besides fairness, another set of desirable properties in this setting is monotonicity with respect to various parameters. Resource monotonicity says that if we add an extra item, then no agent should become worse off. Population monotonicity means that when an extra agent is added, then no existing agent should become better off. And weight monotonicity means that if we add or if we increase the weight of an agent, then that agent should not get hurt. So these properties may seem so natural that you might think that any reasonable algorithm should satisfy them, but that's actually not the case. So for example, well-known algorithms like the NV cycle elimination algorithm or the adjusted window procedure actually fail resource monotonicity. So we give counterexamples in this paper. So these properties are not as trivial as they may seem. And what we show is that picking sequences derived from divisor methods perform quite well with respect to these monotonicity properties. So every divisor method, not just the 5 traditional ones, but all of them, satisfy both resource and population monotonicity. Every divisor method satisfies weight monotonicity for when there are 2 agents. However, they all fail weight monotonicity when there are 3 agents. Okay, another important apportionment method is the quota method. So this is not a divisor method. It has a definition similar to Jefferson's method, which has a function f of t equals t plus 1. However, instead of always assigning the next pick to an agent who minimizes this ratio, an agent may be ineligible if the agent has picked too many times, for some precise definition of too many times. And this method satisfies a natural axiom called, well, the quota axiom, which no divisor method can satisfy. So what we show is that the quota method has properties similar to Jefferson's method, with the notable exception that it fails population monotonicity. And in particular, both Jefferson's method and the quota method satisfy both weak weighted EF1 and weighted prop 1. And these are the only algorithms that we know of to satisfy these 2 properties. Okay, so the last method that we consider is not an apportionment method, but rather a method that is usually considered in the context of fair division, and that is maximum Nash welfare. So in the unweighted setting, this simply chooses an allocation that maximizes the product of the utilities. And it's known that this gives strong fairness guarantees, including EF1. So surprisingly, we show that even in this unweighted setting, max Nash welfare fails both resource and population monotonicity. And this is all the more surprising because in the setting of divisible items, it's known that max Nash welfare satisfies both of these monotonicity properties. Now, in the weighted setting, what we do, we can generalize this max Nash welfare by raising the utility of each agent to the power, which is equal to the weight of the agent. So this is known to satisfy weak weighted EF1, but not weighted EF1. And so what we do is we complete the picture for max weighted Nash welfare. We show that it satisfies weight monotonicity for any number of agents. However, it fails weighted prop 1. So putting everything together, we have the following table. The main takeaway is that the picking sequences derived from apportionment methods perform quite well with respect to monotonicity and fairness properties. Now, even though they all fail weight monotonicity, they all satisfy it when there are 2 agents. On the other hand, max weighted Nash welfare surprisingly fails both resource and population monotonicity, even in the unweighted setting, although it's the only method among the ones that we consider to satisfy weight monotonicity for any number of agents. So taken together, we believe that our results show that the picking sequences from apportionment methods are appropriate for use in weighted fair division setting, such as military allocation. So that's all for me. I'd be happy to take questions if there's time. Thank you very much.
Thank you very much, Ruth. Does anyone have any questions? I see Ariel has.
Yeah, sorry. So is it open whether weight monotonicity and the WEF1 are compatible?
Weight monotonicity and WEF1. Yeah, I believe that's open. So there are actually quite a few open combinations from our paper. So yeah, I can tell you that offline later, but there are quite a few open questions.
Harris, yeah, go ahead.
Thanks for it. I had a question regarding weight monotonicity. Have you explored some weaker versions of weight monotonicity, which put some conditions on where exactly is the weight, how the weight changes for the other agents?
Well, no. So we haven't considered other versions. So yeah, we think this version is the most natural in the sense that you change the weight of one agent only. I mean, there are other notions you could define, like in apportionment settings, where you increase the weight of one agent and simultaneously decrease those of other agents. So yeah, we haven't considered those.
I don't think it should matter because it's normal. I'm not sure. I'm not sure. If you normalize the weights.
Yeah. So yeah, if you're right about normalization, I mean, there's a kind of different version where you could say it's in the sense of you increase the weight of one agent and decrease that of another agent. So like only these two agents' weights change. So you could define that kind of version. And yeah, that's not what we consider. But yeah, so I think the version we consider is like the simplest possible and the most natural.
Thank you.
Thanks. I had a question, but I'll ask you it offline. Let's move on to the next speakers. That's Grzegorz Gawron and Piotr Faliczewski. I don't know which of you is giving the talk, but go ahead.
It's gonna be me. Okay, can you see the screen?
Yes, definitely.
Do you see your pictures as well? Okay, yes. Hopefully should work fine. So I'm Grzegorz Gawron, and together with Piotr Faliczewski, we used multi-winner voting to create a prototype of an engine to help you search for movies or other items. So the way it would work is that you would have some user preferences. As an example here, we have movie lens dataset where people rate movies that they like. They give it 1 to 5 stars. So using this, our system accepts search queries where you say, okay, I want to look for movies which are related to hotshots or similar to hotshots, for instance, right, as an example, which we will actually use throughout this presentation. So I hope you like the movie. And the last point, there's a few missing bits here that we will fill out during the presentation, but the last point is what you want to get search results which are either narrowly focused on the movie that you search for, so movies very similar to hotshots, or maybe on the other extreme end, you might want to look for movies that are related somewhat to the hotshots, but you are interested more in sort of exploring the area a bit more. So you are interested in diverse results. And this is where multi-winner voting helps us do this either narrow or wide focus here. So what I wanted to go through is introduce some components that we use: utility election, OR-based rules, the TF-IDF heuristic, then go through actually filling out those missing bits in the search system, and if the time allows, go through some experiments that we've run. So we use utility elections, and you have some resources. It might be movies, it might be other items. You have some agents here. Each agent has defined a utility function. So essentially, they assign resources real values. So blue agent would assign watch value of 1, and the laptop here value of 5, and so on and so forth for the other ones. So once you have your resources and your utility functions defined here, you actually can construct elections out of those two things. Then if you want to get actually the winner of the elections, you need to have a rule and specify the committee size that you're looking for, the winning committee size. And obviously, once you have your rule, you get your results back. In this case, there's those 3 items. Obviously, there might be multiple winning results, but it's not that important here. The second thing that we use extensively is ordered weighted average based rules. And they are based on the OA operators, where you have a lambda vector of real values. You have another vector x of real values. What you do, you sort the vector x in descending order, and then you apply the lambda vector as a weighted average to this sorted x vector. And this is your ordered weighted average. I'm not sure whether this part here actually hides part of the presentation, Omer, or is it okay? Because I see
we see your, I mean, there's lambda score E. Yeah, I think.
Perfect. Okay, so it's just for me. Fine. Okay, so this is how the OA operator would work. And actually, when we're talking about OA-based rules, the way they work is for a given committee from the candidate set, here called S, we would calculate lambda score for each and every agent, which would be our lambda OA operator applied to the utilities of that agent for the selected committee. And then you just sum up all of those values for each and every agent. You obtain your lambda score for the set S. And this is your essentially score for this given committee S. And now a lambda, OA-based rule would select the committees with the best, highest lambda scores, essentially. So this is how they would work, and we use them for our system. We actually use this specific form of the lambda OA operator here, which we called P harmonic utility voting. And the reason for that is that this parameter P is crucial in what we want to do. You remember about this focus that we wanted to have, either narrow or wide. So when you specify P to be 0, we obtain our very narrow focus, very similar movies to the ones we look for. And when you go up to infinity, you go to the other end, you start getting this very broad focus here. So 0 HUV would be really equivalent to approval voting rule in approval elections, where the vector actually becomes just ones, right? And on the other side, when you go up to infinity, you have this, wide focus again, as this little pyramid. I tried to sort of visually show that. So when you get to infinity, that vector becomes 1 and then all the zeros, which essentially, again, is equivalent to an approval voting rule of Chamberlain-Ron. Now, with those few components, we're ready to fill out the missing bits here. So again, we start with our data set. Then we create global approval election out of that. And the way we do it, we essentially take every movie to be a resource in our global approval elections. And then our user ratings become approval preferences here. So the way it happens is that user approves a movie if they give it a rating of above some threshold. We use actually above 3, that is, if it had at least 4 stars, that means that the user approves of that movie. This would be the global approval election that we have. One thing to note here, we use an example of Movie Lens, but we could really, and I will show later a couple of examples, just take quite a few other domains of user preferences and just transform them into global approval election. And once you do that, you can then just use our system like as it is, like without any other changes. So the only domain specific thing is this first step, or first and second step, creating the global approval election. Moving on, so we specify our search query, and the next step is pretty crucial because what we do, we create this local approval election where we say, okay, so if you're looking for hotshots, we're going to limit the election to only agents or users approving of hotshots, and only to the movies that these users approve of. So this is this limited, very focused election on the query, essentially. So this is very specific for the query itself. And we could actually now apply approval-based rules on top of that election. And this is what we actually did initially, but the results weren't encouraging. So, just looking at them, they weren't great. They didn't introduce much. So we were looking for another, component here. And what we thought about is that to have a guide into to our approval elections with some, well-established search functionalities that search engines use, and we used this TF-IDF search metric heuristic, which we'll go into that a bit later. But anyhow, what we do is we take this local approval election and we transform it into local utility election, where essentially every approval becomes a utility, and that utility is supposed to reflect how relevant this given movie is for the whole search. Okay, we'll get, in the next slide, we're going to go into exactly how this metric would operate. But important thing here is now some of the resources are more valuable to the search query than the others. And this impacts the results of the query. And actually with this approach, we got better results. So the last step is, as we said before, we choose the P parameter for our PHUV, which says if 0 is a very narrow focus, if infinity 2, 3, 4, it's a wider focus. And here we go. We have our hotshots and the exact algorithm, which is 0 HUV. We designed it so that it exactly matches the search metric that you give it. So TF-IDF in this case. And as you can see, some of those movies, there are comedies. I won't go into analysis too much, just by saying that the more you go to the right, when you have 1 HUV and 2 HUV, the more sort of, exploratory movies you start getting, not that much related, not that much similar to the original one, yet user preferences show that people actually, there were people interested in those movies in the context of looking for hotshots. So that sounds pretty interesting. Back to the TF-IDF metrics, because it is a very important one in our solution. So first of all, when you're looking for a movie or hotshots, if you want to look for similar movies, well, you would look for movies that people that watch hotshots also watch, right, and approve of, like. So essentially, when you look at, take a movie and say, okay, all the users that approve of hotshots, there are, I don't know, 75% of those users that actually also approve of this other movie, right? So the higher that frequency, the more relevant that movie would be. And that is the term frequency component. However, that is not all, because some of those movies would be globally popular, right? I don't know, Jurassic Park, everyone would say, and maybe like as well. So Jurassic Park would appear everywhere. And you don't want that to happen. You want to have very specific movies for that query term. So we have this other component, inverse document frequency. And again, this is sort of adapted to this context here. The TF-IDF was, context was a document search. But these are very same contexts that work well here. So again, you want to have this inversely proportional component that says, okay, I'm not that interested in globally popular movies, right? For normal TF-IDF, you just take one and multiply by the other and you have your value. However, we found that we wanted to balance out as well one and the other component. So we introduced this gamma parameter, and essentially our final output is TF, term frequency, times gamma to the power of IDF, right? And this is the metric that we use. There is some things here, but maybe not that important. I'm conscious of time. I'm happy to sort of go offline through those. But as I mentioned, we ran some experiments on books, which is a Goodreads data set, on grocery orders as well. So again, it's very flexible, this approach. Synthetic experiment was an experiment where we said, okay, we want to have a bit more of control over the structure of our data. And we said, okay, what if we divide all of the data in 9 categories? Let's say it would be comedy would be number 1, adventure movies would be number 2. And then each of those categories we would further divide into 9 subcategories. So 1 could be, romantic comedies, 2 could be absurd comedies, as probably Hot Shots would be. Okay, and what we wanted to get at is something like, okay, let's generate a large number of such elections randomly, each of them, and see how each of the rules, by changing, the P in the PHUV rule, how it actually spreads out the winners, the top 10 winners of those elections. And as you can see, the very narrow focus, as we were expecting and wanted to get to that result, is that 0 HUV focuses a lot on the movie that we actually search for. I didn't say that. We searched for the movie, or not the movie in this case, but item from category 1.1, somewhere in the middle here. So essentially it was focused here. And as you can see, the more to the right you go, the wider that focus is. Still, there's 300 in 3 HUV in the same subcategory, but otherwise it just spreads out. Okay, maybe I'm just gonna skip that because it's not that interesting in this context and given the time that we have. But this one is the one that I'd like to go through because this gamma parameter, we introduced it, but we wanted to also somehow calibrate it. And the way we did it, we thought, okay, what is our expectation? Like if we search for a movie with 0 HUV, we really want to have narrow focus, very similar movies. So let's say we take Star Trek movies, all of the Star Trek movies in our data set and expect that when I search for any of those, there's going to be a large amount of other Star Trek movies in our top 10 results, right? So that's exactly what we did. We ran the search for each and every of those Star Trek movies, and we calculated how many of other Star Trek movies are in the top 10. And we did it for, gamma parameter, which was spread in a grid, essentially. As you can see, the number 2 came also from the fact that, on average, it looked like quite a lot of those movies. The average was best across all of those gammas. As you can see, it's not very clear cut, but you do have this sort of rounded shape here. And that's it. I'm happy to take questions. Thank you very much for your attention.
Thank you very much, Grzegorz. Any questions from the audience? So if no one has a question, I definitely had a question. So when you are you presenting multiple answers and ranking them by the TF-IDF, or are you giving only a single answer at each point? Because it seems to be based on committee, so you're producing multiple answers.
Yes, so we are into multi-winner elections. So you do specify you want to have 10 answers, and you do get 10 answers. Is that answering your question, or?
Yeah, but do you rank them? Do you have an internal ranking for them? Or...
Okay. So the way it works for the greedy algorithm, we just return them in the order that it was selected, essentially. Yeah, there is also simulated annealing one. That's a good question. I believe we actually rank them then in the TF-IDF order for simulated annealing.
Interesting. And I assume you haven't examined, like, on user, at least yet, on users and what they're happy with, right? What results? Okay.
Yeah. The only two users were us so far.
And I approve of your movie types, both the Hot Shots and the Star Trek. I can definitely relate.
That's great. Thank you.
Any other questions? Okay, so we are actually pretty short on time, so thanks again so much.
Thank you.
And I think the next talk is by, I don't know who's giving the talk, Dvir, Rika, or Erel, but...
Dvir?
Dvir.
Yeah, okay. You should be able to share the screen, Dvir, if you, I mean, you have the right.
Hi, everyone. My name is Virgilo. I'm graduate student advice. Do you hear me well?
Yes, go ahead.
Okay. I'm a graduate student advised by Richard Gunen, and this is our joint work with Segal Halevi. Let's think about a simple market of one product that there are many buyers and many sellers that would like to trade the product. There is an algorithm that matches up agents to trade the product. The algorithm satisfies the desirable economic properties. In our paper, we built an algorithm that solves more complex markets. The aim of this paper is to automatically arrange the trade in complex multilateral markets. Let's start with a simple example. Consider a market for a laptop. We have buyers who are interested in a laptop and laptop sellers. To make the market efficient, we need to maximize the gain from trade. GFT is the difference between the total value of the sold items for the buyers and the total value of these items for the sellers. Let's look again at the buyers and sellers in the market. Let's find out what is the gain from trade of the market. First, we order the buyers in descending order and the sellers in ascending order. Then we find some optimal deals between the highest buyers and the lowest sellers. The gain from trade is the total profit of all the trades. After we explain the gain from trade, we now want to make sure that the market also has the following properties. The agent values are the private information. We assume that the agents act strategically to maximize their profit, assumed to be their value minus the price they pay. Truthfulness means that if an agent reports his true valuation, he maximizes his profit. A stronger requirement called obvious truthfulness is that for each agent, the lowest profit he may get by acting truthfully is at least as high as the highest profit he might get by acting non-truthfully. Individually rational, IR, no agent loses by participating in the market, which means the amount paid by the trading agent should be at most as high as the agent's value, and the non-trading agent should pay nothing. In Victory Cloud Group's mechanism, the buyers pay the same price of the highest seller price, and the sellers receive the price of the lowest buyer price, but we have budget deficit. which means the auctioneer might lose money. So we need a fourth property, weak budget balance, WBB, which means the total amount paid by the buyers is greater than the total amount received by the sellers. So the auctioneer does not lose money. A stronger requirement called strong budget balance, SBB, which means the buyers and sellers can trade without leaving the auctioneer any share of their gains and without the auctioneer adding money into the market. We prefer the SBB than WBB because in WBB, the auctioneer might take money from the market, which might drive traders away. But we have a problem. The Mason-Centralized theorem states that the combination of all four of these properties is unattainable. One cannot maximize gain from trade while also satisfying IR, truthfulness, and WBB. So the solution is by relaxing some of the efficiency. For example, lowering the gain from trade, we can achieve the other three properties. McAfee solution satisfies the WBB, but there might be a surplus between the two prices. If there is a surplus, it is good for the auctioneer who gets the surplus, but it is bad for the trader. The goal is to satisfy also the strong budget balance, which is good for both traders and auctioneers. Gonen and Segal-Levy's algorithm achieves the goal for two-sided markets. The price for the deals will be the price of the last agent that exited from the market. All buyers pay this price, and some of the sellers receive this price, which satisfies strong budget. In two-sided markets, we have two categories of agents, buyers and sellers. But what if we have three-sided market with three categories, buyers, sellers, and delivery service? What if we have n categories in multi-sided market? The answer to these questions are solved in Gonen and Segal-Levy paper. What if there can be different categories for each trade simultaneously? Even in this simplified market, there may be several different categories of traders. Buyers who are interested in laptops, laptop sellers who sell whole laptops, constructors who build a laptop from its parts, laptop part producers who produce laptop parts. A deal in this market can take one of two paths. A buyer buys a laptop from a laptop seller. This involves traders of categories buyers and sellers. A buyer buys laptop parts and construction service. This involves traders of categories buyers, constructors, and producers. Each path is called a recipe. In each category, there may be many different traders with potentially different profits for participating in a deal. Typically, the value of a buyer is positive and the values of the other categories are negative. The main questions of interest for automatically arranging a trade is who will trade and how much they will pay or receive. The answers to these questions should satisfy the four requirements we saw before: obvious truthfulness, IR, high GFT, and SBB. To solve the problem, we used the algorithm we implemented in our paper, ascending price mechanism for general multi-sided market. First, we present an algorithm with a variety of participants. Each deal in the market might consist of multiple combinations of agents, and different such combinations are simultaneously allowed. The flexibility lets multiple intersecting markets be resolved as a single global market. Our mechanism satisfies the four properties. We evaluate the performance of the mechanism with experiments on real stock market data and synthetically produced data. Here we are going to expand the algorithm. Let's start with the definitions. For each category G, the auctioneer maintains a price PG and the subset MG of all agents that are in the market, which means their value is higher than the current price of their category. And now the actions. At each iteration, the auctioneer chooses a subset of the prices, and it increases by 1 each price PG in this subset. After each increase, the auctioneer asks each agent in turn whether the value is still higher than the price. An agent who answers no is permanently removed from the market. After each increase, the auction computes the sum of prices of the categories in each recipe. When this sum equals 0, the auction ends, and the remaining agents trade using the final prices. Now, we need to explain how the prices are initialized, how the set of prices to increase is selected, how the final trade is determined, who will trade with whom. For each non-leaf G, set the price PG to be the lowest possible price minus B. For each leaf G, set the price PG to be the following formula that contains the depth of G and the maximum of all possible depth. So the price sum of all the paths are equal. How the auctioneer selects which categories to increase the prices. He does it by the following algorithm. Set MG to be the number of agents who are in the market. Set CG to be the sum of the remaining agents of all children of category G. If the MG is greater than CG, then return the parent category G. Otherwise, recursively run this algorithm on each child of the parent G and return the union of the results. This algorithm makes sure that we want to move a child agent if the parent category has too many agents that won't have a deal anyway. The final prices are determined as follows. When the price sum reaches 0, the final price each agent pays or receives is the price of the category, that category. The property SBB is satisfied because the price sum of all paths adds up to 0, which means all deals have no surplus. Let's look at an example. Let's say we have the agents with their values and the receive tree. To find out who will trade with whom, we need to run the contraction algorithm. Here are the summary of how it works. For each leaf that is a single child, combine it with its parent. For any two sibling leaves, combine them by taking the union of their category agents. Let's run the algorithm on the same example we saw before. We have 4 categories with their agents' values. We initialize the prices as we saw before. The first step of the algorithm is to find which category has more remaining agents, the current category or the sum of its children. In our example, the categories that were selected to increase the prices were sellers and producers. The prices increased until one agent said no. They increased V minus 6 times until producer minus 6 exists. And here are the prices after the increase. We do that again with category sellers and constructors and increase the prices V minus 5 times until the constructor with the value minus 5 exists. And again, and the algorithm continues until the algorithm ends, until the price sum reaches 0, and the algorithm stops. Here are the final prices to trade. Now we run the construction algorithm as we saw before to find the final deals and the prices payments. While implementing our algorithm, we found that it is good for all acyclic markets. Let's think about a market that has many recipe trees. In this example, there are 4 possible paths. 2 paths as we saw before, and 2 more paths from another tree. And the algorithm makes sure that all deals have the same price. Our experiments use real stock market data and synthetically produced data. We use the market like laptop market that was shown a few slides ago, which contains a tree with 2 paths. For several values of n less than 1,000, we constructed a market with n agent of each category G. Each agent has the stock price at random day. For each n, we made 1,000 runs and divided the results. We split the values among the categories randomly. So each category has n values. The results from the experiment are represented in this graph. We got some highlights from the experiment, and one of them is the actual GFT of the algorithm is much higher than the theoretical lower bound. K-min is the minimum K of all possible paths in the recipe tree. For example, when n equals 10, the theoretical lower bound is less than 50% of maximum GFT, but the algorithm attains more than 95% of maximum GFT. It surpasses 99.9% of maximum GFT already for n greater than 100. Thank you. Any questions?
Thank you so much, Dvil. There's already one question by Harris. Harris, you want to ask it or can you see it?
Yeah, sure. So I was just wondering that there was a paper by Ostrowski which it's more of a model which generalizes many matching models. So I'm not sure how much it covers monetary aspects, but since it's concerned supply chains, I was wondering what the connections were with your model.
Well, that's actually, I'm not familiar with this model, but I think they don't have the monetary payments. They are more matching markets, as far as I know. Maybe I don't want to be too sure.
Yeah, actually, it's an
Sure.
interesting question. As I looked at the paper after you asked it, I'm not familiar with enough, but it seems that we have it simultaneously, all the multi-side of the market. So I'd be cautious what I answer. I'll look at it more carefully later, but I think we don't have a chain. It's the idea is it's simultaneous.
I see.
Well, I guess you could do simultaneous matching in a chain, but the fact that there are no monetary payments, I think make all the incentive properties quite different.
Right.
Atta, do you want to ask a question?
Yes, thank you. Since just you said there are monitor transfers, monitor transfers also, I was curious about the relationship between the Shapley and Shubik's assignment games for generalizations when we have the multi-sided cases. So maybe this mechanism leads to some core allocation if we can define the core, because we know that in multi-sided cases, TU case assignment games might have even empty core. Do you have any relationship between the Shapley-Shubik's generalization, or could you say anything about the relationship between Shapley and Shubik's model as well? Thank you.
Can you repeat your question again, please?
Yeah, in the two-sided matching markets, right? When we have the transferable utility, we can define the assignment game so that be a cooperative game on the bipartite graph as well. So when we generalize to the multi-sided situations from the two-sided cases with the transferable utility, even the existence of core, so the stable allocations is not guaranteed in all cases. So this model is for multi-sided markets, and I see that you also have the transferable utility so that the monetary transfers are allowed. So I was curious if we can relate with the Shapley and Shubik's assignment game, or to the multi-sided assignment games actually, so that maybe your price mechanism would lead to weekly allocation, or like the one allocation for the side optimal allocation for one side. So is there any relationship between the Shapley-Shubik model, like Harris asked, to Ostrowski model or something like that, more than anything else? So the TU cases, let's say, TU matching games.
I see. I think we should study it more carefully, because before we can answer this question. It seems like a good direction to study. Thank you.
Okay, thank you.
We're running slightly low on time, so I'll defer all other questions to later, offline. There was supposed to be a break right now, but we sort of used that time. So we have about 30 minutes for you to all refresh yourselves. Sorry, thank you to Dvir for your talk. I don't remember I said so before the questions. In any case, the next talk is by Tony Ninagawa, Yasser Mohammed, and Amy Greenwald. I saw at least one of them here before. Vil, can you unshare your screen? Yeah, great. I think Kotone was here before. Oh yes, I see it.
Yes, I'm here.
Great. You can share your screen. I think you're supposed to be able to do that, like the Zoom is supposed to give you information. Great. I should note, by the way, both the talks, this talk, the previous talk, Veer, and the following talk, your easy chair settings are such that you have an anonymous setting, so we weren't able to link to your papers. So if you could de-anonymize your submission in easy chair, we'll be able to link from the web page to your paper. Right now, you can see in the program, some papers are linked, some papers aren't. So if you de-anonymize an easy chair, we'll be able to link from the web page to your papers. But you don't have to do it right now, of course. Anyway, Kotone, take it away.
Thank you for the introduction. Hi, everyone. My name is Kotone, and today I'll be talking about a paper my advisors Yasser Mohammed and Amy Greenwald and I wrote titled Baseline Strategies for ANAC Automated Negotiation League, which outlines the strategies we implemented in our agent that we submitted to ANAC, or the Automated Negotiating Agents Competition, which is an annual competition that provides a benchmark for evaluating negotiation strategies. So here is the outline. I'll go briefly over what negotiation is, especially what automated negotiation is. Then I'll give an overview of the Automated Negotiating Agents Competition, or ANAC, and its setup. Then I'll move on to the general agent architecture and talk about some of the components that we implemented in our agent for ANAC. Specifically how it models the user's utility function using elicitation, how it models the opponent utility function, and the negotiation strategy, and the agent's negotiation strategy itself. Finally, I'll show the results from the competition and then close the presentation with future works and conclusions. And feel free to interrupt me at any point during the presentation if you have any questions. And with that, I'll talk about negotiation. So negotiation, which is an action that's done by all of us in our everyday lives, whether that's through trying to book a flight or with your spouse on who to pick up the kids from soccer practice. And it can be defined as a method to achieve agreements among self-interested actors. And ideally, negotiation achieve win-win agreements. So that means actors are better off after negotiating. And then automated negotiation is when an agent negotiates on behalf of an actor. So an actor here in this illustration is an institution or individual that has a utility function, which are values for outcomes. And then an agent negotiates with a different agent on behalf of the actor. And this actor can be referenced as the user as well. So there are two main components of negotiation, one concerning the negotiation protocol that defines how negotiation is to be conducted, which is the mechanism design problem. And then the other component is the negotiation strategy, which defines how an agent behaves during negotiation. And in this competition, we focus on the negotiation strategy, which is implemented in the agent. So the Automated Negotiating Agents Competition, or ANAC, is an international tournament running since 2010 to bring together the negotiation community. And it provides a benchmark for evaluating practical negotiation strategies in multi-issue domains. And so there are multiple leagues for this competition: the Automated Negotiation League, Human Agent League, Werewolf Game, Humane, and Supply Chain Management, and each of them are concerned with a different domain. And the league that we participated in this year was the Automated Negotiation League. And so the setup of the Automated Negotiation League of ANAC is that there's a domain which is a description of the full outcome space during a negotiation session. This could be party items, or it could be flight booking specifications. And then we have issues, which are possible categories in the negotiation domain. In this case, we have food, drinks, and location. And then values, which are the possible items in the category. So within the issue food, we have values pizza, sushi, hot dog, curry. And then an outcome is a possible agreement in a negotiation, denoted with omega here. And it could be food, pizza, drinks, juice, and location park. So any combination of these three issues would be an outcome. And then for the Automated Negotiation League of ANAC, it was a bilateral negotiation, which means there were two agents negotiating with one another. An agent represented a user whose utility function it does not know. So the user has a utility function in mind of each possible outcome, but the agent does not know what the user's utility function is. And instead, they're given a partial ranking of outcomes that's consistent with the utility function, which I'll explain a bit later. And then agents can elicit further information about the utility function by incurring elicitation costs. Finally, agents run on two parallel threads, one for elicitation, so one to interact with its user, and then one for negotiation with the opponent, described here. So this is the utility function. We know that the true utility function of the user takes this form, which is the sum of weighted value utilities. So here, actually, K represents the total number of issues. So in this case, there are two issues, food, drinks. VK is the set of possible values for issue K. So pizza, sushi, hot dog, curry is the set of all possible values for issue food. And then FK is the function that maps each issue K's values to utilities. So each of these values have a utility, and that's what FK represents. And then pi K is a selection function that returns the value of issue K under outcome omega. So for example, pi 1 of outcome sushi T, where issue 1 represents food, would be sushi. And then pi 2 of outcome sushi T would be T, because 2 represents issues, drinks. And then finally, theta represents the weight of issue K, when F is defined as the weighted combination of FKs. And the sum of theta is all added to 1. So we know we are given that this is the true utility function for the user. And then what is elicitation? So elicitation is a process in which the agent figures out more information about the user through queries. And so, like I said, the user has a utility function, F, which the agent does not know, illustrated here. And then instead, the agent is given a ranking of outcomes consistent with the utility function. So if we have R equals omega 1, omega 2, omega 3, and so on, we know that it follows this utility function that the user has. And then an agent can elicit the rank of a new outcome not in R at some cost. So this agent can ask, where does omega nu go inside R? And then updated ranking of outcomes consistent with F is inferred. So the user can answer that omega nu belongs to this location right here. And in this way, the agent knows more about the user. So there are three main components of an automated negotiation agent. One is modeling the user's utility function, which includes elicitation. The other is modeling the opponent, and finally, the negotiation. So the agent has to think about, oh, what is my user's utility function? What is my opponent's utility function? What additional information can I elicit my user? And how should I negotiate with my opponent? And so for modeling the user's utility function, we use the heuristic to estimate the issue weights, which I won't describe here in detail. But with the estimated, or with the heuristic theta values, we infer an estimate f hat of f by regression analysis. So we try to minimize the sum of the utility difference of consecutive outcomes in the partial ranking. And with that, we model the user's utility function. For elicitation, we elicit k plus 3 outcomes, where the first k outcomes we elicit is determined by the importance, or is used to determine the importance of each of the k issues. So if we have 5 issues, as shown here, and we know the best outcome and the worst outcome for the user, then we replace each issue value of the best outcome with the worst outcome. So in this case, we have Park sandwiches, ice cream, juice, jazz as the best outcome. And for each one, we replace each value with the worst value. And we decide to elicit these 5 new outcomes to obtain more information. And then 3 additional queries are placed. And we didn't really optimize for 3 here. But this is to improve the estimate of the user's utility function. And then modeling the opponent's utility function, we also use the heuristic here, where we use frequency maps to issue, or where we use frequency maps to estimate the value utilities fk and the issue weights. So this I won't go into detail here either. And then the negotiation strategy. So there's 2 components for negotiation. One is the bidding component and one is the acceptance. So bidding is where our agent offers an outcome to the opponent, and the acceptance is where our agent decides whether an outcome that is offered by the opponent is something that we should accept or not. And when we accept, the negotiation session would be over. And so for a bidding strategy, in the initial phase, we only offer the best outcome, which is illustrated here. In the discussion phase, we offer randomly above a conceding threshold. So we concede, so this is represented here. And during these 2 phases, our agent does not accept any offers. In the consideration phase, it offers randomly above the larger value between the conceding threshold, which is the same as the discussion phase, and a utility of outcome that gives maximum estimated joint utility, which is described here. And finally, in the joint phase and final round, we offer an outcome that gives maximum estimated joint utility. For acceptance, it doesn't accept any offers until the consideration phase, and when it does, it accepts offers based on a time-dependent threshold, a strategy derived from our understanding of Atlas 3, which is the 2015 winning agent. And then final round, we accept offers above our estimated reserve value. Finally, the competition performance. Our agent KT was a finalist for ANAC, and it placed 4th overall score, average utility, or in overall score, which is average utility minus the average elicitation penalty. And agent KT also earned the highest average utility, illustrated here, but it incurred high elicitation costs. So the penalty was large, and high elicitation costs did not seem merited, given that 2 out of the 5 finalists incurred no elicitation costs. So for future work, we want to generalize the inference problem as one of learning a probability distribution over a utility function instead of just learning one utility function. We also want to apply existing and proposed generalized inference methods to learn the opponent's utility function. So doing something similar to learn the opponent's utility function as what we have for the users. We also want to implement the fast VOI elicitation algorithm, which computes the expected value of information of all queries and elicit greedily according to these values. And we also want to model the negotiation strategy of the opponent, and then improve the agent's negotiation strategy to best respond to the model of the opponent. So yeah, summary, we described parts of the negotiation problem posed by the Automated Negotiation League of ANAC. We propose baseline heuristics to solve each part, user modeling, opponent modeling, and negotiation strategy. And then we expect the strategy to be released in an upcoming version of the Automated Negotiation League platform, and hope they will serve as benchmarks for the community. And finally, I just wanted to mention that there are many leagues at ANAC, one of which is the Supply Chain Management League run by my advisors, which simulates negotiation in supply chain. And so the league is set up so that there's good documentation and skeleton code for anyone new to join the field easily. So if you're even slightly interested in what automated agents negotiating in place of humans is, this link has more information. So please consider joining. And yes, thank you.
Thank you very much. Great talk. Valentin, you already have a question. Do you want to ask?
Yeah. So thank you so much for that. Very interesting talk. I was just wondering, because your model is now more geared towards elicitation of preferences. Do you need to make some assumptions of the strategy of the opponent to be able to elicit these preferences? And you also make this assumption with the 3 extra steps, the K+3. So that seems to me a heuristic for this competition, right?
Yes, for your second question, yes, the K+3 is a heuristic for this competition. For your first question, the elicitation method is solely for getting information about the user. So for our agent trying to get the user's information, not about the opponent.
Okay. Then I misunderstood. Okay, because I was thinking that the agent has to cooperate for you to be able to elicit this, but this is for the user itself. Okay.
Yes, and we assume that the user does cooperate or give the truthful information.
Okay. Thank you.
Thank you.
I also wanted to ask regarding that is the if your agent was negotiating against itself, as though both sides are your agent. I mean, I assume the competition wasn't, it was different agents, I assume, the competition.
Yes.
But if it was the same agent, is there some guarantee of performance that can be achieved, or it's still a like would it reach something close to optimal? I mean, if they were both pursuing the same strategy.
So even if the two agents that are competing against each other were the same agent, it doesn't mean that they would have the same user, perhaps.
Oh, right. You're right. Yes. Sorry.
And so it would perform differently according to the user. But even if they had the same agent and the same user, they would consider the agents as different agents, I guess.
No, I get that. I was wondering if their behavior is such that if someone was pursuing a similar strategy on the other side, they can achieve some form of best possible achievable equilibrium between agents of these preferences. But I'm guessing that there's no such result on this.
No, I think it is possible though if we know the complete information of the opponent's strategy.
Right.
Like if both sides know complete information about both strategies, then it's possible to make a negotiation that benefits both.
Okay, great. Any additional questions? Okay, actually we're low on time, so thank you very much, Katone.
Thank you.
And our final talk is a paper which was supposed to be our first, but they had graciously agreed to let Gabriel be first because he needed, and Nimrod and Rutvik. I think Rutvik is supposed to present. Yes. Great. Rutvik, you have the floor.
Sure.
Just a minute. So hello, my name is Rutvik, and I'll be presenting proportionality in committee selection with negative feelings. This is a joint work with Nimrod Telman. Now, the core problem on which we focus is that of committee selection, wherein the major task is to design a black box which maps a set of voters, a set of candidates, a fixed integer k, and a preference profile p to a subset of candidates, which we call as the committee. And in this case, the committee should be of a fixed size k. An interesting facet of this problem is that the committee W should satisfy some fairness criterion. One of the widely studied fairness criterion is proportional committee selection, which mandates that a committee should be a microcosm of how underlying voter preferences are distributed. For example, if you have an electorate in which 75% of the voters have their thinking aligned in some way, and remaining 25% of the voters have their thinking aligned in some other way, then in a committee having 4 seats, 3 seats should be allocated to the candidates who are approved by the 75% of the voter faction, and the remaining 1 seat should be allocated to that candidate who is approved by the remaining 25% voters. Yeah, so one of the widely studied preference elicitation mechanism is approval ballots, principally because it is easy to understand. Suppose there are 4 candidates, C1, C2, C3, and C4, and there's a voter V1 who wants to cast a ballot. What V1 has to do essentially is to submit a subset of voters that she approves. What approval ballots don't necessarily address is our V1's feelings towards candidates C2 and C3. For example, here we don't know whether V1 is just unhappy with C2 and C3, or she does not care if they find themselves on the committee. In effect, approval ballots hold voters disapproved candidates and not cared about ones to the same standards, which may not be the best way for a voting rule to estimate the satisfaction of a voter with a committee. And a possible solution is to give voters a way to elicit their approval as well as disapproval ballots, which is captured elegantly by trichotomous ballots. Now, suppose a group of friends have to decide on 2 movies to watch on 2 consecutive days, and suppose they have the following 4 options. They have a comedy movie, they have an action movie, they could watch a drama movie, or they could watch a horror movie, and the 4 friends are, say, V1, V2, V3, and V4. And their underlying preferences are as follows. For example, V1 would absolutely like to see a comedy movie and an action movie. She would tag along with her friends if they were to watch a drama movie, but she would drop out of the plan even if they were to watch a horror movie. Likewise with V2, V3, and V4. Now, if we were to use approval ballots, they would look something like this. Since the not cared about candidates and the disapproved candidates would be merged together, we would have approval ballots like these. And a simple voting rule like approval voting rule would choose a committee containing an action movie and a horror movie. But with this committee, we see that 75% of the electorate is unhappy with at least one of the selected candidates. For example, V1 and V4 are unhappy because a horror movie was selected, which they don't want to see. And V3 is unhappy because an action movie was selected. But now consider the committee containing an action movie and a drama movie with trichotomous ballots. What we observe is that none of the voters' disapproved candidates find themselves on the committee, which means that V1 could now tag along with her friends because they were to watch a drama movie rather than a horror movie. And we get an extra brownie points for saying that all voters get at least one candidate that they approve onto the committee. The notation for the rest of the presentation would be as follows. A set of voters, n voters, V is represented as V1 to Vn. A set of m candidates is represented as C1 to Cm. And for every voter I, we say that AI plus is the approval set and AI minus is the disapproval set. Of course, both of which are mutually exclusive. And we define an indifferent set, which is for a voter, which is found out by picking out the union of approval set and disapproval set from the candidate set. And we say that a preference profile P is the set of n 2 tuples, every tuple containing an approval set and disapproval set of the respective voter. Now, when we talk about proportional representation, we look to answer the following two questions. The first question is who gets represented? And the answer to this is generally that all similarly thinking large enough groups of voters should get represented. And the second question that we look to answer is what exactly is the form of representation? And the answer to this is that we should allocate one or many candidates to satisfy these voter groups. And varying answers to these questions gives rise to different axioms for proportionality. Now, in this paper, we propose two main classes for proportionality with trichotomous ballots. Class 1 axioms are those which vary the amount of representation that a cohesive group gets, and class 2 axioms are those which have a stricter cohesiveness definition, of course, with varying representation. Under class 1 axioms, we propose the following 5 axioms: SPR, WTJR, WTPJR, WAR, and WA. And now we define deserving groups in these as follows. We say that, of course, this is a famous notion of proportionality, which is we say that a deserving group is a set of voters whose size is at least n over k, where n is the number of voters and k is the number of spaces on the committee, or an integral multiple of n over k, whose size is an integral multiple of n over k. And we define cohesive groups as follows. Suppose we were to see if a group of 4 voters, Vx, Vy, Vz, and Vp is a cohesive group or not. So what we do is we take the union of the approval ballots, the approval sets, and we take the union of disapproval sets, and we find the set difference between AI plus and a union of AI plus and union of AI minus. And we see the resulting set. If it's non-zero or an integral multiple of n over k, then we say that this is a cohesive group. Now, why do we do this? Is that the resulting set that we obtain after taking the set minus between AI plus and AI minus contains all those candidates that are either approved by all voters or approved by some and are in the indifferent set of other voters. So this is what we mean by a cohesive group. One of the examples of our class 1 axiom is as follows, which is the strong preliminary representation, which is a very strong notion. We say that a committee W satisfies strong preliminary representation if for all cohesive plus deserving voter groups, the following is true. A unanimously approved candidate of the voters of every group should find itself on the committee, and no candidate which is unanimously despised by all voters in a cohesive group finds itself on the committee. So this is an example of one of our class 1 axioms. Unlike class 1 axioms, for class 2 axioms, the definition of cohesiveness is stronger, which means that lesser groups are considered cohesive under class 2. And therefore, satisfying a group of axioms is relatively simpler. And under this class of axioms, we propose the following 2 notions. First is NCR and second is WNCR. And intuitively, what it says is that if the intersection of approval sets of voters is non-empty, then they deserve a representation. And a committee should contain candidates from either the union or intersection of the approval sets of these voter groups. And the results that we obtain here are that a committee satisfying NCR always exists, and a committee satisfying WNCR always exists and can be found in polynomial time. We also present the hierarchy of the proposed axioms. There's an arrow from axiom A to axiom B if axiom A implies axiom B. Here we segregate these axioms based on our classes, and we come to a conclusion that class 1 axioms are stronger than class 2 axioms. We adapt some well-known voting rules from the domain of dichotomous preferences to trichotomous domain, some of which are very well known. So trichotomous, we adapt trichotomous Chamberlain-Courant and trichotomous PAV. And we also bring in sequential versions of trichotomous Chamberlain-Courant, PAV, and a trichotomous Monroe rule, along with group STV. And we experimentally implement the polynomial time voting rules that we have proposed here. So how do we do that? We generate random profiles, candidate sets, and sizes of the committees, respective sizes of the committees. And we feed them to these polynomial time voting rules. and find the probability with which these voting rules satisfy each of the following actions: WA, WAR, WTPJR, NCR, and WNCR. And we tabulate our results. We say we generate 10,000 profiles randomly. And the number of voters is between 4 and 20. The number of candidates is between 1 and 15. It's randomly chosen, uniformly at random. And the number of seats lies between 1 and number of candidates minus 1. What we see is that group STV has the maximum proclivity, has the highest probability to satisfy our axioms, followed by a tie between trichotomous PAV and sequential Monroe, followed by sequential alpha trichotomous Chamberlain-Courant. And we see that sequential trichotomous PAV is the best rule amongst the presented monotonous rule, since it provides the highest probability to satisfy stronger axioms, for example, NCR of class 2. And as expected, WTPJR, which is a class 1 axiom, proves out to be a stronger axiom than WNCR, which is a class 2 axiom, which is supported by the fact that probability that WTPJR is satisfied by our voting rules is less than the probability of WNCR being satisfied. What's next is to look at participatory budgeting with negative feelings, also with proportionality. There exists a paper on participatory budgeting with proportionality, but negative feelings would be a good thing to look out for. More axioms and positive results in these settings are awaited, and perpetual voting and negative feelings would be another way to go. Thank you.
Thank you very much, Rutvik. I saw that Erel had a question before. Erel, do you want to go ahead and ask it?
Yes, so I wanted to ask, what is the connection between your new axioms and the known axioms for approval voting?
What? Can you please repeat the question? Yes. So, so approval voting, the settings for approval voting are a domain restriction for the case that we consider, wherein no candidate is no voter is indifferent about any candidate. In that way, if you have approval ballots, then they are nothing but a domain restriction in case where you consider trichotomous ballots.
So what I mean is, if suppose you have trichotomous ballots, but people only use two of the three options. So
yes, exactly.
So what do your axioms imply in this setting where they only use two options?
Yes, all our axioms that we have presented here, I think that they imply the axioms in approval settings.
Okay, so there are parallel axioms in the approval setting and the, okay, thank you.
One additional question, Rutvik. Is it easy to extend from so you just extended approval voting, which has two sets to trichotomous. Is it easy to extend to any case sets of sets, not just three, but I know 4 or 5, whatever? Or is it a more elaborate? It doesn't just change easily.
Yes, so that is one thing that we have not considered. We were, of course, thinking about that, but trichotomous settings seem to be natural because anything more than 3 would lead to increasing mental burden on the voters. So, but I think on these lines, I think they must be at least as hard. So, for example, if you consider 4, if you ask a voter to partition the candidate set into 4 sets, then I think it may be at least as hard. I mean, finding results on that kind of ballots would be at least as hard.
I see. Thanks. Yasser, you had a question?
Yes, I had a related question about extensions. In this work, and also if it's extended to more than 3 groups, the burden of deciding the approval is on the voter. In many cases, the evaluation is multidimensional by nature. For example, if you're evaluating a political candidate, there is their economic policy, their social policy, these kind of things. So is it possible to extend it to multidimensional evaluation? So evaluate approval of specific factors of the behavior of the committee chosen, or the member of the committee chosen.
Yes,
I'm wondering if that's possible.
Yes, that is definitely a direction that we would like to think about. It's a nice question. Thank you.
Great, thank you very much. We have 5 minutes before Mike will start his talk. So I'll let you all, go to the restroom for a while. You know what? I'll break it into breakout rooms in case some people want to have some discussions for 5 minutes with other colleagues. It's not a long time, but some people may. Hopefully, people would find some non-talk discussions helpful. So feel free to join the room, and have a great day. And see you in 5 minutes for Mike's talk. Mike, do you want to share your slides if you have any? think we're all back. I think so. Oh, sorry. So we are very honored to have Michael Warbridge of Oxford to give a talk. Not sure there's anyone who isn't familiar with him to present him, but he's of course professor of computer science at Oxford. He's been a researcher for over 25 years. He has many papers and books, some of which are widely spread. I can talk from experience also on his latest book, which is on AI, which is excellent, not just the one for kids, but also the one for adults. He's of course been chair of European AI Association, of ICHCAI, and again, we're very honored to have him give a talk at our workshop. Mike, you have the floor. If you prefer, by the way, questions to interrupt or at the end, we did at the end so far, but if you prefer it differently, just say so.
Okay, you'll probably be smoother at the end, but if there is something really burning and pressing, then please go ahead and ask. Okay, I will start to share my screen. Okay. Okay, so firstly, thank you for the invitation to speak. Thanks to Omar and Harris and all the organizers. It's very kind of you to invite me. And it's wonderful also to see familiar faces and names on the list of participants, and a reminder that at some point soon we will all get through this and we will all be able to meet up in person again. So my talk is about understanding equilibria and multi-agent systems. So what this talk is a rather broad brush picture of a kind of a 10-year-long research program, which is, as the title of the talk suggests, is about understanding equilibria in multi-agent systems. So what I'm going to start by doing is motivating what we're doing and explaining what the basic idea is. And then I'm going to talk about two different approaches to this problem of understanding equilibria. And one of them is based on game theory and is a very analytical approach. And the other is based on modeling and simulation. And what I'm going to try and do is motivate the idea at the end of bringing those two things together. So first, just a bit of historical perspective. As we've seen the multi-agent systems field grow, as we've seen the artificial intelligence field grow over the past decade, I've had a number of kind of agonized conversations with colleagues who've been in multi-agent systems for longer than I have, for more than 30 years, who kind of expressed some sort of disappointment that multi-agent systems, while it's still a vibrant research area and it feels like it's a very active field, isn't receiving the prominence that the other more obvious areas of activity particularly in machine learning, are receiving. And there's kind of this sense that somehow we haven't quite achieved its potential. So the first thing I want to do is just to sort of dispel that myth a bit. When I got into multi-agent systems, the vision of agents that we talked about, the vision of agents that many people talked about, was the idea of having pieces of software which were no longer just the dumb recipients of our instructions, but could work with us cooperatively as active assistants. And that was the software agent idea. And it was a very widely discussed idea in the late 80s and early 90s, but it took some time to actually appear. But it did appear, right? And Siri and Alexa and Cortana are direct descendants of that dream, and they are real, right? We all carry with us a software agent. It's important to remind yourself, I mean, Siri, for example, is a direct descendant of work on agent architectures from SRI in the early 1990s, the open agent architecture, where their work was published at the conferences that make up the AAMAS conference today. I mean, the early work on what became Siri more than a decade later was published at the Autonomous Agents conference in the late 1990s. So it really did happen. But of course, one big piece of the puzzle that we all thought was very natural and was going to happen didn't really quite turn out the way we anticipated. We all thought that not only would we be carrying Siri, but that Siri would be talking to Siri, right? That the agent in your pocket would be busy having conversations with Alexa and Cortana in somebody else's pocket. So that part of the puzzle didn't yet manifest itself. I strongly believe that it will do. I strongly believe that the future of AI generally must be connected AI. Why? Because the history of computing tells us that that must be the case. That's the overwhelming trajectory of computing for the last 50 years. But we aren't there yet. And so while I remain convinced that multi-agent systems, the Siri talking to Siri part is surely going to be there, I don't know exactly what that's going to look like. But that masks a deeper truth, which is that multi-agent systems are actually already used today. And one of the most important uses of those is high-frequency algorithmic traders. These are software programs which buy and sell stocks and currencies and financial instruments on the international markets completely autonomously without human intervention, and very often making use of AI techniques. But what history tells us is that when you build systems like that, they have unpredictable dynamics. So if we go back to the 1980s, October 1987, there was a market crash, a big market crash. I forget if it was Black Monday or Black Wednesday. It was Black some day of the week anyway. And one of the big causes for that market crash was that what was called the Big Bang of the global markets. And this was not automation of the global markets. This was just putting global markets onto computer systems and network computer systems and allowing humans to do trading via computers. But it was a very small step from that. That happened in the mid-1980s. It was a very small step from that to actually start having computers do that trading. Now, as is always the case with these things, there were many complex causes behind the October 1987 crash, but one of them undoubtedly was the fact that very simple computer programs, primitive agents, were being used to do trading. And the kinds of behaviors that they exhibited were things like, if prices go down, then you sell, because that's what you do when prices go down. But with when the markets are populated, when the market ecology is populated almost exclusively by very simple behaviors like that, then that lends itself to feedback loops. And I say there were many complex causes of that, but of the October 1987 crash, but those simple feedback loops were undoubtedly a part of the story. Then we fast forward to May 2007. This was May 2010. This was May 6th, 2010. We were having a general election in the UK, so we were all busy, distracted that day. But over a 30-minute period on the afternoon of May 6, 2007, the Dow Jones Industrial Average in the United States collapsed, and it briefly lost over $1 trillion. And there were some extremely anomalous things happening. So some major shares, Accenture famously, were very briefly trading for a penny a share, which is just an unimaginable state of affairs for a very prestigious share to be trading at that kind of level. But then this happened, this collapse unfolded over a period of about 15 minutes. But then the weird thing is the markets quickly recovered. And so this is what it looked like. This is a picture of the, oh dear, I seem to have lost the bottom of the picture. But anyway, this is the Dow Jones Industrial Average over the day of 6th May 2010. And then it's not on a great trajectory, you'll see, but not anomalous, really. It's sort of gently heading down, but then it starts to collapse. And you've got to remind yourself that's a 15-minute period. So the joke at the time was that if you went to the bathroom or you went to a coffee break, you would have missed it. So this unfolded on timescales that were incomprehensible for human beings, right? People could not keep track of what was going on, and they had no hope of intervening in those markets to try to understand and how to try to salvage the situation. And without any deep insights into what was going on, the market started to recover. And obviously it was very shaky and continued to be shaky for some time. So more than one commentator pointed out that if you look at the trough there, if that trough had happened at 5 p.m. on the afternoon of a Friday in New York, then the markets would have closed and there would have been no possibility of intervening. And the huge losses that had been incurred on the markets would have propagated throughout the global marketplaces. And it would have been days before the New York Stock Exchange opened and had chance to respond. So this is extremely serious and extremely troubling. Again, once again, there is no single reason for the flash crash. It's been investigated time and time again, and it seems like there are a number of issues involved, including potentially fraud. Actually, I didn't check to see what the most recent theory is. There's kind of new theories on the flash crash every month, but there's a whole complex bunch of reasons. But it is absolutely, I think, accepted that the flash crash could not have happened without the fact that the trading was taking place by automated trading programs that were buying and selling without human intervention. So our research agenda, I say the 10-year sweep of our research agenda, is to understand and manage multi-agent system dynamics, and in particular to understand the equilibria. And when I talk about equilibria, I'm really using it in two related but distinct senses. The first is just the sense of some sort of general steady state behaviors, the sort of normal trading behaviors that you might see, for example, on the global marketplaces, the equilibria where everything is happening normally as it should do, and you've got normal sort of market conditions. But then the second sense that I'll come back to is, of course, the game theoretic notion of equilibrium. So the two basic ideas that have informed our research are, number one, what we do is we try to treat the flash crash as a bug, right? So we are used to dealing with bugs in computer programs and computer protocols. So why don't we treat the flash crash as a bug? And we use ideas from automated verification and, as we will see, game theory to try to analyze and find these bugs and to reason about these bugs. So that's the biggest part of the talk. The second idea is instead of going through the very formal approach, which we go down in the first avenue, what we do is we do simulation. We use simulations to try to understand the dynamics of these systems and to explore their dynamics. So let's dig into the first approach. So the first approach, what we do is we treat the flash crash as a bug, right? So it's something that we don't want to happen in our program. Of course, our program in this case is not just one program, but millions of programs that are interacting with one another. And we try to understand where these bugs might happen. So the antecedents, the historical antecedents of our work lie in the work on verification and correctness within the automated verification community, and in particular, a technique called model checking, which is the most successful approach to automated verification. So the basic idea of model checking and automated verification is we start with some program P. So think of that program P as just your Python program or your Pascal program or whatever it is. Sorry, Pascal, I'm showing my age there, apologies. Or in the case of the flash crash, it's a large collection of programs which are busy interacting with one another. And the basic idea is that we can abstract from that program essentially a state transition graph, a directed graph where nodes in the graph correspond to program states and edges in the graph correspond to system transitions. And that state transition graph can be viewed as a model for temporal logic. That is a structure over which we can interpret temporal logic formulas, what's formally called a model. Now, then what we do is we view the correctness property, the property that we want to check. Think of this as there is not a flash crash, right? We express that as a query in using a particular temporal logic. And then verification amounts to what's called a model checking problem. We check that the property that we want to investigate is true in the temporal logic model corresponding to the program. So we check that that temporal logic property holds in the state transition graph corresponding to our program. Okay, so this idea originated in the early 1980s. Originally, it was not at all practical. and was only viable for very small systems with, you know, a few states, but it's gone on and grown to be an entirely viable industrial strength technique with many model checking tools widely available. And it's now routinely used, for example, for checking communication protocols and finding bugs in communication protocols, for checking hardware, for checking computer processors and so on. And the particular temporal logic that we're going to focus on is a language called LTL, linear temporal logic, which was introduced at the end of the 1970s, unbelievable, but it's the lingua franca of that community. So this is the overall picture that we're looking at. So on the top left here, we've got the model of our program. And I say it's just a state transition graph. Nodes in the graph correspond to program states. Edges correspond to the execution of program instructions. In our case, of course, this model, I emphasize, is going to be derived from large numbers of interacting agents. So that's the model that we want to check. And then we've got the property that we want to check on the right-hand side, the specification. Think of this as just being, I don't have a flash crash. And that's expressed in linear temporal logic. And what the model checker does is it says, yes, the claim is true of the model, or no, the claim is not true. Now, what is yes, the claim is true of the model typically amounts to checking that there is some execution of the program, that is some path through that program state transition graph, which would make this corresponding formula, the specification formula, true. There is some path through that state transition graph which would make that specification formula true. That's what model checking does. Okay, a little bit more about linear temporal logic. We tend not to use first order languages. We want to keep things nice and finite state and manageable. So we use propositional languages. So we extend propositional logic. So we've got primitive propositions. And in this talk, I'm going to use big capital Greek phi here to denote the set of primitive propositions, atomic propositions. Think of those as just the Boolean variables. Think of those as being the bits in the programs that we're talking about, the bits that can be either true or false. And then we've got our usual negation and disjunction, but then we've got these funny temporal logic operators. In the next state, the circle operator means in the next state, phi is true. Okay, so this language is used for talking about state sequences, right? The individual computations of our system. So next phi means in this next state that I get to on the sequence, phi will be 2. This diamond means it will eventually be the case there is some state in the future on which phi is true. The box phi means it is always the case that phi is true. And then finally, phi until psi means that phi remains true until psi becomes true on that state sequence. Okay, so let's have a look at some example formulas. This is usually a reliable one at a conference because everybody is jet lagged, but fortunately today I'm not, unusually. So this just says eventually not jet lag. So this just says eventually it's the case that I will not have jet lag, right? So there's some point in the future, diamond means there's some point in the future, there's some future state on the sequence that we're currently in on which I'm not jet lagged. Think of this. You could think of that alternatively as being, for example, diamond flash crash is expressing the property that eventually there will be a flash crash. So that's a property that you might want to check of your property. So always not crash just means the plane, or in our case, the global financial markets will never crash. So box not crash, box means it's always the case that. So box not crash, the plane will never crash. That's what we call a safety property, because generally it is used for expressing properties related to the safety of a particular system. And in our case, not crash can be interpreted as we don't ever have a flash crash. We start to combine these operators, you get a much richer language. So sadly, we have no AAMAS reception where we could try and make this formula true, but this says box diamond phi. It says that all the states on which you reach are followed, no matter where you get to on the state sequence, you're subsequently followed by a state on which you drink beer. So in other words, you drink beer infinitely often. Okay, so that's what that expresses. In computer terms, why would you want to express properties like that? This is just like you would want to express, for example, a server you would want to express of a server that it was available infinitely often, that it never entered a stuck state. So it's always going to be available. If we flip those two properties around, we get a very different meaning. So diamond box dead, right? This means eventually there is a state that you get to after which you're always dead. So eventually there will become a point after which you're always dead. So there will become a point at which I'm dead forever afterwards. And then finally, this binary operator, this until operator says, we're not friends until you apologize. So there's a, we are not friends remains true until the point in the future at which you apologize. So we're not friends at which you apologize. So LTL model checking is piece-based complete, but actually it can be done reasonably efficiently. And there are some automata theoretic algorithms for doing LTL model checking, which work reasonably well in practice. And remember, the two general questions that we're interested in related to reachability and invariance. Reachability, roughly speaking, is there some computation of the system on which phi eventually hold, or does phi hold on all computations of the system? But now if we look at our problem, the problem of understanding equilibrium properties of multi-agent systems, and what we're going to do is we're going to use LTL for expressing properties that we want to check of equilibria. We're going to say, are there computations of our system which hold, which would be generated by equilibrium strategies of the agents in our system, which would make LTL properties true? So the standard model of correctness just assumes that there is some absolute standard of correctness. The specifier is able to say the system is correct or not correct. The specifier involves some privileged position, but for multi-agent systems, this isn't appropriate because all these agents are owned by different people. It doesn't make sense to talk about whether the internet is correct or whether global financial markets are correct. So what we do instead is we do rational verification. So I'll motivate rational verification with the following example, which is one of the examples that we are, some of our students are looking at. This is an automated warehouse example. And you've got these two robots, and the top left robot wants to visit the bottom right location and return infinitely often. So you've already seen how to express that in LTL. And the bottom right robot wants to do the same thing in reverse, visit the top left and then return. So you imagine these are servicing some locations in a warehouse. So the classic view in AI was, from the point of view of the robot in the bottom right, can I get my goal achieved, my plan? Can I guarantee to get my goal achieved? And the answer is no. Why? Because the top left robot could block this entranceway here. So if you just think about this scenario without thinking about the other agents and what the other agents want to achieve, your answer is, the classical AI answer is, no, I can't get my goal achieved. I can't guarantee to get my goal achieved because the other robot would block my way. But if we think about this in the sense of a game, and we think about this from the point of view of the robot in the top left, who wants to visit the bottom right location and return infinitely often, actually it turns out that both of them can get their goal achieved in equilibrium. That is, there is an equilibrium, there are infinitely many equilibria, which allow both of the robots to get their goal achieved. For example, this robot can just move over here and get out of the way. The robot in the top left can move over to the top right and get out of the way, allow the bottom left robot to service, then the robot on the bottom left gets out of the way, and so on. So neither a robot can guarantee to get their goal achieved, but they can if we flip to a game theoretic point of view and reason about this from the point of view of equilibria. So in the rational verification approach, that's what we do. We reason from the point of view of equilibria. We use a game theoretic standpoint. We assume that the agents are rational actors that are trying to bring about their preferences. And the standard equilibrium concepts are the ones that you're familiar with from game theory. We focus on Nash equilibria. We've looked at others, obviously subgame perfect Nash equilibria and so on, are very natural in this case. But what we're doing is we're shifting the focus from saying, could something happen? Could some particular property hold on some path, to saying, could some particular property hold under the assumption that the players choose a Nash equilibrium collection of strategies, as in the example that I just demonstrated? Or could a particular property hold on assumption that the agents, will a particular property hold inevitably under the assumption that the agents choose Nash equilibrium strategies? So we call those two problems E Nash and A Nash, E for exists and A for all. So now our focus has shifted a bit. It looks a bit like model checking, but there's a big difference. We've got our state transition diagram, but this is a multi-agent state transition diagram. So the edges are not labeled with individual program instructions, but typically with tuples of actions that the agents are performing. A tuple of actions, an action profile, one action for each agent in the system. We've got the query that we want to check. So again, think of that query in the middle as being, is there a flash crash? But now the additional thing we need to know the player preferences. We need to know what each of the agents is trying to achieve. And what our rational model checker, what we call our equilibrium checker, will do is it doesn't check whether the claim is true on some path or on all paths. It says, is the claim true on some path that could be generated if the agents chose Nash equilibrium strategies? That's the key difference in our work. Okay, so let's look at a model. In fact, we're going to look at two models that we've used to explore these ideas. And the first model is called iterated Boolean games. And it's a very simple and very elegant model, which makes it very nice for formulating these properties of these systems. So basically, the idea is that what the players do is each player simply has a collection of bits or Boolean variables, and the game is played over an infinite sequence of rounds. And what each player does is at each round, they can just set the bits under their control, the Boolean variables under their control, to be true or false arbitrarily as they choose. Right? So at every round, every player can set the bits or Boolean variables to be true or false as they choose. And then in the next round, they can set them again as they choose. And there's no requirement that they're the same in subsequent rounds or anything like that. They can flip all of the variables if they want. Okay, so that's going to define the strategy space for the agents in our system, right? So the strategies for our agents in the system are just going to tell the agents how to set their switches, right? You can think of this as each agent is looking at a row of switches, a switch here, switch here, switch here, which they can flip to be true or false arbitrarily as they choose. So the strategy for a player is just going to tell them how to set their switches at each round in the game. So what about preferences? So the idea that we use for preferences is we express preferences by giving each player a goal, standard AI idea, but the goal now is a formula of linear temporal logic. That goal formula of linear temporal logic is going to define the runs that the player is happy with and the runs that the player is unhappy with. A player is going to be ultimately satisfied if it gets its goal formula achieved and unsatisfied otherwise. Okay, so think of, your goal could be drink beer infinitely often. You're satisfied if you generate a state sequence in which you get to drink beer infinitely often. The challenge is, of course, you may not control the variable drink beer. That might be controlled by somebody else. Okay, so formally then, an iterated Boolean game is a very simple idea. It's just given by a set of players, the agents in the game, a vocabulary of Boolean variables. These are all the Boolean variables in the game. For each player I, you've got a set phi sub I of variables controlled by player I. And then for each player I, you've got a goal, gamma sub I, which is a linear temporal logic goal. So my goal could be drink beer infinitely often. Almost could be always not die or whatever it is, right? So we each have our own goal. Okay, so V sub I is going to denote the valuations for the variables that are controlled by player I, the instantaneous valuations, right? So the set of all valuations that you could give to a particular to player I's variables. And when each player has chosen a strategy, what they do is at each round, they choose a valuation for their variables. And what that's going to generate is an infinite word over the set of overall valuations. We call those infinite words runs. And those runs are either going to satisfy or not satisfy our agent's goals. And our agent is going to prefer runs that satisfy our goals over those that don't. And this expression here, rho models phi, just means that rho satisfies this LTL formula phi. Okay, so When we look at strategies, is a slightly technical aside. I mean, formally, a strategy just says, on the basis of everything that I've seen, what is the valuation that I'm going to choose for the current round? So it takes as input, a strategy just takes as input a history of the game to date. That is a finite word over the set of valuations, and it generates as output a valuation for the variables under player I's control. The problem is, of course, that's a kind of infinitary mathematical representation. It's useful mathematically, but not useful computationally, because the domain of the function is infinite. So what we use instead, without going into details, is we use finite state machines with outputs. Now, I'm not going to go into the details, but we have a theorem in our work which says that actually, if you have LTL goals, then finite state machines with output are all you need. Right. So now these finite state machines with output, they're basically simple computer programs, very simple computer programs, and the output that they generate are the choices for the players each round. And actually, that's all we need. Once we've got all that, we can start to apply game theoretic terminology. So we've got the standard idea of a strategy profile. Strategy profile is just a collection of strategies. Each of these strategies, sigma sub I, is a finite state machine for player I, which is going to choose a valuation for on each round of the system. The strategies are played against each other. The definition of this is somewhat labored, but you all get the idea. These finite state machines just all play against each other. And since these strategies are deterministic, we have looked at non-deterministic strategies which generate directed graphs rather than individual runs. But if the strategies are deterministic, then each strategy profile induces a unique run, which we just denote by rho of vex sigma. Okay, so then given that, you can define Nash equilibrium in exactly the expected way. And what Nash equilibrium in this case means is that a collection of strategy profiles is a Nash equilibria if every player that does not have their goal achieved in the run that's induced by that strategy profile has no deviation to another finite state machine strategy, which would result in their goal being satisfied. It's the basic definition of Nash equilibria for the game setting that we've got. Here's a simple example. We've got two players, 1 and 2. Player 1 controls P, player 2 controls Q. Player 1 wants P and Q to be the same infinitely often, and player 2 wants them to be different infinitely often. Well, it's not hard to come up with strategies to play these games which generate a Nash equilibrium. So player 1 just sets P to be true and then just fixes it to be true, irrespective of what player 2 does, while player 2 alternates the values of Q. So starts by setting Q to be true, then flips it to be false, and goes back to setting it to be true, and then just repeatedly goes through that cycle. Okay, so some decision problems. Firstly, given a game G and a strategy profile for that game and an LTL formula, is that LTL formula true under the assumption that the players execute their strategies vex sigma? Remember, their strategies are given in the input to this problem. And we call that model checking because it's a variation of the standard model checking problem. It's not a game theoretic problem. There are no game theoretic questions at stake there. In the second problem, though, what we do is we ask whether a given strategy profile is actually a Nash equilibrium of this game. So the first results that we have is that these two problems are no harder than model checking, regular model checking for LTL. So for the first problem, this is not a surprise because it more or less amounts to model checking for LTL. But the second one is a little bit more surprising because it's asking a game theoretic question. So we've got a game theoretic question: is a strategy profile a Nash equilibrium of the corresponding game, which is no harder than regular model checking. Okay, the trick to these, the technical trick to these, is that we can encode these finite state machine strategies as LTL formula. So we can derive the linear temporal logic theory of these finite state machine strategies and then reduce these problems to satisfiability and model checking problems in LTL. Let's move on now to the core problems. These are the ones that we're really interested in. These are the problems that go to the heart of what we're doing, the E-Nash and A-Nash questions. So it's important to understand the E-Nash question. In the E-Nash question, we're given a game, G, which consists of the players and their preferences, and we're given a linear temporal logic property. And the question is, Does the game have some Nash equilibrium? That is there a collection of equilibrium strategies for that game such that in the run that would be generated by the players following those equilibrium strategies, the query phi would be true. The query phi would be made true. Why is that one of the core problems? What we're asking, think of that phi as being there is a flash crash. What this amounts to is, could the flash crash happen under the assumption that the players made rational choices, chose strategies that formed a Nash equilibrium? And for the A-Nash question, we're saying, is it the case that for all Nash equilibrium strategy profiles, phi would be true? That is, phi is true for all Nash equilibrium collections of strategies. And then finally, the non-emptiness problem asks whether the game simply has any Nash equilibrium. Now, all of these, we get a massive blow up in complexity. They all can turn out to be 2x time complete. Why is that the case? Because we can encode a famous problem called LCL synthesis, which was first proved by Amir Pinelli and Ronnie Rosner back in the late 1980s. So that's a negative complexity result. Let's now move on and quickly look at a more concrete language. Iterated Boolean games is a nice theoretical model, but it doesn't in some sense resemble models that you might use for actually programming or building systems. So what we do in reactive modules programs is we do exactly that. We use a language called reactive modules to define agents, which is in some sense related to iterated Boolean games, but is a much more practical language. So this is an example definition of an agent in the reactive modules language. This is an agent called toggle. It controls a single variable x. So we've still got this idea of agents controlling variables. But then its behavior is not defined by just allowing this agent to set these variables to be true or false as it chooses. It's constrained by some rules. And it's got two classes of rules: initialization or init rules and update rules. So the initialization rules just define how it sets its variables initially, and then the update rules just define how it's allowed to set its variables subsequently. So if we look at these update rules, for example, the first update rule, that square box thing is just a syntactic separator, so ignore that. This just comes from the guarded command notation in programming language theory. What this says is this update rule says if x is true, then I'm allowed then to set x to be false. The value of x afterwards can be set to false. So if x is true, I'm allowed to set it to be false. And the second rule says if x is false, then I'm allowed to set it to be true. Now, this is a very simple language, but actually it's a Turing complete language. In the general case, if you have unbounded memory, of course, we don't have unbounded memory, it's actually a language which is widely used for modeling systems. So then a reactive module game is defined by a set of players, n, a vocabulary of Boolean variables, exactly as we did in the iterated Boolean games case. And then we have, for each agent, we have a module which defines that agent, which consists of the vocabulary of Boolean variables that that agent controls, and its initialization rules, I sub I, and its update rules, exactly as we saw on the previous slide. And then once again, what we do is we give our players preferences by giving to them linear temporal logic formulas. We give our players preferences by giving them a temporal logic goal. Actually, we've looked at other languages in addition to LTL. For the purpose of this talk, we'll just stick to LTL. So now this is our picture again. This has now changed. So now notice that our system is not the explicit state transition graph. It's what looks much more like a computer program or a collection of agents that are interacting with one another. We've got our player goals, which are expressed in LTL, and we've got a query of our system. Okay, what our rational model checker will do is it will check whether that claim is true on some Nash equilibrium or all Nash equilibrium. Okay, the interesting thing here is that we get many of our results follow over. So we get the 2x time, completeness for the E-Nash and the A-Nash problems. So they follow over. So it's in some sense a much richer language, but no harder complexity-wise. For the membership problem, it remains p-space complete, but the non-emptiness problem goes up to 2x time complete. Okay, we've implemented a system to check this. This was done by Mohammed Najib in his DPhil thesis. You can have a look at this system. You can play with it online at eve.cs.ox.ac.uk. There's a few systems up there that you can play with, and you can compute the Nash Equilibria, and it will draw you the strategies for the agents in this system. And so on. And it makes use of some quite sophisticated automata theoretic techniques, reduction to parity games, and a complicated sequence of transformations from one kind of automata to another to make that work. But it does work. So briefly, in the last couple of minutes, let me just flip to the second part of the talk, which obviously I'm not going to go into in detail. So this analytical, this game theoretic approach works nicely on small systems. At the moment, it doesn't scale to large systems. So if we want to look at large systems, and let's face it, you know, the global markets are very, very large systems, you need something different. So the alternative approach that we've adopted is agent-based modeling. And the kind of questions that we were interested in were the following. In the flash crash, do market interventions work when things go wrong? So current marketplaces have what are called interventions, which are supposed to stop flash crashes again. This is what they look like. If a stock drops 5% in 5 minutes, then you stop trading in that stock for 5 minutes. If the Standard & Poor drops 7%, then you stop trading everything for 15 minutes. If it drops 20%, then you stop trading for the day. And what we were interested in is, do things like that actually work? And I emphasize, these are, you can Google limit up, limit down and circuit breaker and see how these have been introduced by regulators and so on to try to stop flash crashes. So do they work? The punchline is no, they don't work. So to address this, what we've done is we've used agent-based models, and we model the system down at the level of individual decision makers. And this is a very old idea, but realistic agent-based modeling is possible now for a number of reasons. Firstly, because it's computationally very intensive, but secondly, because of the availability of big data, the availability of data to populate these models. And after the 2008 financial crisis, regulators, for example, in the United States, required banks and other large investors to file through regulatory mechanisms to file data about what they were investigating. We can scrape that data and use it to populate our agent-based models. There are a number of challenges in getting this to work. So one is just getting meaningful simulations. And one of the problems is magic numbers. When you start by doing these simulations, you just get nonsense behavior. And in order to get anything that resembles realistic behaviors, you have to tweak the system, which involves what we call magic numbers. These are just numbers that end up being set to a particular value for no, this particular value comes out as 3.267, and there's no special reason why it should be. It's kind of an artifact of your simulation, but that's kind of troubling if you want this simulation to tell you anything about the real world. The problem of calibration, when does $1 in the model correspond to $1 in the real world? You would want these models to be useful and predictive, but the extent to which they are useful and predictive is controversial. And whether or not you can interpret the models quantitatively is problematic. So this is from our students, James Paulin, for his DPhil thesis. I'm happy to provide it if anybody wants an example. James didn't stay in academia. He's gone back into the finance industry. He developed very large calibrated agent-based models specifically intended to look at flash crash scenarios. Using millions of data and lots of real world data. And the kinds of findings that he had, I'll just give you very briefly because we're out of time, a kind of a flavor of those. So for example, one of the basic ideas is that if you've got crowding in a particular asset, then this can cause contagion in markets. So if everybody buys into a particular stock and that stock suddenly becomes distressed and its price goes down, because they have some bad result or there's some bad news about one of their products, one of their products turns out to be lethal, something like that, and the stock goes down, because lots of people have bought into that stock, then they need to regain their position, so they sell their stocks, and you get contagion spreading out. So that's where crowding, and paradoxically, James discovered that under certain circumstances, crowding can actually be beneficial to system stability. And what James looked at is, for example, you can look at the network topology of investments. You know, this bank is investing in this, and you get, it's really weird. You get these kind of, this bank is buying stocks in this bank at the same time buying stocks in this bank. This bank is lending to this bank, who is at the same time lending back to this bank, and all sorts of weird networks like that. And he looked at kind of, you can, with these agent-based models, you can look at these network topologies. So we've got two different approaches. We've got the rational verification approach, which uses ideas from automated verification and game theory. It's very analytic to try to understand what the equilibrium properties are and whether those equilibrium properties are desirable or undesirable. And the main questions to us there are E-Nash and A-Nash. These are the fundamental questions of analysis for game-like distributed systems, we strongly believe. E-Nash: could a particular property occur under the assumption that the agents made rational choices? A-Nash: will it inevitably occur under the assumption that the agents make rational choices? But we have high complexity for these problems. And that means that you require some sophisticated techniques. So I urge you to look at Mohammed Najib's DPhil thesis to get a feel for those techniques. Interestingly, some of the proof strategies that we use in that work derive from proofs relating to the folk theorems and game theory. And it's kind of strikes me as weird and at the same time really rather wonderful that the ideas from the folk theorems, which were originally discussed in the 1950s, turn out to have relevance for proving properties of computer systems in the 2020s. And agent-based modeling provides a completely complementary approach. There are no analytical guarantees there. It's very simulation-based. It's kind of in some sense rather ad hoc. And really what our future research, what we want to do is we want to try to bring those two approaches closer together. So here are some of the papers that you can look at if you want to get a feel for that work. Any other papers? No. So here are a few of the papers that you can have a look at to get a feel for that work. Okay, thank you. I think I'm about at the end. Apologies, I've overrun by a couple of minutes. So I'm happy to take any questions.
Thank you very much. Great talk. We're already into the time of the next session, so I'll only allow one question. I know I have multiple ones, but I'll start with if people in the audience. I'll only allow one question because of the time. But if anyone has a question, go ahead.
Yeah, I would like to ask something.
Shoot, go.
So if your system is automated as a set of individual rational agents, what should guarantee that the system would actually converge to equilibrium?
No, well, I think what you're pointing at is there's a big assumption. Well, there are a number of big assumptions there. All the assumptions relating to Nash equilibria, for example, carry over into our system, into our work. So assumption of sort of perfect knowledge of the other agents and their preferences and so on. And now there are cases where that's kind of viable, but it certainly isn't viable in the general flash crash case, which is why you need other kinds of approaches there as well. So, I mean, I think the answer is, yes, indeed, that's a big assumption that's built into the work. I mean, we've worked on a number of variants of the model where we try to drop those assumptions, but there's a long way to go with those.
Okay, thanks.
Thanks. Actually, I think there's a lot to do also in what you just in the whole flash crash model that you talked about with robustness, and what does robustness mean? In a sense, the flash crash, and not Black Monday, but the flash crash is an example of a robust mechanism, right? Because it reverted after 15 minutes to a stable state.
Yeah, I'm not sure anybody has great confidence that it couldn't happen again and happen worse. I think you could easily cook up scenarios where bad thing happens. I mean, one interesting question that we started to look at is, could somebody engineer a flash crash? Suppose you had sufficient money to invest in the markets. Could you design a flash crash, right? Suppose you're a state level actor who simply has no interest other than destabilizing the global markets. And I think the answer is almost certainly yes, you could. I think there is I'm not sure it's a robust system. I mean, I think we got lucky would be my interpretation of it.
Oh, I wasn't trying to say it's wrong. I think like conceptual ideas of what robustness is are things I think we're still lacking. And like we're using Nash equilibrium type language, which isn't exactly like a definition of robustness, right? It's a definition of if everyone's behaving in a particular way, it's, yeah, but sorry, I don't want to take the next session's time.
Sure.
So thanks again to Professor Michael Aldridge for his time and for the talk. And I think my chair is going to Sophia. I think you're the chair of the next session.
Yep.
So,
thank you, everybody.
Thank you very much, Michael, again for the talk. It was really great. And I think we can go straight to the second session. I don't know who the speaker is, but we either have Felix, Martin, or Anel.
Hi, so I will be the speaker. So let me
great.
Share my screen. Okay, so.
Perfect.
Okay, I think everybody can see the slides, right? Okay, so hi everyone, my name is Martin. I'm a PhD student from the Technical University of Munich, and I'm going to present you a paper which was recently published at AAAI, which is called Reaching Individually Stable Coalition Structures. And this is joint work with my PhD advisor, Felix Brandt and Anel Wilczynski, and they are also both in the audience, so might also be able to answer questions in the chat already during the session. Okay, so let's start with a nice example here, which is joining the European Union. So we are considering a coalition formation setting, and in the European Union, so these are the 12 members which founded the European Union in the form it exists also now, and then at some point it was among the first countries that wanted to join the European Union was Sweden. And so how does it work to join the European Union? And of course, there's a founding treaty of the European Union, the so-called Maastricht Treaty, and everything is nicely regulated there. And in Article 49, they also consider the case if somebody wants to join the European Union. And if they want to do so, they have to address their application to the Council, and this Council shall act unanimously. And this is the important assumption that I will consider in the form of making coalition formation. So in my model here. So we are considering a formal model of coalition formation under the unanimous consent by the welcoming coalition. And more formally, we are given a finite set of agents here, and I just I'm using here these flex symbols for the agents, and these agents have preferences over the coalitions which they are part of. And in general, this could be any ordinal preferences. We'll see in a second that it's useful to consider some preference restrictions here. And what we are considering now are dynamics of joining other coalitions. So when does an agent have an incentive to join another coalition? And of course, first, I mean, the important incentive is that the agent, by joining another coalition, improves her utility or improves the coalition she's part of. So, and this is a so-called Nash deviation. And here you can see in this example, Canada prefers to be in a coalition with South Africa and France compared to Argentina and Australia, and therefore would like to deviate here. And now we have also to model this unanimous consent here. And by unanimous consent, we mean that the welcoming coalition, every member of the welcoming coalition has to agree to this new member joining them. So for instance, here South Africa has to agree that Canada is joining them compared to the coalition without Canada. Okay, so this is the formal model, and I think many of you already have some interesting questions in mind that you could ask about such a model. So, and by the way, if no such deviation is possible, then we reach an individually stable state, and this notion is due to Dresden and Greenberg already in the 80s. Okay, so it's a classical notion of unilateral stability. And so one of the questions that you come in mind right away is the problem of cycling. So can it happen that agents want to join, and that this dynamics that we consider here cycles? And there's a very, very simple example here with 3 agents. So it's basically rebuilding a Condorcet cycle structure here where one agent wants to join and then she joins. So for instance, here Italy from the bottom left might want to join Spain, and then the agents, so in the middle, they all have the preferences that they want to be with the next agent in the cycle, and so on. And also this example shows that individually stable partitions need not exist. Okay, so this is one of the problems that we could ask, is the problem of cycling. And another problem that we might ask is, now, okay, we can cycle, but maybe there's still a path to stability. And so for instance, here, if we now add the grand coalition, so the set of all players at the top of the preferences for all of the players, then maybe if we start with everyone in a singleton coalition and Italy then joins Spain and then France joins this coalition of size 2, then we reach the grand coalition. And we reach a state which is a perfect state where everyone gets their most favorite coalition. Okay, but we also see in this example that the cycle which we have seen right before still exists. So if the members never go towards the grand coalition, then maybe still cycling can occur. So another natural question, which is also related to cycling, so it's basically the complement of cycling, is convergence of all sequences. Okay, now as I already said in the beginning, it's useful to consider some succinct game representations, and there is an abundance of game representations which were proposed in the hedonic games literature, I would say. And in our paper, we looked at 4 classes of games extensively, and these are anonymous hedonic games, about which I will talk in a second, and also fractional hedonic games, so a cardinal class of hedonic games, and hedonic diversity games, and dichotomous hedonic games. And as I said, there's much more out there. And so, for instance, 2 further classes for which we also have implications follow from our work are additively separable hedonic games or common ranking hedonic games. And there's of course a lot more that could be considered here. Okay, and rather than just telling you the results now for every game, I decided to really spotlight one of the games, and therefore I wanted to stick now to anonymous hedonic games and rather showcase them and give nice examples, because for many of these classes of games, similar things will happen, and yeah, so it's nicer to see one of them intensively, I guess. Okay, so let's start to quickly define anonymous hedonic games. So anonymity basically is what you would expect from such an axiom. Players don't care about the identity of other players, and therefore the dependence of the preferences solely on the coalition size. So for instance, here the country France might want to be in coalitions of size 5, and this is more preferred to coalitions of size 4 or size 6, and this is more preferred to coalitions of size 3, and so on. And so, for instance, this could be, then if we consider it now with agents, then this coalition of size 5, but also any other coalition of 5 size would be preferred to a coalition of size 6, and so on. Okay, and now the first result that I want to show here is that there's already a small counterexample where individually stable partitions need not exist. And I've written here an incomplete version of the counterexample. So whenever you have these dots within the brackets, then you can arbitrarily extend the preferences, and only in the final one, it's the dots without the brackets. So it's just natural order going down here. And so this is a nice example with 15 agents and strict preferences. And previously, the only example which was known where individually stable partitions need not exist was a 63 agent example. So it's already quite an improvement, I would say, in size. And now let's have a bit more a closer look at this example. Let's first say, so the individual stable partitions need not exist, and also the corresponding computational problems, so the path problem and the convergence problem, they are both hard. So for path, it's natural to consider NP, and for convergence, co-NP, because of the complement of cycling. And they are both hard in anonymous games with strict preferences. Okay, but now let's have another look at this example, which I just showed you. And what you can see from the example is that the preferences are quite unstructured, and probably many of you who are familiar with this kind of games are already seeing where I'm going. So I'm going towards introducing single peakness. And just for the information, so you can do two things now if you want to structure the preferences with single peakness. Either you want that agents have single peakness with respect to this axis, which we have down there, or you could change the axis and ask single peakness for another axis, which is maybe a bit artificial, but I just want to mention that this example would satisfy single peakness if you're allowed to change the axis. Okay, but now let's see what happens if you don't change the axis, but if you require single peakness with respect to this natural ordering. So for instance, here, in this example, all the agents have single peaked preferences. I'm not going to define it formally, but just from the picture, there's one peak in the middle, and then the preferences go down towards both sides of the peak. Okay, now let's look at an example in the collision formation process here in this example, and we maybe start with a coalition of size 3 consisting of France, Argentina, and Australia, and then 2 singleton coalitions. And now, if we look here, then Argentina has an incentive to join South Africa because Argentina prefers to be in coalitions of size 2 over size 3. And also, this coalition of size 1 consisting of South Africa gives their approval. So we can perform this change here. And now, maybe we go on, and South Africa has an improvement, and there is approval from the other countries. So this is nice, and we can join here. And now in the next step, maybe Canada can join Argentina, and they will form a coalition of size 2. And now we have reached the state where there is no deviation possible anymore. So we have reached an individually stable state. Okay, so was this coincidence? As we have seen, if you have only strict preferences in anonymous hedonic games, and if you have some artificial notion of single peakness, then this needs not to be the case. However, here it is no coincidence, and we can prove convergence under single peakness. So if we consider this dynamics, then it always converges. So regardless of the starting coalition and regardless of the path we take, it will always converge in anonymous hedonic games. And this holds now for strict and single peak preferences. And also, let me give you a quick proof argument. So I'm giving you an argument why this proof works, and then of course also the running time would be interesting, and you can bound the running time and get another proof here, but it's far more complicated then. Okay, so the proof is quite simple. By contradiction, you assume that the dynamics contains a cycle, and then the basic idea is to extract an infinite sequence of coalitions of strictly increasing size. And since the games we are considering are finite, then this is already a contradiction because the size of coalitions cannot rise arbitrarily. Okay, and more concretely, we can start with somewhere within the process. We know where if there's a cycle, then at some place we need to have a deviation towards a larger coalition. And then if we start with this coalition, we can just consider this new coalition towards which we deviated. So here, this coalition of size 4. And now we have to distinguish two cases. Either it's another agent which deviates here, and then we know that this agent deviates towards a larger coalition. And here we use both strictness and single peakness, because we know that since France here allowed Canada to join in the first place, that France must prefer coalitions of size 4 over coalitions of size 3, and therefore the peak must be to the right. So also we use strictness here. So because the preference is strictly here. Okay, so this is the one case, but it could in principle also happen that it's the same agent that is deviating before. And also if this agent deviates to a larger coalition, this is also fine because again, we are increasing here. And we know now that the peak must be on the right. However, it could also happen that this agent deviates towards a smaller coalition. However, if we consider now deviations of this agent from this coalition that has formed, then basically after some finite number of steps, we must reach a coalition from which he cannot deviate towards a smaller coalition anymore. And this must be larger than the coalition on the left, from which she deviated to the last time towards a larger coalition. And then we know, okay, this agent cannot deviate anymore, and then we need to be in case 1 where some other agent needs to deviate to be in a cycle. Okay, so this is the proof in a nutshell. And now let me just give you brief overview of what is happening beyond anonymous hedonic games. So here are the 4 main classes, and I abbreviated them now to make the table look a bit nicer. So we have these additive anonymous hedonic games where we have seen that strict and single peak preferences yield convergence, but if we only have strict, there's cycling, and we have hardness under strict preferences. And then also for fractional hedonic games, which is maybe also interesting here, is that if we have simple and symmetric hedonic games and start from the singleton coalition, then we will also always converge. However, if we only have simple games or if we only have symmetric games, so simple mean that we have binary valuations, only utility 0 and 1, then we can already cycle. And this is quite easy, I would say, but symmetric weights is something which was not known for a few years now, and which was an open problem before. Okay, and similarly, we have some other results here. So if you're interested, you can have a more detailed look at the slide or maybe ask a question later on. Okay, so let me now finish with some interesting further directions. So I think looking at dynamics based on individual stability or at other unilateral stability notions is really an intriguing direction, and there's a lot that you could do here. So for instance, we left open some candidates where I think that convergence should be possible. So here these binary fractional hedonic games, so which I call simple on the last slide, with an arbitrary starting partition, I would guess that we still have a convergence result here, but we were not able to prove it. And also, I guess that it would be possible to prove convergence in anonymous hedonic games under weak single peak preferences. So if we drop the strictness condition, I guess single peakness is still enough to guarantee convergence. But also this is still open. And then there's the running time of dynamics, for which we already made some improvements since AAAI regarding anonymous hedonic games. And then also one other problem, which I think is particularly interesting, is the combination with other properties. So for instance, with Pareto optimality. So here below, you can see an example of 2. So you can consider this game, for instance, as a fractional hedonic games, but also other game representations work here, where you have basically friendship according to the edges of the agents, and both of these coalitions are stable. It's the same game. I just moved out for the right presentation. I just moved out the interior triangle to the left. And both of them are individually stable. However, the right one, Pareto, dominates the left one, and it might also be an interesting question to satisfy some other properties here. Okay, with this, I'm at the end, and I'm very happy to answer to any of your questions.
Thank you very much. Is there any quick question, especially interest of time? Okay, I was actually wondering about the future direction of weak single peak preferences. What is at the moment the obstacle that you see in improving the results also for the weak single peak preference?
Yeah, so basically the problem arises here in this first case where a new agent deviates, that we need the strictness to know that this coalition where the agent joined is strictly preferred to the one in which she was before. And now, if this agent performs a deviation, and if it's only weak preferences, then we don't know if it goes towards the left. But we have, like I said, we have an analysis where we do use a potential function argument to show that the convergence also holds in a polynomial number of steps. And there we can deal with jumps to the left of the peak. So this is possible, but still we cannot deal with weak preferences. But I think this is already going into the right direction. Yeah, and in short, here's the exact reason where the proof uses strictness.
Okay, thank you very much. Unless there are other questions, I would move maybe to the next speaker. Thank you, Martin. If Can you share your slide, Mehmet?
Oh, yes. Can you hear me?
Yep.
Perfect. I'm sharing my slide. Can everyone see my slides?
Yes.
Okay, great. Thank you. Thank you very much. Let me just make this screen bigger. Okay, so thank you to the organizers for organizing such a fantastic workshop, especially coming from economics. I really appreciate these public good provided by this workshop and amazing referee reports and so on. Today, I'm going to talk about the strategy of conflict and cooperation. So let me start my talk. Let's see. Okay, so that's better, I guess. Okay, so my paper in a nutshell. In this paper, I introduce a novel framework, which I call coalitional strategic games, which is a generalization of non-cooperative extensive form games, and a novel solution concept in this framework, which I call equilibrium system. And this is obtained by applying the so-called recursive backward induction algorithm. This algorithm is a novel generalization of the standard backward induction algorithm that we know in non-cooperative games. Yeah. So what do I show in this paper? That every coalitional strategic game possesses an equilibrium system. And in particular, if we are talking about perfect information coalition strategic games, then the equilibrium system includes strategies in pure strategies only, together with some coalitions. So during my talk, obviously everybody is an expert in his or her own field of research, subfield of research, and you've been probably working on some research area recently. So if you please keep in mind the following question during my talk, and then maybe if you let me know afterwards your thoughts about this, I would be really grateful. So can the framework and the concept I introduced in this talk be applied to the games or research area you've been working on recently? Okay. So what is the motivation for introducing a new framework? Think about the games, the strategic situations such as wars, for example. Let's think about the First World War. What happens is that, well, there are coalitions, right? So there are coalitions, and these coalitions fight against each other. The payoffs at the end of the war differ across and within coalitions. So, for example, two losing empires as well as a winning empire, Russian Empire, collapsed. Some countries managed to stay independent. For example, Switzerland, if I remember well. So, and think about other strategic situations like airline alliances, trade, oligopolistic cartels, the evolution of species and genes. The question is, can we model these games just as non-cooperative games or just as cooperative games? That's a rhetorical question that I'm going to come back. Yeah. So what are those non-cooperative games? In Nash's own word, our theory in contradistinction is based on the absence of coalitions, in that it is assumed that each participant acts independently without collaboration and communication with any of the others. Yeah, so there's a common kind of view in game theory that cooperative games are the games in which you can write contracts, and non-cooperative games are strategic games in which you don't write contracts. I have a different view. Obviously, different people have different views. You might have a different view. You may not agree with me, but my view is that in non-cooperative games actually are the games in which non-cooperation should be enforced. Think about the prisoner's dilemma, right? Prisoner's dilemma, strategic situation of the prisoner's dilemma is not prisoner's dilemma if those individuals if non-cooperation is not enforced. Think about the story behind it. Well, they are in separate cells, so the non-cooperation is enforced. If the non-cooperation is not enforced, and if there is mutual gains from cooperation, I believe that people will find ways to cooperate. And humans throughout history have developed formal and informal mechanisms to cooperate and coordinate among themselves. So this problem of strategic cooperation, as far as I know, first identified in von Neumann in his famous Minimax paper. Other than his famous Minimax theorem, he discusses, there's a lesser known part in which he discusses about the strategic cooperation problem in a 3-person zero-sum game, in which 3 or more person games, he says, do not have the same solution properties as 2-person zero-sum games, minimax equals max min. And we know that there's a recently published paper which tells the communication, which tells Gödel's personal notes when he visited the Institute of Advanced Study, I think in Princeton University. And basically he mentions Gödel about this strategic cooperation problem. Gödel takes note in his personal notes. Okay. So in this talk, I'm going to introduce you some very basic notation of coalitional strategic games to give you an idea of what is the mathematical object that I'm dealing with, what is the framework, mathematically speaking, what is the mathematical object of the solution concept I'm going to describe, but I'm not going to define formally the solution concept itself in the interest of time. It is based on a recursive algorithm, but what I'm going to give you is a illustrative, simple, yet complicated enough example that shows exactly the main points of the algorithm. Okay, so for those interested in my YouTube account, you can find more detailed explanation of step-by-step explanation of the algorithm that I'm going to talk about today. Okay, so what are those coalitional strategic games? Well, coalition strategic games, think of a standard non-cooperative extensive form game, and I add only one thing, most importantly, which is this utility function, not just for individual players, as we have in standard non-cooperative games, but also for coalitional players. Okay, so so in standard non-cooperative games, we have individual utility for each single player. What I add is basically a utility function for each feasible coalition. And this is basically P is the player set, okay, which might be, I don't use N because a player might be a coalition. X is the set of, X is the game tree, set of decision nodes. I is the player function. S is the set of all strategy profiles. H is the set of histories. Okay, it's a standard extensive form game with an addition of a, you can think of coalitional utility function. So how do I define forming a coalition? Formally speaking, if some players I and J form a coalition C, okay, then each player becomes, I and J becomes an agent of player C. Of course, more players might form a coalition, in which case, again, each player who forms a coalition becomes an agent of this coalitional player C, okay? And then these agents act according to the utility function, according to the goal of the coalition, okay? And to decide in the solution concept, that's not part of the framework, but as a part of the solution concept, individuals use their individual utilities to decide whether it is beneficial to join a coalition or not. But once they join a coalition, they commit to coordinating their strategies based on the coalitional utility function. Okay. If there are some costs, this can be included in the utility functions, side payments can be defined, and so on. But in this talk, I just focus on the simplest case in which there's perfect information, no side payments, and so on. Okay. So a supertree of a game gamma is a game in which some players form a coalition, and among those some players, there is the player I, which is the player who acts in the root of the game tree. Okay, so if a player at the root of the game tree joins a coalition, and that defines a new game, a super game, I call this a super tree of gamma. A subtree it starts from information set and contains all of its successors. And in perfect information case, a subtree is exactly the same as subgame. In imperfect information case, a subtree might start from an information set which is non-singleton. Okay. Let me check the time. Okay. So a system is a solution. A solution concept is a system, which is this complicated object here, sigma and gamma, where, please bear with me a second, capital G of X denotes the set of subgames of the course's subgame starting at X. So at the beginning of the game, this is basically a set of all subgames. Sigma of X comma G is a strategy profile in G, okay? And pi X comma G is a partition of players in G. Technically speaking, for each X decision node in the game tree, sigma of X is a collection of strategy profiles for each successor subgame. Similarly, pi of X is a collection of partition of players. So sigma is a family of collection of strategy profiles, and pi is a family of collection of partition of players, compared to a standard solution concept in non-cooperative games, and equilibrium is just one strategy profile. Here, a system is a family of collection of strategy profiles and family of collection of partitions. And an equilibrium system is a system, informally speaking, that is both subtree and supertree perfect. Okay, so in an equilibrium system, coalitions, there are different coalitions at every single subgame and subtree and supertree, and they are in equilibrium, and the whole system supports each other. Okay, informally speaking, I'll give you an example. Equilibrium system is defined and computed via the recursive backward induction algorithm, which I'm illustrating now. Here we have a 4-player game, okay? And in this game, you see individual utilities here, standard extensive form game with an addition of utility function for coalitions, which I assume that coalitions try to maximize the minimum payoff of the members in that coalition, okay? Just for the purposes of this talk, in general, it can be any von Neumann-Morgenstern utility function. Okay, so in 4 steps, how do we solve this coalitional strategic game? Let's start from step A. This is the standard non-cooperative solution, okay? And the standard non-cooperative solution outcome is basically on the path, the outcome is 3, 3, 2, 1. Okay, so I'm now focusing on this part of the game tree, okay? This sub-game over here. In this sub-game, notice that if player 2 and 3 form a coalition, they can actually choose L and L, in which they are both better off, 4 versus 3 and 3 versus 2. So they are both better off. So coalition, as a coalition utility, choosing LL is better for those players. Okay, so that's the kind of the first step. But if player 1 anticipates this potential coalition between 2 and 3, then player 1 will not be choosing actually L. Instead, player 1 would choose R. And in this super tree, the solution, the outcome of this super tree would be R and L. The outcome has changed actually from 3, 3, 2, 1 to 2, 1, 2, 4. But then player 2 notices that if player 1 chooses R, then player 2 receives 1 here, its worst payoff. Player 2 might actually propose to form a coalition, in which case player 1 chooses L. So here the 1 and 2 represents a coalition player of between 1 and 2. Player 1 chooses L, player 2 chooses R, and they end up again at this outcome in which that is better for both player 1, 3 versus 2, and for player 2, 3 versus 1. again, with respect to this counterfactual over here, forming a coalition between 1 and 2 in step C is a rational thing to do. But is that the end of the game? No. Well, player 4 in this case received a very bad payoff. So now player 4 is offering, in some sense, that's the kind of the words interpretation, player 1 to cooperate, in which case, actually, if player 1 and the player 1 and 4 chooses R and R, they end up at a outcome where player 1 receives 4, which is greater than 3, and player 4 receives 3 greater than 1. And turns out that this is the last step. There is no more possibility, given this scenario, there is no more possibility of forming coalitions. And then that is the outcome of the recursive backward induction process. And the equilibrium system is gives at every counterfactual, it should state what happens in the future subtrees and supertrees. Okay, let me just check how many minutes do I have? 2 minutes. Okay. Cool. Okay, so the equilibrium system outcome in this game is 4, 1, 2, and 3. Right? Let's suppose that, just to give you another example, and I think there was one referee comment here, instead of this is 2, let's suppose that this is 4. Just this payoff, player 1's payoff is changed. In that case, actually, there would not be these coalitional steps that I calculated over here, because, well, in the beginning of the game, player 1 would directly choose non-cooperatively R, and player 4 would choose L, and this would be the outcome of the game without any further cooperation possibilities. So what makes player 4 here propose player 1 to cooperate is the fact that player 1 can form a credible coalition with player 2, making the outcome very bad for player 4. This brings player 4 to the bargaining table in some sense. And that's why in that case, the cooperation between 1 and 4 occurs. Okay, so for those who will watch this video later, just you can pause this. I give a full solution of what I've described here, full equilibrium system solution. You can have a quick look, pause the video, and see the full solution over here, which I'm not going to go over, but I just would like to state the theorem, which says that, you know, there exists an equilibrium system in every finite n-person coalitional strategic game. In other words, this cycle of coalitional deviations actually converge at some point. Okay. A general question I received that, you know, would it be possible to actually just make a fully non-cooperative game given a coalition extensive form game? It is not possible because, well, adding a strategy, then adding a cooperation strategy, such as in Prisoner's Dilemma, doesn't make the game cooperative. But in game theory, right, we don't, the name of the strategies don't matter. So if we add another, it's a non-cooperative strategy. If we add a non-cooperative strategy called cooperation, we are not actually solving the problem. We are actually increasing the possibilities of further cooperation in some sense. And the coalition strategic games, like the mathematical speaking, is a generalization of non-cooperative games. So it is really not possible to do that. There's a huge literature that studies cooperation from very different aspects. Coalition formation, as Martin talked, there's a huge literature that combines, you know, literature in computer science and economics as well. I refer to Ray's 2007 book, which is now freely available online for many references. And my paper most related to coalition-proof non-cooperative concepts, AAMAS strong equilibrium and the coalition-proof Nash equilibrium, Burnham, Pellick, and Winston. Yeah, and the difference is that their solution concept is a refinement of Nash equilibrium, whereas an equilibrium system is not a refinement nor a generalization of Nash equilibrium. And it is fully, the cooperations occur fully strategically. So it's kind of the solves one potential, you know, so in the coalition proof, Nash equilibrium is a recursive concept as well, and it does consider some coalition possibilities. But when you form a coalition in that concept, players do not consider the possibility of forming a coalition with other coalition members of the other partition in some sense. But that's kind of the literature that that's a huge and recently growing literature. Okay, so that's the end of my talk. I hope I'm on time. As I mentioned before, if you have any comments or questions, I'm happy to take. Thank you very much. And you can write me later as well if you have any suggestions regarding applications. Thank you so much, everyone.
Thank you, Matt, for your presentation. There is a question in the chat for you, but since for time reason, I think we already need to skip the break. And so I was wondering if you're happy to answer to the question in the chat instead of taking it live at the moment.
Yes, perfect. I'll do it.
Okay. Is in the chat waiting for you, the question.
Okay, okay. I'll have a look at it. Yes, I just saw it.
Okay. So maybe in the interest of time, we can move on with the next presentation. And sorry, again, we need to skip the break. And we should have Patrick ready to go. Patrick?
Yes.
Great.
So I guess you see my screen?
Yep.
Okay, perfect. So hi, I'm Patrick Lederer. I'm at the Technical University of Munich in the group of Felix Brandt. And I'm going to present my results on spreadsheet-proof randomized social choice for restricted sets of utility functions. So this is all about social choice. I guess most of you know the problem. So we get the preferences of multiple agents, and the goal is to select one alternative of the winner of the election in the end. And while it is known that this problem is quite hard in many situations, it's easy to think of situations where the winner of the election is clear. So for instance, if you look at this example here, 3 out of 4 voters report A as the best choice. One voter says that A is the second best choice, so it seems quite plausible that A should be the winner of the election. However, even though it seems plausible to choose A here, it's not really clear that you can choose A here. Particularly, it might be in conflict with basic properties such as strategic proofness. And that is what I'm aiming to address today. So let me first formalize the setting a bit more. So we are in the classic setting of the choice. That is, we have a finite set of alternatives. In our example, that is A, B, and C. In general, we just assume that we have M, which is at least 3 alternatives. Next, we have a set of voters. Voters are denoted by numbers from 1 to n, and we once again assume that we have at least 3 voters. And finally, each voter has a preference relation, which is a complete, transitive, and antisymmetric binary relation on the alternatives. So that are just classical strict preference relation. For instance, the preference of voter 1 states that it prefers A strictly to B and B strictly to C. Now, we do not want to talk about the preference relation of a single voter, but about preference profiles, which just consists of the preference relation of every voter. The goal is then, given such a preference profile, to determine the winner of the election. And for that, we use social decision schemes, which map preference profiles to lotteries on the alternatives. The idea here is the following. The social decision scheme determines for every alternative its winning chances, and the final winner is then decided by chance according to those probabilities. So for instance, you can do the plurality rule, which just randomizes uniformly between the alternatives that are first ranked by the most voters. In our example, this would mean that A is chosen with probability 1. Now, to formalize the problem which we had before, we need, first of all, some decisiveness axiom which formalizes that we should choose A in our example preference profile. And for that, I use K-unanimity. And the idea of K-unanimity is that you choose an alternative with probability 1 if it is top ranked by all but K voters. So stereo-unanimity is just the classical unanimity notion, which you probably know. And if you require 1 unanimity in our example, this means that A must be chosen. The larger this value of K is, the stronger this unanimity notion gets. The second ingredient that I want to consider is strategic proofness. And for that, I want to first introduce what's a manipulation. And for that, I think it's great to consider an example and just consider here the preference of voter 3. He prefers A the least, but A is currently the winner of the election. Now, he might just misreport his true preferences, so he might report C as his best alternative, and then the plurality rule would choose A and C with a probability of a half each, just because both alternatives are top ranked twice. This is beneficial for voter 3 because he prefers C to A and C has now a winning chance. So this voter has an intent to lie about his true preferences, and that's why we call the plurality manipulable. In general, we say that a social decision scheme is manipulable if a voter can benefit by lying about his true preferences. Clearly, manipulable social decision schemes are not appealing because voters may now lie about their true preferences, and if they don't get the true preferences of the voters, I cannot really make a good group decision anymore. Therefore, we are interested in strategy-proof social decision schemes, which are just social decision schemes which can be manipulated by any voter in any situation. Now, this is still a quite informal definition. For defining it formally, we have to solve one problem. We have to compare the lotteries on alternatives, but we are only given these preference relations. And probably the most standard approach to that is to just assume that voters have utility functions. Then we can compute expected utilities and use those to compare the lotteries. Nevertheless, voters still submit the preference relations, and therefore it's common to quantify over the utility functions consistent with a preference relation. This idea leads to the well-known notion of SD strategy-proofness. So you probably know the definition which relies on stochastic dominance. I like to give the one which relies on utility functions. So for that definition, we consider two preference profiles R and R'. These only differ in the preference of a single voter I. That is our manipulator. This manipulator has a utility function U, and the only requirement here is that this utility function is consistent with its true preference Ri. And then what SD strategy requires is that voter I, the expected utility of voter I, when voting honestly, so when reporting R, is at least as large as his expected utility when lying. Or more formally, less formally, truth telling maximizes the expected utility of the voter. Now, this is a really strong way to define strategy proofness, just because we allow here all possible utility functions. And as a consequence, we get quite negative results. So for instance, Gilbert has shown that only random dictatorships are SD strategy proof and theory unanimous. That's known as the random dictatorship theorem. And later on, Benoit has shown that no SD strategy proof SDS actually satisfies one unanimity, which kind of means for our initial example, that it's really not possible to always choose A in such situations with a SD strategy proof SDS. Now, we could just give up, but the most plausible out of that is to weaken SD strategy proofness just because it's defined really, really strong, maybe too strong for practical applications. Therefore, I want to introduce U strategy proofness, and the idea here is quite similar to SD strategy proofness. So what we do here is, again, consider two preference profiles R and R'. We consider one voter, that is our manipulator. This voter has now a utility function, and now the important point is this utility function comes from a predefined set U. I don't have to consider all utility functions, but I define a set U beforehand and only have to focus on these utility functions. And then I again want that truth telling maximizes the expected utility of the voters. And now, if I choose U as the set of all utility functions, so that's what I indicated here with this R to the A, then this is exactly equivalent to SD strategy proofness. And if we choose smaller sets U, I get weaker strategy proofness notions. And for instance, I can't just exclude things that I don't like. For instance, I might say there are implausible utility functions in some application. For instance, utility functions with infinitesimally small differences between the utilities of alternatives might be implausible in practice. Therefore, I can't just say, okay, I don't want to have these in my sets. This is from the practical side. Also from the theoretical side, this usage proofness is quite nice because it allows a finer analysis. So in principle, I can now ask for every SDS for which set of utility functions am I strategy proof. Or I get strong impossibilities, but just using very strongly restricted sets of utility functions, which kind of tells me the real reason for these impossibilities. And based on this notion, we can, for instance, show that usage prudence allows for decisive SDSs in the sense of k-unanimity. So for instance, we can modify the random dictatorship rule. So that rule here, this is probably well known. This random dictatorship, the uniform random dictatorship assigns probabilities proportional to the probability score of an alternative. So that means if an alternative is top ranked by k voters, it's get a probability of k divided by n. Now what we can do is we can just say, okay, if there's no clear winner, we do this random dictatorship. And if there is a clear winner, so if an alternative is top ranked by all but k voters, we just return this alternative with a probability of 1. So it's clear that this rule RDK is k-unanimous. And it turns out it's actually used to proof for if the utility functions satisfy this requirement here. And what this requirement roughly says is that the utility gap between the best alternative of the voters and the second best alternative of the voters must be sufficiently big. So in particular, it must be bigger than k times the gap between the second best alternative of the voters and the least preferred alternatives, and the utility of the least preferred alternatives of the voters. Now, it's nice that we have this positive result here. We have decisiveness and some degree of stretch proofness. The main problem is that we have here this k in our inequality, which means the larger k gets, or the larger n gets, the less appealing the set of utility functions is. One way out of that is just another approach. We can define this omni rule, which relies on a very similar idea. So first, let me define this top rule here. So what this thing does is it just randomizes uniformly among the alternatives that are at least top ranked once. And what it can do then is the same idea. If there is a clear winner, which means in this case that an alternative is top ranked by an absolute majority of the voters, then we assign this probability of 1 to this alternative, and otherwise we just return the outcome of the top rule. And for this, for Omni, we can show, so it's obviously, if there's an absolute majority of the voters that agree on an alternative, it's chosen with probability 1, so it satisfies this degree of unanimity. And also use stretchy proof if the difference between U1 and U2 is again big enough. Now, big enough depends here on M. If M is small, like 3 or 4, this is actually quite plausible and quite a positive result. Again, for larger M, this requirement becomes quite unrealistic. This kind of leads to the question, what you can do in general. And unfortunately, it turns out that with these approaches, we will not be able to get that much better results, and because we have a really strong possibility here. So what I could show is that there's no neutral rank-based social decision machine that satisfies the usage proofness really for a single utility function here, and k-unanimity if the gap between the utilities here is too small, between the best and the second best alternative. So that's quite negative because it means we really need this large gap between the best and the second best alternative of the voters, at least if we focus on rank-based social decision machines. And just to get some intuition about what this means, if we have 4 alternatives, body utilities already result in impossibilities. Now, these were quite a lot of formulas. Let me give you a bit of an intuition what these results really mean. What you can nicely do with these results is you can just pick one utility function and for some set of alternatives. So what I did here is assume we have, I have 5 alternatives, and I fixed the utility of the second best, third best, fourth best, and fifth best alternative of the voters. And what you can now do is you can compute how large U1 must be in order to achieve stretch proofness or in order to run in our impossibility. And on the horizontal axis, I additionally display the degree of k-unanimity which is achieved. And what you see here is, for instance, that with larger k, this RDK rule requires an increasing amount of utility on the best alternatives. That's bad. In contrast, Omni does not require such an increasing amount, but it's just already really large. So Omni needs that U1 is 9. In contrast, U2 is 3, so that's already 3 times the amount of U2, and we only have 5 alternatives. However, these results are quite tight because this red area here is where our impossibility triggers, and so we cannot really improve ourselves with rank-based social decision machines. Now, that kind of leads to the question, what if we just omitted that rank-basedness axiom, which I did not formally define so far? So in principle, things turn not out to be that much more positive. For instance, we can also consider consistent SDSs. And for these, we get a similar impossibility, even stronger, because we don't need a requirement on U stretch on the U. So this kind of leads to the key insight. Stretch proofs is hard even if you just consider few utility functions, and in particular, it is difficult if we have utility functions that are indecisive in some sense between the best and second best alternatives. So if there's a small gap in the utilities, we cannot really get decisive search decision trees out there. All right. I want to finish with this slide. Thank you for your attention.
Thank you very much, Patrick. And I think Paolo has a question for you. I don't know, Paolo, if you want to ask it directly.
Sure. Let me see. Yeah, it's a very short question, so it's quite easy to ask it directly. So how do we know what a good restriction is of the utility function if we cannot have this information from the agents? Thank you.
So in principle, we would like to get as weak as possible restriction. So the set use should be as large as possible, because that just means we are stretch proof for large sets of possible voters, right? That will not work out. Therefore, what we would really need to have to do is we have to kind of sample what and do some surveys what are common utilities in some sense, and try to achieve stretch proofs for these types of utility functions then.
Okay, thank you. We can take it offline because I'm very interested in also a follow-up conversation. Thank you. Bye.
Sure.
Thank you very much. I would move to the next talk, but I really encourage everybody to reach out in the chat to the presenter if you have any further question. And hopefully maybe we can have also a little bit more discussion during the break if you want. So we have next presentation. I'm not sure if who is the presenter.
Hello, it's me.
Hello.
Yeah. Let me share my screen. I guess all of you can see my screen, right?
Yep, perfect.
Okay. Hello everyone. Today I would like to introduce our work, Load Balancing Game in Loss Communication Networks. My name is Chenghao Wang from University of Nebraska-Lincoln. This is a joint work with Cheng Liu from INSA, France. Okay, here's the outline. First, I will introduce this problem, and then is the model, and then is our results on performance analysis and experiments. Okay, for the motivation, this is actually a different problem from social choice. It's about packet switching. As we know, in packet switching telecommunication networks or wireless networks, the packet may lose due to two types of reasons. The first type of packet loss is the congestion loss. It happens due to buffer overflows because usually the buffering is limited or restricted or have capacities. And the second types of packet loss is the random non-congestion loss. It happens due to transmission channel, for example, the radio channel. Okay, let's see the figure for an illustration. In this figure, there are several senders or users who wants to send the packet to the receiver along two possible routes or two possible ways. One is DP, is the direct path, and the second one is IP, indirect path. Every packet along the indirect path will incur a non-congestion loss, and every packet along either IP or DP will incur a congestion loss. So this is the packet loss. Actually, there are many works study the load balancing in loss networks, for example, telecommunication systems and wireless networks. Our work is grounded on the load balancing game studied by Curry 2014 and tutorial in 2020. These two works consider the load balancing games in a very limited or restricted loss network. It consists of only 2 sources and 1 destinations. In this game, every user or sender has 2 possible strategies. One is DP, the direct path, and the second is IP, indirect path. So one paper consider pure strategies and another consider mixed strategies. Actually, our work provides a generalization of existing works on the load balancing game. We provide a tractable mathematical framework to analyze the Nash equilibrium and the price of energy, POA, in loss communication networks. We consider multiple sources and strategies. Let's see the traffic model in this figure. Okay, in this figure, there are M sources, S1, S2 to Sm. Each source Si, there are Ni users arriving at it. You can see N1 users arriving at S1, N2 users arriving at S2. So every user it can have 2 types of routes. One is the direct path or DP. For example, the user arriving at S1, he can choose the direct path S1D directly. It consists of a single link, S1D. And an alternative strategy is a 2-hop indirect path, IP. So it may be S1, S2D. It consists of 2 steps, or S1, SMD. So it's 2-hop. So every such strategy is SISJD is called an indirect path. For each path, there may happen the packet loss. For every direct link, SID, going from the source to the destination directly, the packet may have a congestion loss due to the limited buffering. And for every relay link, between 2 sources, Si, Sj, there is a relay loss. It happens with a fixed probability Q. Okay, we need more notations to define this model. Okay, phi is the every user the packet flow of every user actually follows a Poisson distribution with a rate phi, and we assume the transmission time or service time of a packet in any direct link SD follows an exponential distribution with a rate mu. And for every strategy profile P, we define TIP. The flow over every link SID is a Poisson process with a rate TIP. It is actually TIP equals the total rates of all DP packets arriving at SI plus 1 minus Q times the total rates of IP packets arriving at SI. Here, 1 minus Q is the successful probability after relaying, because as we know, Q is the relay loss. So 1 minus Q is the successful probability after the relay. Okay, now we can define the congestion loss probability over every direct link SID is defined as Ti over Ti plus mu. So let's see this figure for illustration. We can see that between every relay link S1, S2 or S1, SM, a packet, the successful probability of a packet over this relay link is 1 minus Q. And for every direct link S1D or S2D, there is the successful probability of every packet along this direct link is mu over T1 plus mu. So this is the model. Now we can define the social traffic in this system. We measure the system efficiency by the concept of total traffic. The total traffic has two equivalent definitions. The first definition is from the links perspective. It is the summation of total rates over all direct links. For example, in the direct link SID, the traffic rate is Ti, and the successful probability is mu over Ti plus mu. So Ti times mu over Ti plus mu is the successful packet rate over this direct link. And the other definition is from the user's perspective. Every user K has a traffic rate phi. However, the phi needs to minus the loss rate. LR is the loss rate of K. So phi minus the loss rate is the successful traffic rate. Now we can define the Nash equilibrium of this lower balancing game. We say an arbitrary strategy profile P is a Nash equilibrium if no player can decrease her loss probability or loss rate by unilaterally deviating to any other strategy. That is, the loss rate cannot decrease. Okay, we can also define the price of energy of this game, POA. The POA measures the efficiency of NEs, Nash equilibriums. It's defined as the ratio between the optimal traffic rate over the traffic rate of the worst NE. Okay, let's say an example to better understand this model. We consider an instance with just two sources, S1, S2, and only one user arriving at S1 and one user arriving at S2. We assume the relay loss probability Q is a sufficiently small positive value. And we consider the strategy profile P in which both users choosing IP. That is, user 1 choosing the indirect path S1, S2D, and user 2 choose S2, S1D. Then in this strategy profile, the traffic rate over each direct link SID is 1 minus Q times phi here, because 1 minus Q is the successful probability after relaying, and phi is the traffic rate of each user. And the total traffic is 2 times this traffic rate, then times the successful probability after congestion. So the loss probability consists of two terms. The first term Q is the relay loss probability, it's a fixed probability. And the second term is 1 minus Q times the congestion loss probability. It's not hard to see that if a user deviates to DP, then her loss probability will increase. So P is a Nash equilibrium. However, on the other hand, the optimal solution is that both users choose DP. Then the optimal total traffic is this one, which is larger than the original traffic rate of P. So it implies that the POA is larger than 1. Okay, let's see our results. We first consider the setting with two sources. We assume N1 is no less than N2. Actually, this setting is also a generalization of existing walks because those walks only consider the case with N1 exactly equals N2. We denote a solution by U1, U2 by the number of players choosing DP. Then we find that if a condition, this condition holds, then the solution gamma N2 is optimal. Otherwise, the solution N1, N2 is optimal, which means all users choosing DP is optimal. And we also provide a characterization of Nash equilibriums for an arbitrary strategy profile P. We provide a sufficient and necessary condition for it can be a Nash equilibrium. And furthermore, we show the existence for every instance there exists a Nash equilibrium. And furthermore, we provide an upper bound on the price of energy. The POA is no more than 1 plus this term. And in particular, when mu is sufficiently small, mu is small, then the price of energy approaches to 1. For the multiple source case, we provide similar but more complicated results. So optimal solution, NE, and POA. And lastly, let me simply briefly introduce the experiment results. Let's say we consider the price of energy, how it changes. The price of energy is depicted in the blue curve. And for figure A, you can see when the relay loss probability Q increases, then the POA first increase and then decrease and converges to 1. And in the second figure, figure B, when the mu increase, also the price of energy first increase and then decrease and converges to 1. And for figure C, it has the same blue curve. Lastly, to conclude, our work is a generalization of existing works on load balancing game in loss networks. We show how to maximize the total traffic rate and provide characterization of Nash equilibrium and the upper bound on the price of energy. So then there may have several interesting directions because we only consider pure strategies. So it may be interesting to consider mixed strategies with multiple sources. And we only consider the 2-hop indirect path. So it may be interesting to consider the multi-hop indirect path, and also to consider the case with the source have different service rates, mu1, mu2, mu-i, mu-j, like that. That's it. Thank you.
Thank you very much for your presentation. Maybe while the next speaker is setting up, I was wondering if anybody has any question. Otherwise, I have a quick question. As the future step you were mentioning about mixed strategies and other possibility, but I was wondering if you are considering also including consideration about the current balance of the network and potentially the expected next request that we're going to get on the network.
Yeah. So
just wondering if these are things that you are considering as possible steps, or like in terms of the dynamicity of the system, the current load.
Yeah, it may be possible to consider.
So maybe we can take this offline in the chat. Is
okay.
Too much for now, for a discussion now. I'll pick it up in the chat.
Let me stop sharing.
Okay. Thank you very much.
Thank you.
Thank you, Nicolas. If you're ready to go, I'll give you the stage.
Hey everyone, so I'm Nicholas, and this is joint work with my advisors, Yair, Zik, and John Scarlett. Our work looks into individual and group fairness in the problem of allocating indivisible goods. Okay, so the problem of how to fairly allocate indivisible goods is a fundamental and long-standing one in the field, and many works, both more established as well as more recent ones, have explored a variety of distributive justice criteria that falls broadly into two categories, right? The first, of course, is individual fairness. How can we allocate goods in such a way such that individual agents are not envious of their peers? And the second being group fairness, basically ensuring that agents of certain groups, right? And by groups, we can refer to ethnicity, gender, or professional groups to ensure that they are treated fairly overall. Then a natural theoretical question that we can ask is, can we satisfy both individual and group fairness concurrently? So we went down this line of inquiry with the goal to establish efficient mechanisms that can concurrently ensure approximate individual and group fairness under certain assumptions. Right, we assume that groups are predetermined, so considering both individual and group fairness and its compatibility in this setting is, to our knowledge, largely unexplored. Right, but it's a really important question because in real life, there are many cases where sort of satisfying group fairness on top of individual demands is really important, and I'll show you a few examples now. So take, for instance, in conference peer review, right, whereby the reviewers are the goods and the papers are the agents, and the groups basically represent the various tracks. So for example, in AAMAS, I think there's learning adaptation, there's like robotics track, right, in the conference. And then not only should we actually treat papers fairly in that every paper should approximately get reviewers of comparable suitability and expertise, but tracks should also be getting reviewers, well, in the case where reviewers can belong to multiple tracks, they should get reviewers of comparable expertise and suitability as well. Right. Another example is in the allocation of public resources, such as housing or slots in public schools. So for example, in Singapore, public housing goes via a balloting system, and we have many ethnic groups in the country, right? So how then can the government allocate housing in a way such that individuals feel that they are treated fairly, but yet at the same time, not show any bias towards any ethnic or racial groups, right? So basically to treat them fairly as well. So for individual fairness, we consider relaxed version of classical properties such as like NV fairness up to one good, and it's up to any good, and it's up to one good version. And similar notions of group fairness, we make use of this notion called weighted NV freeness, which was more formally introduced in a recent work in AAMAS last year, and also in the first session, there was a presentation by Warud on picking sequences, which uses weighted NV free. Well, and similar notions like it have been used in the past as well. Okay, so this is basically the model that we consider. We have a set of agents, groups, and goods, right? And agents belong to a single predetermined group, right? And they have positive additive utility valuations for the goods, right? Individual fairness then use classical NV fairness property and its relaxations. WEF is just simply a generalization. And what WEF or weighted NV fairness means is that it is basically saying my group's valuation for my group's bundle, right, normalized by my weight, or in this case, the number of agents in my group, right, should be at least as much as my group's valuation for your group's bundle, right? Divide by the number of agents in your group, which is your weight. And then we can, of course, derive the relaxation of up to one good by dropping one good overall from the entire like other group bundle. Okay, so we focused on additive valuation functions and looked into three main cases. The first we term as all common valuations, where all agents across all the groups have a common single valuation function. Right? And then the second case is the group common valuations, where agents within a group can have the same valuation function, but valuations across groups may differ. And of course, the last case is general valuations, where agents within the group can potentially have different valuations for good. And we can see that for each of these cases, we have varying levels of guarantees. Right? For the simplest case, we basically have EFX or NV free up to any good plus weighted NV free up to one good. And then for the case of group common valuations, we get EF1 plus WEF1. And in the last case of general valuations, we get EF1 and this notion of WEF1 and expectation up to a factor of 1/3. Right? I'll talk more about that case later. But now I'll just briefly detail each of these cases. So in the all common valuations case, I think it's well known in the literature that when valuations are additive, then individuals of NV free up to any good EFX is the most common and arguably one of the stronger approximations under this setting, right? And so one example is to achieve EFX is, for example, well, I think some papers call it the egalitarian or sequential egalitarian or something, or rather the sequential maximum algorithm, where we allocate goods sequentially to the worst off agent at any stage. Right, so the first step in our proposed algorithm is to do an EFX allocation using any kind of EFX algorithm that you have. We then get these bundles in red and the green goods in those bundles. So that's basically an EFX bundle where the red one can represent sort of an agent that was preliminary allocated one of these bundles. Right, and then what we basically do is after this allocation, we basically treat these bundles, the red ones, as goods, right? And then we simply do a reallocation, right? We reallocate to agents via an algorithm that is known to be weighted and briefly up to one good, right? Or we call the iterative weighted round robin algorithm, the IWRR, which I'll detail later. And where in this case, where each agent gets exactly one good, right? Or good. So the black rectangles basically indicate the groups. Then basically after this allocation, each agent will then get the goods corresponding to whatever representative good, the one in red or the bundle that they were allocated, right? The green, they eventually get the green goods in that bundle. And so obviously we can see that these are individually EFX bundles, and I did not change them, right? They remain in the red sort of circle throughout, meaning that it is EFX, is individually EFX. And I guess the slightly more complicated, the more complex property that we show is that this way of allocating also maintains that weighted and briefly up to one good property across the groups, right? Where we only drop one good in the black square. So we just drop one of the green good, right? In the weighted NV comparison. Okay, so that's for the first case. And then for the second case, where we are able to achieve EF1 plus WEF1, we have group common valuations, whereby agents within each group share a common valuation functions, but it may differ across groups. Right? And so the algorithm that we propose basically combines the popular round robin algorithm along with the weighted round robin algorithm in the literature that was introduced in the weighted NV free paper. Basically at each stage, I first pick a group with the least weighted bundle size. So it's the number of items in that group's bundle divided by the weight of that group, right? That's the weighted bundle size. I pick the group with the least weighted bundle size. And then within that group, I pick an agent that has the smallest bundle size, right? And then I allocate to the agent. And I just keep doing this until all the goods are allocated. So it's a sequential algorithm. And what we can observe is that on an individual level, it's exactly a round robin, right? Which was previously proven to return an EF1 allocation. And at a group level, it is exactly a weighted round robin, which was also proven to return weighted and free up to one good allocation. So very nicely, we get to piggyback on these two properties of these two algorithms combined, and basically are able to achieve individual and group NV freeness concurrently in this case. Okay, so the third and final case that we had was for general additive valuations. Right? And this also presents some difficulties, which is worth highlighting. So just like how individual NV freeness is defined, the intuition for weighted NV freeness is defined as, again, my group's value for its own bundle should be at least as my group's value for another group's bundle. Right? And in the group sense, defining a group's valuation for another group's bundle is not straightforward if valuations within the group can differ. Right? Because a group's value would then depend on some belief of, if I had that group's bundle, how would I have allocated it to my agents? Right? And how much better off would my agents have been as compared to their current allocation? Right? And then collectively, we can then define the group's valuation as a comparison in NV. Right? So considering such reallocations would basically be what I call sort of an allocation-based approach, right? And there are many things that we can do in this space as well. But what we opted for, the opposite, would be if we don't want to consider an allocation-based approach, but we simply take an on-average approach, right? Then we can basically define weighted NV free in expectation, right? So basically, on average, how much better would I, the group, have been if I had that group's bundle, right? And then we basically use this to define group or weighted NV. And we prove that the IWRR, or the iterative weighted round robin algorithm, would then achieve this property up to a constant factor of 1/3. Okay, so an important point that I'd like to raise from our results is that there's an inherent difficulty in concurrently achieving existing notions of individual and group fairness out there in the literature. So now suppose that we have some real life application that desires for an algorithm that is both individually and group fair. Under more complex settings, this may not be possible, right? Or the approximation may be unsatisfactory. So there may be questions regarding the suitability of this particular group fairness notions that we chose, but other notions that exist are arguably even stronger than WEF in certain aspects. And I'll be happy to discuss more on this offline. So this work basically gives us a first look into reconciling fairness at these two levels, and hopefully let us think more about novel notions of distributive fairness that maybe relies directly on the relationship between individuals and their group structures instead. So just to make it concrete in our work, in the appendix, we also propose two of such properties. We show that our algorithms satisfy them, but ultimately we hope that this sort of opens more avenues into this area. So just for example, the first property that we propose is what we call like proportional envy freeness, which is kind of a hybrid between weighted envy freeness on a group level, right? Weighted envy freeness is across groups, and proportionality on an individual level. So we sort of connect the individual to group. It basically says that every individual agent, right, should value their bundle as much as they value an average agent in another group, in any other group, right? And our algorithm basically satisfies this notion approximately up to one group, right? And then the second property is group stability, which is possibly applicable in scenarios where group membership can be declared prior to the allocation process. So it's basically not inherent, but taken as a preference. Then we would like there to be like not have some kind of regret that happens, right? And that they could have been better if they had chosen to join another group. So just one example, but in a hypothetical peer review setting, right? If a paper could possibly be submitted to like 2 tracks, but is more suitable in one of the tracks, but the track that would be slightly less suitable is, for example, known to be way easier for a paper to get accepted. And then the authors might be incentivized to submit to that track instead. And then having an allocation algorithm in such a context that approximately guarantees you this property might be useful in ensuring that authors submit papers to tracks that best represent their paper rather than strategizing for easy acceptance. So hopefully this will allow us to think about moving to look directly at notions that take into consideration individual and group fairness in many societal applications. Okay, yeah, so that's the end of my presentation. Thanks.
I see that Aris has his hand up.
Yeah, I can go first. So I had a question regarding your treatment of this dual treatment where you have individual fairness on one side and group fairness on the other side. So there are a few concepts, for example, Nisag Shah, Kunitzer, Freeman, and Shaw, they had a paper on group envy fairness up to one item. And the elegance of that particular concept is that it simultaneously achieves individual fairness as well as group fairness at the same time. And you don't even have to take care of explicit groups, even groups which you're not familiar with or you're not aware of. Fairness with respect to those groups is also captured without explicitly taking care of these concerns. So I was wondering why you didn't explore that further.
Oh, okay. So the paper by Konitzer and yeah, their paper looked at all possible partitions of agents, right, into groups, and sort of their notion, their definition of group fairness had, because it's so strong, like it considers all possible partitions, they have to drop one good per agent, right, in the group, in order to that's basically the approximation that they use. So in our case, they raise an open question also. That suppose that we have fixed groups, right? Then can we like get something better? So we opted for this because in this case, weighted envy freeness was defined and it could be used for fixed groups. And it very nice, like the approximation is basically just dropping one good per group. So we found that to be rather attractive, especially in the case of fixed groups. So that's why we opted for this. But definitely the way the Konitzer paper approached, I think they used some kind of Pareto, like no Pareto dominating sort of allocation in that comparison of group fairness. That is one possible avenue of exploration that we can consider moving forward in this setting.
Thank you very much. And I would again encourage people to use the chat to ask extra questions, but at the moment we need to move on with the last paper talk for the session.
The screen.
Hello.
Yeah, it's me.
Thank you. Perfect.
You see it?
Yep.
Okay, so hi, I'm Noam Chazon from Ariel University, Israel. And I will be presenting the work Strategic Voting in Negotiating Teams, which is a joint work with my student, Leora Schmerler. So we are all familiar with voting. This is a process that aggregates the preferences of different voters in order to reach a joint decision. And usually in voting, the voting rule outputs hopefully one winning candidate, and then this process is called social choice function. Sometimes we are interested in a complete preference order as the winner that will represent somehow the preferences of the voters. And then this process is called a social welfare function. Negotiation is another process for reaching a joint decision. And usually in negotiation, there's some sort of dialogue between the agent. Usually also the preferences are represented by utility functions. And the negotiation protocol defines the interaction, which messages are sent and when. And there's many types of negotiations, but the most common negotiation is bilateral negotiation, where we have only two negotiating parties. And indeed, there are some negotiation protocols that can work with ordinal preferences, where each agent has a complete linear order over the candidates. And again, the negotiation protocol defines the interaction between the agents. Now, in many settings, each negotiating party is a single entity. However, in some settings, a negotiation party may be composed of different agents. And social scientists call this situation negotiating team. For example, consider the European Union Council that is negotiating with the UK regarding the Brexit. So the EU Council may be composed of different countries with possibly different preferences. So how do they decide on their strategy? I mean, which offer to accept, which offer to reject, which outcome to offer to the other side? Well, then they can use voting, but it is known that voting is prone to manipulation. And indeed, the problem of manipulation do exist in this setting of negotiation team. Consider again our example. And now suppose that Portugal, that currently holds the presidency of the EU Council, is familiar with the preferences of her team members. We may also assume that Portugal is familiar with the preferences of the other negotiating party and with the negotiation protocol. And now if we assume that both parties are rational and they follow some sub-imperfect equilibrium strategies, then Portugal may be able to reason what will be the outcome of the negotiation. And then maybe Portugal will have an incentive to switch between candidate and misreport her preferences in order such that a more preferred outcome candidate will become the outcome of the negotiation. So in our paper, we study exactly this problem of manipulation in the context of negotiating teams. We use positional scoring rules as social welfare functions. We use the voting by alternating offers and vetoes negotiation protocol, and I'll give all the details in a minute. And we analyze both constructive manipulation, where the goal is that a specific candidate will be the outcome of the negotiation, and destructive manipulation, where the goal is that a specific candidate will not be the outcome of the negotiation, sorry. And we show that for single manipulator, the problem is in P for any scoring rule. For coalitional manipulation, it is still in P for approval-based rule, but we show that it becomes hard for Bourda. However, we provided an approximation algorithm, and again, note that all of our results hold both for constructive and destructive manipulation. So to summarize our contribution before I go into all the details, our work is the first to formally analyze voting manipulation in the context of negotiation. We actually study manipulation of social welfare function, which was rarely studied since you need to assume something about the preferences of the voter regarding different preference orders. And I think a takeaway from our work is that analyzing voting rule within an actual context is important and interesting, since it provides us with a better and deeper understanding of voting rules. So let me give you just some details about our settings and algorithms. We assume that the voters rank the candidates, so we are given completely in our orders. We use scoring rules. Scoring rules are characterized by score vectors. Score vector is S sub n-1 till S sub 0, and each voter awards S sub n-1 points to her most preferred candidate, S n-2 points to her second most ranked candidate, and so on. And then the candidate with the highest aggregated score is ranked first, the candidate with the second highest score is ranked second, and so on. We have result for some specific positional scoring rules. The first family is approval-based rule. It's a family of rules where the score vector consists of x1s and then followed by zeros, and plurality is part of this family where you give 1 point for your most preferred candidate. Veto is part of this family where you give 0 points to your least preferred, 0 point to your least preferred candidate, and of course, key approval. We also study the border rule where you give n-1 points to your most preferred candidate, n-2 to your second preferred candidate, and so on. Now for the negotiation protocol, use the valve negotiation protocol, which works as follows. Suppose that we have two negotiating parties, P1 and P2, and a set of candidates composed of A, B, C, and D. Suppose that P1 initiates the negotiation, then P1 can offer every candidate, for example, in this example, C, and now P2 can either accept or reject. If P2 accepts, then C is the negotiation result. If P2 decides to reject, then C is removed from the table. Now the set of candidates composed of A, B, and D, and now it's P2's turn to offer. So for example, in this case, P2 offered A, and then it's P1's turn to either accept or reject. So using this protocol, we'll have at most M rounds till we have a decision, which candidate is the negotiation result. Why did we choose this protocol? It has several desirable properties. It is intuitive, easy to understand, and the negotiation result is Pareto optimal. And most importantly, if we assume that both parties are rational and they follow a subgame perfect equilibrium, then we can identify who will be the result of the negotiation by a simple procedure, the RC bargaining rule, or equivalently, it's actually equivalent to the Buckley voting rule. It works as follows. We look on the most preferred candidates of both parties, and if there is an intersection, then we are done. Otherwise, we look on the two most preferred candidates, and so on till, like in this example, we found an intersection. So we know that B will be the result of the negotiation. Now, let me describe a little bit of, give you some details about our algorithms. Let's start with manipulation by a single voter. Suppose that we have 4 non-manipulators, and we have the preferences of the other party, and suppose that we use Bourdin, and we want to make P the negotiation result. So what do we do? First, we need to guess the iteration number, denoted by I, in which RC terminates. Then we compute PT. PT is the preferences, the outcome of the social welfare function over the preferences of the non-manipulators. Then we identify the set H. H is the set of I-1 most preferred candidates according to PT, which are not part of the I most preferred candidate in PO. Okay, and then we also add P to the set H. So in this example, I equals 2. So the set H composed of A and P. Now we place H in reverse order with regards to the order in PT in the preferences of the manipulator, and we place the remaining candidate in a reverse order. And note, that's interesting, that unlike the regular manipulation, where you put your most preferred candidate in the first position, here we put P in the second position, even though we want P to be the negotiation result. And if we would have placed P in the first position, we won't find any manipulation. So that's an interesting phenomena here. So after we decided about the preference of the manipulator, we can compute what will be the outcome of the social welfare function, and hopefully, like in this example, we'll have P as the negotiation result. What do we do if we have a coalition of manipulation? Actually, quite the same in a greedy manner. That is, we can guess the iteration in which RC terminates. In this example, 3. We compute PT, we identify the set H, And then for each manipulator, we place H in reverse order, we place the remaining candidates in reverse order. And this is very important, we update PT, we update the result of the social welfare function. Why? Since when we move to the next manipulator, we need to decide of the order of the candidate in H. Note that in each stage, in each manipulator, the set H does not change, but the order may change. For example, here, this manipulator puts C above E, since in PT, E is preferred over C, okay? And then we move to the next manipulator, and we can compute now the output of the social welfare function, and verify, again, in this example, we can verify that P is the negotiation result. And note that this algorithm and also the previous algorithm, they both work both for constructive and destructive manipulation. For destructive manipulation, we only need to change a little bit the definition of H, but it's actually the same procedure. So to summarize, we analyzed manipulation in the context of negotiation. We actually study manipulation of social welfare functions. We provided two intuitive algorithms, which are quite general. I mean, they hold both for constructive and destructive manipulation. And also note that our algorithm for coalitional manipulation, it provides an exact solution for approval-based rule, and the same algorithm serves as an approximation for Borda. Okay, this is also quite interesting. Our next steps is, of course, to analyze other voting rules and also to extend this framework and study manipulation of voting rules in other contexts. That's it. Thank you.
Thank you very much, Noam. Is there any question? I have probably it's a silly question, but here you assume that the set of options is known by both parties of the negotiation. Is this correct? So
Yes.
I assume not having that information would invalidate the analysis you have done, or have you had any thought about that?
Well, usually in negotiation, as I said before, there is assumption that the preferences are represented by a utility function, and then the set of possible outcomes is not known in advance. That's right. But there are some settings where the set of outcomes, but we assume, is known in advance. Yeah.
Okay.
So this is the setting.
Thank you. It was very interesting. If there are no other questions, maybe we will go with a break. We are actually on time for the invited talk, but I think probably people would appreciate a 5 minutes break at this point, since we skipped the previous one too. So let's say let's take like 10 minutes. So we'll coming back in 10:30 for Yannis' talk, and I'll set up the breakout room as before. Thank you again, and see you in 9 minutes. Hello, we should be back all in the main Zoom room. I'm not sure if the break room actually works, since a lot of people were taking breaks. Maybe we can revisit the strategy for next break. I can see, I assume everybody's back in the main room, but we still have a couple of minutes break.
You can force cancel the break rooms. I mean,
yeah, I did.
Oh, you did. Okay. So,
yeah. There was like only one person or at most two person active in each break room. So I thought instead of leaving people alone, it would be nice to bring them back all together. Okay, we have Yanis. Hello, Yanis.
Hi. Hi, Sophia.
Okay. At 1 minute, we're going to start. I don't know if you want to start sharing your slide.
Yeah. Let me try.
Perfect.
So can you see it? Is it okay?
Yep, in presentation mode. That's perfect. Okay, so let's start on time with our delay. And let me introduce Yanis Karagiannis as our next invited speaker. Yanis is a professor at the Department of Computer Science at Aarhus University. But before this, he's been for a long time at the University of Patras. He started there by getting his diploma, then he moved on in obtaining a PhD, and then he was also a faculty member there. And I think I can like generally summarize your interest in algorithm design and analysis, in particular in the area of interaction between computer science and economics. And I'll just give back the scene to you, Yanis. Thank you very much.
Thank you very much. Thanks for the invitation. Thanks everybody for coming to this talk. So I'm going to talk about impartial selection, additive approximation guarantees and priors. So I have structured the presentation into three parts. So first I'll give the definition of the problem, some examples. I'll talk about previous work. And then I plan to cover briefly two papers. These are joint work with George Christodoulou and Nikos Protopapas from the University of Liverpool. The first introduces the notion of additive approximation guarantees in impartial selection, and the second one uses tries to use prior information about the input to get improved results. So let's start with impartial selection first. So the story is that we have the members of the society who wish to give their annual award to one of the members of the society, let's say the most distinguished member. And the setting is that each member can vote any other member of the society for the award. So each member here is a voter and a candidate. And there are several scenarios where this story is relevant. So, So this is just one of them. So there's no typo in the title here. So this is the Professional Football Association Men's Players Player of the Year. It's the name of the annual award. The football players in England and the Wales give to their colleagues, to the best among them. And according to John Terry, who got the award in 2005, this is the ultimate accolade to be voted for by your fellow professionals. Of course, there are other settings where this problem is relevant. Scientific communities or the movies industry or other communities want to give their annual awards to the best of their members for the particular year or for many years. Other examples include selecting the chair of a committee among the members, or the selection of scientific grants to be funded, or the papal conclave is another example. In all these cases, the members of the community vote and are at the same time candidates. So there is a major requirement of impartiality. So we would like to design mechanisms for selecting who will get the award, so that the agents are not able to increase their chance of being selected by acting strategically. And let's see an example. So there is an obvious algorithm to use here. So the algorithm that selects the member of the community with the highest number of votes. And we can represent this voting profile with this graph. So the nodes in this graph are the agents, are the voters. And the edges, an edge indicates, for example, then an edge from node 2 to node 1 indicates that node 2 votes for node 1. So assume that this is the true preferences of the voters, and this is what if they had no chance to increase their probability of being selected, that's what every voter would do. Instead, each node, our assumption is that each node wants to win. So actually, impartiality is different than the standard assumption of truthfulness in mechanism design. So here, the voters care just about being selected themselves. And since I'm going to present an example from a deterministic algorithm, I have to define what happens in the case of ties. And let's say that here the node with the lowest ID wins when there are more than 2 nodes that have the same degree. So in the following, when I'm saying degree, I mean in degree. I mean number of votes that a node has from other nodes. Okay, so in this example, we have 2 nodes, node 2 and 5, that have the highest degree of 3. Node 2 is the winner because it has the lowest ID. And now the situation is as follows. So node 5, assume that the nodes have knowledge of of the whole profile. So now node 5 thinks that I have the same support from the community as node 2, and the only reason that he's the winner and I'm not the winner is that I'm voting for him, and this makes us have the same number of votes, and he wins because of the minimum ID. So the apparent strategic decision for node 5 is to remove the directed edge to node 2, and then the only node that has a degree of 3 is node 5 and becomes the winner. Okay, so one would think, so that's an example of the strategic behavior that alters the outcome of this mechanism. And one would think that that's not a big deal. We had 2 nodes of maximum support, and strategic behavior just led one of the 2 to be the winner, to be selected. That's not what the algorithm was. So the outcome is not the one that the algorithm should return the way described, but it's a good outcome anyway. So let's see another example that shows that this strategic behavior can be catastrophic in this case. So we have this profile, and here we have a node that has the maximum possible degree. So node 6 here has incoming edges from any other node of the graph, and node 1 on the other side has no support at all. And now strategic behavior, so the winner is node 6, and strategic behavior by node 5 would remove the edge from 5 to 6. So now, and then 6 and 5 would have the same degree of 4, but 5 becomes the winner because ties are resolved so that the lowest ID node wins. And then 4 acts similarly and becomes the winner, and 3 becomes the winner, and then 2 becomes the winner, and then the worst possible thing happened. So 1 became the winner. So essentially we're in an instance where there is a node that has the highest possible degree, but the strategic behavior of the agents results in one becoming the winner, and the bad news is that one has no support at all. Okay, so we would like to keep the requirement of impartial selection, but now we shouldn't aim for an optimal solution for selecting the guy with the highest degree, but instead will be fine with a good approximation ratio. So a good approximation ratio, let's say an approximation ratio of 2, would mean that we have a mechanism which, for any instance in which there is, let's say, the maximum degree overall nodes is delta, the mechanism selects some node that has degree at least delta over 2. And this is an approach that has been studied in the literature. And in order to achieve this good approximation ratio, randomization is important. Randomization has to be used. So I have an example here with just 2 agents, and assume that we use a deterministic mechanism. So in this very simple instance with 2 nodes and no edge between them, the mechanism has to return some of the 2 nodes as the winner. Let's say node 1. Then I claim that in this profile, well, where there is an edge from node 1 to node 1 should still be the winner. And why is this the case? Assume otherwise that in the second profile, node 2 is the winner. Then node 1 would have the incentive to hide his outgoing edge, and then will be at the first profile, in which strategic behavior would lead node 1 to become the winner. So, and then we can continue with this argument to the other 2 instances of this two node setting, and essentially we can conclude that there are 2 deterministic algorithms here. So one that always returns node 1, and another one that always returns node 2. And what is and why the approximation ratio is bad? Because if we look at this case here at the top right instance, the winner has degree 0, while there exists a node of degree 1. So the ratio goes to infinity. Okay, so randomization has been used in previous work, and here is a well-known algorithmic result by Alon, Fisher, Procaccia, and Tenenholz from 2011. So the input is again a directed graph, and the first step is to randomly partition the nodes into 2 sets: the set S and the set W. So W means the set of the potential winners, so the set of nodes which still have chances to become winners. And then at the second step, the node of among the potential winners, the one with the highest number of incoming edges from set S wins. Let's see an example. So this is a random partition. So we have 8 nodes. Randomly, we selected each node to be either in the green set or in the blue set. So among the 8 nodes, the nodes 1, 3, and 6 belong to the set W, and these are the potential winners. And now we ignore all edges from the nodes in the set W. We ignore all edges between nodes of the set S and just consider the edges from nodes of set S to nodes of set W. And then we compute the node with the highest degree from the edges we see, and this node is the winner. If we had ties here, we could resolve the ties according to the lowest IED tie-breaking rule. And the claim here is that this algorithm is a 4-approximation impartial algorithm or mechanism. So we'll show impartiality first, and impartiality follows because the node that is selected in set S cannot win. So this node is by definition not a winner. The nodes that are winners are in set W, but the edges that come out of this node are not taken into account at all. So these nodes have no way to affect the outcome of the mechanism. And a few words about the analysis. So let's assume that U star is the highest degree node in this instance. Then this highest degree node will be selected in the set of potential winners with probability 1/2. And then the expected in degree this node will have will be half its original degree, because each of the nodes that have edges to this node U star will be in set S with probability 1/2. And then we know that the node that will be selected as the winner at the end will be the one who has the maximum number of the coming edges from the set S, which will be at least the number of edges, to node Q star. And this inequality holds for the expected degree of the winner as well. And we get this 1/2, the probability that U star is in set W, times the degree of U star over 2 that this second argument gives us. So this gives the approximation ratio of 4. For some years, it was an open problem to close this gap. So there was also a lower bound in the original paper by Alon et al., lower bound of 2. So a few years later, Fisher and Klim closed this gap by extending in a non-trivial way the random partition method and obtained the best possible 2 approximating partial selection mechanism. So independently from the work of Alon et al., there is a paper of Holtzman and Moulin. Holtzman and Moulin focus on axiomatic properties of impartial selection, and among other results, they show that it's impossible to have an impartial mechanism that never selects as the winner a node of degree 0. So a winner of degree 0 is possible to select. There are also other papers. I'll say a few words about the paper of Bousquet et al. In the next slide. So at this point, I'm done with the first part of the talk. So in the following, we'll define. So more or less, this was previous work, and now I'm going to present results that we had in the 2 papers with George and Nikos. Okay, so first, we deviate from this approximation ratio, and we instead care about the additive approximation for impartial selection. And the reason for studying additive approximation is that the worst case scenario for the approximation ratio is for small graphs. So essentially, we could use the example that I presented with the 2-node example that I presented a few slides back to show that a lower bound of 2 on the approximation ratio. So for deterministic algorithms, we showed essentially that there are just 2 of them. The algorithm that always returns node 1 and the algorithm that always returns node 2. And both of them have infinite approximation ratio. If we use randomization, then there is an obvious algorithm that returns one of the 2 nodes equiprobably as the winner, and this algorithm would have an approximation ratio of 2. And so Fisher and Klim had similar observations, and there is a paper by Bousquet et al. That proved that if we don't care about instances in which the maximum in degree is small, then excellent approximations are possible. So 1 plus epsilon approximations of the maximum degree are possible by mechanisms that are impartial for instances with large maximum degree. So instead here we care about mechanisms that have a delta additive approximation, which means that for any node graph we can see as input, the difference of the maximum degree and the expected degree of the winner returned by the mechanism is at most this term of delta. So delta will in general be a function of the number of nodes. So our objective here is to design impartial selection mechanisms that have as low additive approximation as possible. And here is the first set of mechanisms that we have. So our mechanism, given an input graph, select first the sample set of node S. So this is the blue set. And W is again the nodes in the green set, which are defined as follows. So the nodes in set W are those that have incoming edges from the nodes in set S. And then the winner is selected according to some rule that the mechanism uses among the nodes in the set W. So again, W is the set of potential winners. So the set S somehow determines which the winner will be, either directly or indirectly. And the main difference with the algorithm of Allon et al. Is that there are also additional nodes that do not belong in any of the two sets. And we also have this definition of strong sample mechanism where the sample set is selected impartially as well. This does not this is not necessary for obtaining impartiality at the end, but that's a natural class of mechanism, and I mostly have the definition here because I use the term in the next slide. So this is a summary of the results we have for the additive approximation case. So our upper bound is this order of n to the 2/3 times some polynomial of the logarithm of n, additive approximation. And the lower bound for mechanisms that look like, that are sample mechanism, randomized sample mechanism is square root of n. So there is a small gap, but essentially we know that we can achieve a sublinear additive approximation close to square root of the number of nodes. So what is embarrassing here is that the only general lower bound we have for, and this is for deterministic algorithms, is an additive lower bound of 3. And it is technically it's very interesting to prove something better than that. If we start imposing restrictions on the mechanism, then we can prove additional lower bounds, higher lower bounds, which we actually do in our first paper. Okay, so here is a particular mechanism we have. So we call it this naive name simple case sample mechanism, because the mechanism is as simple as it can be. So in the first step, we form the sample set S by repeating k-node selections uniformly at random and with displacement. So we select the first node in the sample set by picking uniformly at random among all nodes. We select the second node, again picking uniformly at random among all nodes, and this can produce a sample set in which a node appears twice or even more. So this does not violate any of the properties that we have defined so far, and actually makes our life easier because we have because there is independence that can be used in the analysis. Okay, and then the node of set W is the one that has the highest in degree from the edges originated from S. So essentially, the mechanism looks very similar to the mechanism by Allon et al., but the crucial property here is that this K, the size of the sample set, should be small. So we cannot, a probability of 1/2 being on the set S or the set W as it was used before will not work in our case. And for the analysis, the important observation is that the number of incoming edges a node has from set S is actually a sum of binary random variables. And if the original expectation of node V is the degree of V, then the expected number of incoming edges from the sample nodes will be this quantity times K over N. So we have Bernoulli, a sum of Bernoulli random variables, and let's again assume that the node U star is the node that has the highest degree, let's say delta, and then we prove that the probability that some node of degree smaller than delta minus k wins is very, very small. And to do so, and after we do that, then essentially we know that the additive approximation of almost k can be achieved. So we need k to be small because we need to, so we need this node U star to be selected. So we need that node U star is not selected in the sample, so the sample size should be small. And also we care about this additive approximation of k, and we want this, so in order to make sure that the probability that no node of degree smaller than delta minus k has higher support from the sample set than the node U star is small. So this will happen only if k is large. Okay, so to get the best trade-off between the two properties, we use Hofding bound for analyzing the probability that a node of small degree will win, and by optimizing k, we get this n to the 2/3 result. So I've hidden many of the details of the analysis, but believe me, the main ideas are there, and the rest is essentially what is missing is what would make the proof really really accessible to somebody who really wants to verify it. Okay, so this is not the lower bound we have in the paper. This is a simple additive lower bound of 2 for deterministic mechanisms. So let me say a few words about this. I believe that this is it's a nice problem for students. So essentially, we want to show here that impartiality requires that that for any mechanism that one can consider, deterministic mechanism in this case, for some of the instances, the additive approximation will be at least 2. So again, we start with a deterministic algorithm that returns 1 as the winner in this 3-node example, and then let's consider not the whole space of instances, but we have identified these 2 additional profiles which are important. And in these profiles, we know, due to impartiality, that 3 will not be the winner in the second one, and 2 will not be the winner in the third one. So let's assume that 2 is the winner in, so it might be the case that either 1 or 2 is the winner in the second profile, and either 1 or 3 is the winner in the third profile. Let's assume that 1 is the winner in the second one. Then impartiality implies that when one votes, so when one deviates from the no outgoing edges case to the outgoing edges to the nodes 2 and 3, then it should still be the winner. Otherwise, impartiality would be violated. And here we have an instance where the winner has degree 0, the highest degree node has degree 2, so the additive approximation is at least 2. So we get a similar observation if we assume that the 1 is the winner in the third profile as well. Now let's assume that 2 is the winner in the second profile and 3 is the winner in the third profile. And then, unfortunately, we cannot define the winner in this fourth profile you can see here, because if we look at the second profile, impartiality implies that 2 should be the winner in the new profile. And if we look at the third profile, impartiality implies that 3 should also be the winner in the new profile, and we don't allow 2 winners in the same profile, but the definition of the problem. Our proof of the lower bound of 3 unsurprisingly starts with 4 nodes, and what one could wonder whether considering slightly larger examples would give us better lower bounds. Unfortunately, there's some key observation that we are missing, and it's not at all obvious to us. It's not at all clear to us how to prove something better of 3 at this point. Okay, so the open problem starts to close the gap between 3 and n-1. So n-1 is the trivial algorithm that selects any node, even of degree 0, and the deterministic case is widely open. And for randomized mechanisms, it's interesting to improve this n to the 2/3. Most probably with the improvement could be dramatic, but we should use mechanisms that have considerably different properties than the ones presented here. And of course, since we haven't proved any lower bound, constant additive approximation is still possible. Okay, so I've covered the second part of the talk, and for the third part, would like to use deterministic mechanisms. So we saw that in the worst case, deterministic mechanisms are pretty bad, but here we have we assume that we have some knowledge on the input. So we assume that the input is random, so it's a random n-node graph, and we know the probability distribution according to which this graph has been created. So our main assumption that restricts the problem is that there is voter independence. So the random edges outgoing from node U are selected independently of the random edges outgoing from node V. And the objective is, given the information we have about the probability distribution with which the input is produced, to design an impartial mechanism, deterministic impartial mechanism, with as low expected additive approximation as possible. And we have 3 different models, a hierarchy of distribution that has at the highest level the opinion poll model. So here its node selects its set of outgoing edges according to a probability distribution P sub V. So this probability distribution will give, let's say, probability 10% that I vote for Sofia and Reshev, probability 20% that I vote for Nisarg and Sofia, and probability 70% for voting for nobody. The a priori popularity model is simpler. So here we assume that each node has a popularity level of P sub V, and an edge to this node V exists independently with probability P sub V. And the simplest case of this a priori popularity model is the uniform model, where the probability is just 1/2. So the most general among these models is the opinion poll model. So this is the model which would like to answer our questions and to make our mechanism work on this model. We partially succeed in this. So the uniform model is, we don't expect to see it in practice, of course, and we use it to prove lower bounds. And the a priori popularity model is an intermediate model. We can argue that is realistic in some cases, but that's the model in which we have the most interesting results from the technical point of view. So I see there is a comment, so let me respond to that a bit later. So
Martin, do you want a question now, Yanis?
I think we can also take it after the talk.
Yeah, let's talk about that. Okay, so the first mechanism we consider in this prior information setting is the simplest one. Let's consider the mechanism that returns a fixed node as the winner, and this mechanism is pretty bad in the worst case, when worst case analysis is what we care about, because a fixed node may have degree 0 in some instances, which also have a node of degree n-1. But here, since we have information about the probability distribution that produces the input, we can select as this fixed node the node that has the highest expected degree. And then we can exploit this information and get a very good additive approximation of square root of n log n. So essentially here the even in our most general model, the degree of the nodes follow binomial probability distributions, and we select this node that has the red probability distribution, the node that has the highest expected degree, and then all we have to do is to show that the expected maximum degree is no more than square root of n log n than this expectation bound. So this is done using a simple application of Hofting bound. So our most interesting result from the technical point of view is obtained for a mechanism that we call approval voting with default. So the mechanism extends a mechanism by Holtzman and Moulin in the restricted case where each node can vote for just one other node. So the informal definition is that the highest degree node wins, is essentially what we would like to do if it is unique. So if we have a tie at the highest degree, then a pre-selected default node T wins. So essentially the motivation here is that if we have a node that has much higher degree than any other node, then this should be the winner, and nobody can do anything, can act strategically to change this decision. Otherwise, we have to do something to make sure that that impartiality is guaranteed. And this particular way I have defined the rule, we don't have impartiality. So there is this formal definition that gives us impartiality. So essentially, when we compare the degrees of two nodes U and V, we ignore the edges between them and any edge originating from the default node T. And if there is a node that, according to this definition, beats any other node in their pairwise comparison, then this node is the winner. Otherwise, the default node wins. So the main difference of the formal definition is in the definition of the degree of the node we consider in the comparison with any other node. So the degree can be different depending on which is the other node to which we compare. But we can show that this formal definition guarantees impartiality. And then this is the list of results that we have for AVD. So we have this polylogarithmic upper bound on the a priori popularity model. This is almost idle. We have a lower bound of log n on uniform instances. Unfortunately, the particular way that AVD is defined gives us a bound of square root of n log n in the opinion poll model. So the upper bound is obtained because AVD is always better than the constant mechanism. The lower bound is an interesting construction that exploits the structure. But we hope here that some more clever definition of AVD could give us a polylogarithmic result even for the most general of our models. So I have a few minutes before completing the talk. So let me say a few words about the analysis. So I'm not going to present any of the any piece of the of our actual proof, but I wanted to just to mention that the node degrees in the analysis of our second model is the main characteristics that the node degrees are binomial, random variables following the binomial probability distributions, and would like to consider quantities that are related with ties at the top. There is literature in the random graph, researchers studying random graphs. There is literature on the probability of having a tie at the highest degree, but here in our analysis we'll need a quantity that is considerably different. And unfortunately, these results have not been useful to us. And the most technically challenging part of the analysis is that we need, because we want to measure the probability of a tie, so we need to have estimates that the binomial random variable would take a value of y. And instead, what we can handle using Chernoff bounds or the nice formula of the binomial distribution is this probability that X is higher than Y. So essentially in our analysis, it's absolutely necessary either to prove the upper bound or to prove the lower bound. This bounds on this hazard rate, the probability of X being equal to this value Y over the probability that X is higher than the value Y. And this is a result that could be of independent interest, that this hazard rate is of order the square root of logarithm of n over essentially the expectation of the binomial random variable. So this is something we use in the analysis. So actually every term here is important to get the results we have. If we didn't have this minimum of the expectation, the n minus the expectation, the denominator, we couldn't prove anything. So the only bound we can show is the square root of n or something. And this logarithm at the denominator here contributes to one of the logarithm in the upper bound. Okay, and to summarize this third part, the open problems are to obtain polylogarithmic or constant expected additive approximation. This is still open in the most general of our models, to consider variations of AVD that could give us this result. And an interesting deviation from our model is, so here we assume that the prior information we have is accurate. So what if this information is not accurate? And what if we have just rough estimates of the highest expected degree, let's say? And we believe that we can recover the square root n log n bound. It's not clear whether we can recover the polylogarithmic result in the a priori popularity model using just rough estimates of the popularity of the nodes. And I'll stop here. Thank you very much.
Thank you very much, Yanis. And maybe we can have a first question, what Martin was trying to ask in the chat.
Yeah, so let me maybe repeat my question orally. So since you started your talk, I was thinking how I would act in this scenario if I want to be selected and what I would do. And my first idea was maybe not to select anyone, because it never can help me to select someone. And then I thought, okay, my next idea would just go to a friend and say, okay, you select me and I select you. And this will improve the chances of both of us. And I think this is quite realistic that people will act like this. And in your sampling algorithms, it seems like this would be a valid manipulation. So I was just wondering if you consider this type of manipulation, or if this is already too much group manipulation, too much group involved in the manipulation, and if it's still possible maybe to modify your mechanisms to also prevent people like this to manipulate.
We haven't considered this. Essentially, the question is whether coalitions of agents, strategic behavior by coalitions of agents could be handled by some clever mechanism. We haven't thought about this. Yeah, and then the results we have here are already, you know, they're important challenges in designing impartial mechanisms with good properties that, I have no idea what the answer will be in that case. But that's an interesting question, definitely.
Okay.
We have also a question from Nizar.
Hi, very amazing talk, Yanis. I have two questions, so I'll ask first question and then I'll raise my hand again and go back in the queue. So one question is for getting the lower bound higher than 3. I was wondering if you have tried doing basically. It seems like for small number of nodes, you can actually just write this as a set solving problem, and you can basically have like the answer for each possible graph as a variable, and then you can just encode like the constraints of impartiality, and then you can basically just check if you can get something, maybe not, if not set solving, definitely an ILP. And I was wondering if you had done that
Yeah, we have spent hours, days, weeks. I think Nikos has spent months on trying this. I mean, trying variations of this, and yeah, and pruning the space of solutions many different ways. We haven't managed to show anything beyond the case of instances with 4 nodes.
I see. And up to 4 nodes, you do know that I guess, yeah, up to 4 nodes, the lower bound is going to be 3. So
yeah. So
yeah, okay.
for 5 nodes, we don't have a proof.
All right, thanks.
Then we have Aris.
Yeah, thanks. And thanks, Nisarg, for the round robin sort of way of doing things. So my question, I think, is simple. It's since you have priors, would it make sense to consider Bayesian incentive compatibility? Then perhaps you can get better approximations, or is it not possible to do that?
Yeah, that's a great question. The answer is I don't know. So for several months while we were working on this problem, we used this Bayesian impartial selection as a working title of our paper. At some point, we realized that what we had was not Bayesian incentive compatibility, and it's not, and we didn't have any interesting idea of a mechanism that would guarantee Bayesian incentive compatibility, but not incentive compatibility. So it didn't help us. But But I think it will be nice to have a mechanism that guarantees this.
So we go back to the second question from Nizar. Sorry.
Hey, so yeah, my question was whether you have looked at approximate impartiality in the same sense as approximate strategy proofness, where you say that a mechanism is alpha impartial if by manipulating a node, I guess here it's a bit weird because you have only kind of winning or losing. I guess you would need to, or maybe in probabilities you can do this, where by manipulating you wouldn't win by probability alpha higher than the previous probability.
Yeah. So yeah, the space is even the space of mechanisms we need to consider is even is much larger now. So
yeah, so you can probably get better approximation.
Yeah. I mean, it could be it could be much closer to optimality with depending on how you define the approximate impartiality. But analysis seems to be analysis with this kind of problem is always challenging.
Thanks.
I would like to thanks again, Yanis, for the amazing talk. We kind of don't have any more time for questions. So again, happy to use the chat if there are more questions. But I would now pass the microphone to Haris, who's going to, thank you again. Haris is going to chair the third session. And to you, Haris.
Yeah, thanks a lot, Yanis, for such an interesting talk with such clean results. We're running really late, so what we'll do is we'll lose our first break and we'll immediately start with our first talk. So Ben Armstrong or Kate Larson are requested to share the screen.
I think
so Yanis, you could unshare your slides. We can.
Great. Right, you can see the slides now.
All good?
Great, thanks. Hello, I'm Ben Armstrong. I'll be talking about the limited applicability of liquid democracy. So I'll just start with a bit of an overview of what liquid democracy is in case there's anybody that doesn't know about it. Then introduce the basic model that I'm working with, talk about some of the analysis that I've done, and finish up with a discussion about some of the experiments that I've done. So liquid democracy is essentially a form of transitive proxy voting, where every voter chooses either to vote directly or to delegate their vote to another voter. And if you do vote directly, then you vote with the weight of all the delegations that you've received plus your own weight. So this first voter, for example, receives 2 delegations, one directly and one indirectly, and votes for A. So A receives 3 points, or however you want to think about it. B receives 4 weight because this voter receives 3 delegations. And what I find kind of interesting about liquid democracy is that even though only one of the 4 voters votes directly for B, B will still receive a plurality of the weight and therefore win. So it kind of, in that way, provides a middle ground between representative democracy and direct democracy. So in my model, I'm going with the very basic model of liquid democracy in voters choosing between 2 alternatives. And one of these 2 alternatives is the correct ground truth winner. And that correct winner is the same for all the voters. We use weighted plurality voting, and every voter can delegate to any other voter unless that would cause a cycle, or they can choose to vote directly. In that case, a direct voter is modeled as delegating to themselves. Each voter then has some probability greater than random of choosing the correct alternative. And in some cases, we look at a cost for the effort of voting directly. This is meant to essentially model the cost of looking up candidates, figuring out who you support, whatever, which is, some people say, easier than just choosing a trusted friend to do that for you. Then the weight of each voter is either 0 if they delegate, or the number of delegations they receive, including themselves, if they vote directly. And each voter gets some utility equal to the chance that the population will elect the correct alternative. And this is the same utility for every voter because they're all trying to accomplish the same goal. And if we have a cost for direct voting, then that gets subtracted from the utility of any direct voters. So the first question that we were interested in with the analysis is what happens when voters just greedily choose to maximize their utility in a repeated setting. So will this converge to equilibrium? And it's fairly straightforward to show that yes, both with effortless voting and where there's a cost for voting, then a Nash equilibrium exists and will be reached by greedy action. But open questions are still there, and we're not too sure how many actions it might take before reaching this equilibrium, or how much utility will be received by greedy action. But we've done some experiments. Because the utility function is relatively complex, we have to be limited to fairly small population sizes, but we can see that in a fairly low number of actions, the population will reach equilibrium. However, it doesn't really gain very much utility when it does this. So then we wanted to extend this to a more practical setting and try to evaluate what it might look like using liquid democracy on a real task. So we extended to ensemble learning or classification. And then in this setting, voters are implemented as classifiers. So rather than voting on a single pair of alternatives, voters make decisions on M pairs of alternatives, which is essentially binary classification on a data set of M examples. Voters or classifiers need to either classify all M examples or delegate to another voter on all M decisions. We still continue to use the weighted majority vote to decide the winning class for each example. And previously we talked about accuracy as the chance of correctly choosing the correct alternative. But now when we talk about accuracy, it's the fraction of examples in the data set that either a voter or a group have classified correctly. So, and here we still are interested in what's the chance that delegation will be beneficial. We can answer this for a slightly restricted question, which is how many states are there where a single delegation away from the state with no delegations will guarantee a strict reduction in accuracy. And we can show that any state like this has to have at least n pivotal examples. And assuming that we have exactly n pivotal examples, we get numbers like this when we do some calculations. We can see that basically the chance that delegation will be strictly harmful pretty quickly goes to zero as the size of the data set and the number of voters increases. So delegation, at least in theory, can be beneficial, or will usually be beneficial. Then we look at a number of different experiments to see how this fares more practically. First, we look at very small populations where we can look at all possible delegation strategies, or sorry, all possible delegations, and compare the best delegations to a few other mechanisms and the full ensemble. Then second, we look at larger populations just with more tractable delegation mechanisms. So these are the 5 delegation mechanisms that we look at. First, just no delegations at all, full ensemble. Then all possible delegations are looked at and we use the best ones. One mechanism where we try to maximize the diversity of an ensemble. One where the least accurate voters delegate to the most accurate voters, spreading their weights out as uniformly as possible, and a baseline random setting where delegations just happen randomly. And voters here are implemented as decision tree classifiers. An election is training all the classifiers, gathering their predictions, deciding delegations, combining their predictions. And we look at 50 different elections for all of our results and 6 different data sets. So in our first experiment, we can see that the best mechanism, as expected, outperforms the other mechanisms. There are a couple columns, I think Hart and KR versus KP, where the max, or no, Hart, whatever, and span base, where the max does slightly better. That's just due to random initialization issues. But the main thing here is that none of these columns are significantly different from each other. So even the best delegations are not much better than just delegating randomly. And when we look at a larger setting with 49 voters averaged over a few different numbers of gurus, we see the same thing. Max continues to be very slightly better than the other settings, but not significantly so. So both theoretically and experimentally here, we've seen that delegations can have a positive effect on group accuracy, but this effect is fairly small and it's easy to run into computational constraints when you're trying to maximize it. So if we wanted to stay in this setting, there are still some potentially interesting theoretical questions to look at in the future, like how quickly will we reach a Nash equilibrium? What will be the expected utility gain, stuff like that. But it's not really clear if this model will be useful. So the main conclusion here is that in the future, liquid democracy should be looking more towards practical application, and to do that, we might need more complex delegation structures or some sort of centralized decision-making. And there are a few papers beginning to do this, but it seems like a very important future direction. So I'll end there, and I see there are already a couple of comments in chat. Thank you. I don't know how to see the chat.
Shri has a question. Shri, do you want to unmute yourself and ask it?
Yeah, I can. And I was curious on two things. One, in the simulations, if you varied the distribution of the competence, so like different distribution, let's say 20% very high expertise, 20% low, 60% around the average, if the results of the simulation were different. And the question asked in the chat was whether perhaps the ensemble's base rate of the prediction was very high, so they could gain very little of delegation. So like it would be interesting in different settings where the improvement is kind of significant in terms of accuracy, for instance.
Yeah, so for the second question, that's something that we looked at. Like I think we used just a depth of 1 to 4. So I tried to make the classifiers fairly weak, but I think that is still a bit of an issue. But previously, I was doing experiments with, I think, a depth of 20 to 25 or something. And it seemed like reducing the depth somewhat mitigated that issue. And I still saw the same results of not really seeing benefit from liquid democracy. So my expectation is that with even weaker classifiers, that would continue to be the same. And I missed some words in the first question. Could you maybe repeat it?
Okay, maybe I'll phrase it differently. So I think the benefits of liquid democracy a lot of time depend on the distribution of the competence within the community. So, the QI we assume is bigger than half. Really, that distribution determines whether we should use or not use liquid democracy a lot of times. Let's say if you have a lot of people which are actually under than half or close to half, but few nodes which are enough nodes, proportionally, which are high competence, then you benefit a lot, for instance, from delegation. Just I was wondering with that.
That's definitely a good point. And I think that's where we run into benefiting from kind of more either complex delegation structures or centralized decision-making, because the biggest challenge there is figuring out who is more competent. It's really not clear if that's a realistic thing to assume agents would have knowledge of. So there are probably modeling issues there of deciding what's most realistic to do. But yeah, that is definitely an important thing to consider.
Okay, I'm afraid we don't have more time for questions, so let's thank Ben. And the next speaker is going to be one from Umang.
It's me. All right. Hi.
Yeah. Okay, it's Rohit. Welcome. So if you could share your screen.
Do you see my screen?
Yes, all good. So let's start.
Okay. All right. Okay. So thank you, Horace. So hi, everyone. Thanks for joining in. My name is Rohit, and I will be talking about recent joint work with Umang Bhaskar and AR Sricharan called On Approximate NV Freeness for Indivisible Chores and Mixed Resources. Before I get started, let me note that this talk was supposed to be given by my co-author Sricharan. Unfortunately, he became unwell at the last moment, so you're stuck with me for now. So if you like anything about the slides, it's all credit to Sricharan, and if you don't like something about the talk, then that's on me. Okay, good. So this talk is going to be about resource allocation, specifically fair resource allocation. And the setting is that we are given a bunch of indivisible or discrete resources that we want to allocate among a set of agents in a fair manner. Now, these agents have certain numerical utilities or valuations over these resources. And these items or resources that have positive value, we are going to call them goods. And items that give negative value or undesirable, we are going to call them chores. And there are good reasons for studying fair division of goods and chores. So for example, think about allocating seats and courses at universities, or allocating the items in an inherited property. These are all examples of assigning goods in a fair manner. Similarly, fair allocation of chores has also a lot of applications, for example, in distributing household tasks, or in assigning global climate change responsibilities, and many, many more. So there's a good motivation for these problems. Okay, so what is fair? I'm sure many of us are aware of this classical fairness notion called envy-freeness, which just says that if I'm one of the agents, I should be happy with what I got. I should not envy the share of anybody else. Okay, so if you look at this example, so for the next couple of slides, I'm going to look at examples that involve only goods, meaning agents have positive values. If you look at the one on the left top, agent A is getting a car, which he values at 10. And so he would not envy agent C, for example, who gets the candy, and agent A has a value of 1 for that candy. Okay? And similarly, assuming that agents have additive values, you can verify that none of the agents envies the other in this. So this is an envy-free assignment of the objects. Okay, so wouldn't it be nice if an envy-free allocation always existed? Unfortunately, it doesn't. Think of a simple setting where you have 2 agents fighting over a single item. Whoever loses out on the item is going to envy the other agent. So envy-freeness is impossible to achieve here. However, note that if we remove the item from the envied bundle, we are able to eliminate the envy. So although there is some envy in the system, it's bounded in some well-defined sense. And this really motivates notions of approximate fairness, something that you have already heard in a couple of talks in this workshop, called envy-freeness up to one good, which just says that, fine, there might be some envy in the system, but if we remove one of the items in the envied bundle, the envy should go away. Okay. Now, a natural question to ask at this point would be, well, does an EF1 or envy-free up to one good allocation always exist? Turns out there is a very strong yes answer to this question. Such an allocation not only always exists, but there is a very nice polynomial time algorithm for finding such an allocation. So I'm going to describe this algorithm to you in the next slide because it's going to be important later on. And the algorithm is fairly simple. It's going to work in rounds. At every round, it assigns an object. And the key thing, the key invariant that the algorithm maintains is that at every step of the way, the partial allocation remains EF1. So we are always going to maintain this EF1 property. Okay, so let's look at an example. Suppose we are given an instance like the one on the left top. Okay, it would be useful to keep track of the envy in the system. So let's draw something called an envy graph. It's just a graph where the vertices are the agents, and we are going to draw directed edges to denote the direction of envy. So suppose in the first step we assign the candy to agent A. Now agents B and C are envying agent A, so we draw directed edges in that direction. And the algorithm just keeps assigning objects in every round. One thing to be mindful of is that we want to preserve EF1. So the next object that we assign should be given to some agent who is not already envied. In other words, in terms of the envy graph, it's an agent that is a source in that graph. Okay, so say we assign the next object to agent C, the envy graph changes. Again, we assign something to B, and at some point we are going to get stuck. And the reason we get stuck is because there are no sources in the graph, meaning there's a cycle, there's an envy cycle in this graph. Now, a natural thing to do at this point would be to do a cyclic exchange. And interestingly, it turns out that doing such exchanges or resolving the envy cycle also preserves EF1. It's not too hard to see. The brief sort of intuition is that suppose I'm one of the agents who is not part of the cycle, then I only see the bundles changing hands, but the bundles are not broken in any manner. So EF1 from my perspective is maintained. And if I'm one of the agents who is participating in the cycle, then my utility is only getting better, and the other bundles are again changing hands. So in that sense, if the allocation was EF1 before, it continues to be EF1 now. It preserves EF1. Okay, and so we proceed in this manner. The final allocation magically turns out to be EF1. Okay, so just to recap, the algorithm is very simple. As long as there is an unallocated good, we look for any NV cycles. If there are none, just give it to the source. It preserves EF1. If there is an NV cycle, we resolve any cycle of our choice that preserves EF1 as well. Okay, great. So what we're interested in this work is chores or negative valued items or undesirable resources. And again, you can imagine that exact NV freeness is not possible in this setting. And so one must look for approximate notions of fairness. And once again, you can think of the analog of EF1, which we're going to call NV freeness up to one chore. Note that because the items are negatively valued, this time in order to eliminate NV, you should be removing something from your own bundle. Okay, so just want to take a moment to sort of pause and ponder about this asymmetry between goods and chores. So these two settings are not just different in terms of a sign change. It's not just like chores are just a sign change of goods. It's also that the notion of approximate fairness is conceptually different. In case of goods, we are removing something from the NV'd bundle, but in case of chores, we are removing something from the NVS agents bundle. And this distinction is actually going to be crucial algorithmically, as is going to be obvious in the next few slides. Okay, so suppose we want to design algorithms for finding an EF1 allocation for chores. How do we do that? Well, a natural starting point would be to go back to the goods problem and just do the opposite. Okay, so in the goods case, we were allocating items to sources in the NV graph. Now here, one might think that we should assign items to the sinks. Okay, so let's do that. So suppose we assign something to agent A, like job of collecting papers goes to agent A. Now agent A is envious because it's gotten an item of negative value. So we assign the next item to a sink in this graph, say agent C. Next we assign to agent B. Say next we assign to agent C. Okay. Now at some point we might again witness a cycle, right? And a temptation would be that, okay, let's just like in goods, let's just resolve these cycles. Okay. But this time it turns out that resolving a cycle could actually end up destroying the EF1 property. Why is that? Well, look at the pair of agents A and C, right? If I resolve the cycle, agent A ends up getting agent C's bundle, which is that of cleaning the house and taking out the trash. Okay, and look at agent A's values for these items. So agent A's value for its current bundle is -5. But if I do the cycle resolution, its value would be -4. Okay, so certainly agent A is getting better, right? But note that while the previous allocation before resolving the cycle was EF1 up to the removal of these correcting papers, sure, it's no longer EF1 now, because even if agent A removes one of its current items, it still continues to NV agent B. And the reason this is happening is because in the newly acquired bundle, there may not be any chore that is large enough to compensate for the NV on its own. It could be that in the newly acquired bundle, there are really, really tiny chores, and removing any of those chores really does not make much of a difference. Okay. Okay, so here's the algorithm that we were thinking about so far, and the problem occurs in this step of cycle resolution, which does not seem to preserve EF1. Okay, so what do we do? It turns out that the solution is subtle but simple. We just have to think about, instead of resolving arbitrary NV cycles, we just have to remove certain specific kinds of NV cycles. Specifically, we're going to think about top trading NV cycles, which is an NV cycle in which every agent is pointing to its most NV'd bundle. Okay, so suppose every agent is pointing to its most NV'd bundle. If there's a cycle, we call it the top trading cycle. Okay, and the important observation is that either the NV graph has a sink, in which case we can keep assigning chores and preserve EF1, or if there is no sink, then there always exists such a top trading cycle. And the intuition is very simple. If there is no sink, then any vertex must have an outgoing edge, which means there must also be a favorite outgoing edge. And you just follow the nose in terms of these outgoing edges. Because there's only finitely many agents, there's got to be a top trading cycle. Okay, so resolving a top trading cycle preserves EF1 because every agent in a top trading cycle is getting its favorite bundle. So the problem that occurred before, where we got a bundle with very, very tiny chores, that does not happen anymore because every agent is NV free who's participating in the cycle. Okay, So what we can show more formally is that using this top trading idea, we can find an EF1 allocation of chores in polynomial time. Okay, and so here's the algorithm. The change is right here in this step. So instead of resolving arbitrary cycles, we just resolve top trading cycles. If you just want to remember one thing from this talk, it's that for chores, we have to be careful in which cycles we resolve. All right. So far I've been giving examples about additive valuations. Let me note that this top trading algorithm works just as fine for monotone valuations. Okay. It's also not very difficult to extend this idea to work with instances where you have both goods and chores, such that every agent can partition the items into goods and chores, such that its valuations are individually monotone for goods and for chores. These are formally known as doubly monotone instances, and a modification of our algorithm can find an EF1 allocation for this setting as well. All right. Okay. So I want to, in the remaining time, I just want to talk about a further application of this top trading idea, which is in a setting where we have both divisible and indivisible resources. Okay. Now, when we're thinking of both divisible and indivisible, we have to think about what kind of fairness concepts apply in this setting, because exact NV-freeness makes a lot of sense in divisible setting, but maybe not so much in the indivisible setting. But now we have a combination of the two. So it turns out that probably a good notion in this setting is NV-freeness for mixed resources, or EFM. And it just says that suppose any agent has any amount of divisible desirable resource, also known as a cake in the cake cutting literature, then that agent should not be envied by anybody else. If any agent has divisible undesirable resource, also known as a bad cake or a burnt cake, then that agent should not envy anybody else. And subject to these two conditions, we obey the EF1 property. Okay, so any allocation with this property is what we're going to call EFM. Okay, so right off the bat, we have these four settings, because the indivisible resource could either be goods or be chores. Similarly, the divisible parts could be either a cake or bad cake. So we have these four problems that we're working with. And thankfully, one of these cases was resolved in this work by Bay et al. They showed that an EFM allocation always exists when you have indivisible goods and divisible cake. Okay. What we are showing in this work is that by building on this doubly monotone valuations algorithm, we can actually show the existence of EFM in this row below. So when we have both goods and chores, and when the divisible resource is only the undesirable one, when it's only the bad cake. We also have some special case results for the setting where the indivisible items are chores and the divisible resource is the cake. But the general question we were unable to solve, and I think it's a nice problem to think about. Okay, so just to wrap up, I just want to remind you about the EF1 algorithm for computing EF1 allocations using this top trading idea. It applies to doubly monotone valuations. And what I did not talk about, but you can check out the paper for that, is that you can also compute EFM allocations in this divisible plus indivisible mixed kind of a setting. A couple of juicy open questions, I believe. So obviously, the EF1 result that I showed you, we only have it for doubly monotone valuations. But what if you don't have double monotonicity? What if you have arbitrary valuations? Can we get EF1 allocations? I think that's an interesting question. Also, can we resolve the EFM question for divisible goods? The divisible cake and indivisible chores. And finally, I think it's an interesting question to think about combining EF1 with certain other well-motivated economic notions, such as Pareto optimality. So a concrete question there is, well, can we get an EF1 and Pareto optimal allocation if we say only have chores? Okay, so that's all I have to say. Thank you for listening, and I'm happy to take questions.
Thanks. We have time for maybe one question. Okay, if not, I was curious, what's your intuition for number 2, EF1 for completely arbitrary valuations?
So sorry, the motivation for it?
No, intuition.
Oh, the intuition for it.
Whether it holds or not.
So that's it. I mean, so I can tell you that like the stronger version, like if you are going for EFX, the stronger fairness notion for completely arbitrary evaluations, there the answer is no. So there is definitely an existing line in sand, right? We cannot go all the way. EF1 is sort of a nice sweet spot between double monotonicity and arbitrary evaluations. In general, it seems difficult to find counterexamples for EF1. In many settings of interest, it tends to always exist. So if I have to make a guess, I would say it probably does, but many of the algorithmic techniques that we have at hand, they don't seem to generalize to the arbitrary setting. So they crucially use this monotonicity, which we don't have in the arbitrary setting. So I think some new algorithmic ideas would be needed in this setting. Yeah.
Thank you for a very interesting talk.
Thank you.
So the third in line is another fair division presentation. So Rupert, Avi, or Nasag, I think we have all three of them in the room. Hi.
Can you see my screen?
Not yet. It says that you started screen sharing, but I can't see it.
Give me a second, I think that it's frozen.
Well, while Avi is trying to set up a slide, if you have any other questions for Rohit, feel free to ask.
Maybe you can try stop sharing and then start sharing again.
For some reason, my PC is completely frozen. What happens?
Actually, the sound is pretty unclear as well. I wonder if it's a connection issue.
Yeah, it's probably a connection issue.
Nasag, if you wish, we can reorder the talks and have it a bit later.
Yeah, I think that would be nice if the people who are supposed to go after are ready and can go now.
I think I'm supposed to be next, and I'm happy to do it now.
All right. Okay, let's do that.
Let me just check if I am supposed to be next. Yeah, I think that's right.
I can't see Avi. Okay, well, when she comes back, she'll find out. She's been replaced. All right. Okay. Welcome.
Hello. Thank you. Let me share my screen quickly. Can you see my presentation?
It works. Yes. Yes.
Okay. Hello, everyone. So today I'd like to present the work we've done with Omer, Lev, Nick Matei, and Paolo Turini on the PS selection problem. It's quite similar to what Ioannis talked about before, just a bit of a different setting. So we originally developed the algorithm called peer nomination, which improved performance on some state-of-the-art algorithms in the field in most settings. And now we are focusing on how to make it work in the noisy settings, basically. So quickly about the problem. So most of you will probably have encountered PS selection many times in your lives. Say you submit a paper to a conference, then you get to review some papers yourself, and your paper will get reviewed by some other people. And in the end, obviously we want to select some subset of papers to be accepted. So everyone wants to be accepted, but still we are assessing each other. So we have a set of competitive agents that assess each other with no external assessors. More formally, we have n agents that each review m other agents and are reviewed by m agents, so we have a balanced assignment. And in the end, we want to select k of them. So these assignments are drawn at random, and once you get your assignment of papers to review, we ask you to output a ranking. In fact, for our algorithm, we won't even need a full ranking. It's more of a approval-based thing, but in literature, we often use rankings as our reviews. So we'd assume there is a ground truth, which is simply a linear order of all agents, which is meant to represent somehow the objective quality of the candidates or the papers, for example. But the agents don't have direct access to the ground truth. They only have noisy observations that we model in some way, more on that later. But as I said, we have a set of competitive agents, so they can strategize to be among the top K, to be selected. They can mark down their competitors and manipulate their reviews in all kinds of ways. So basically, what we want to do is to prevent that and develop so-called strategy-proof or impartial algorithm. But we still want to select the best K agents, or at least close to that. So a quick graphical overview. So we start with an assignment, then each agent gives their reviews, which are simply rankings in the general case. And then we aggregate these reviews to either construct a ranking or select a winning set. So in our work, we concentrate on selecting a set. So a quick overview of our algorithm PR nomination. It's quite simple, really. We expect to select k out of n agents. So out of each individual review pool of size m, we expect to select k over n times m agents. So we basically set this as a nomination quota, and we let each reviewer nominate this many agents out of m they're reviewing. So because this is unlikely to be an integer, we have to do a bit of modification. So we round it down and nominate this many agents certainly, and then we nominate one extra agent probabilistically, where the probability is equal to the fractional part of the nomination quota. This is just to make the accepting size to be close to k. And then we simply go through all the agents and their reviews, and if they're nominated by the weak majority of their reviewers, we select them, we add them to the winning set. So because each agent is considered independently, there is kind of not direct competition between them. So your review doesn't affect your chance of being selected. Hence, PR nomination is strategy proof. But the downside is that it's not exact. So we cannot guarantee to output exactly k agents every time. Under reasonable conditions, we can show that in expectation we output k agents, but we will see that under high levels of noise, for example, this tends to break down. But under these reasonable conditions, empirically, it beats state-of-the-art algorithms in most settings in peer selection. But now we look more closely into the noise, and how we model noise in our empirical tests is using the Mallow's noise model. And what it does is, for each agent, it shuffles the ground truth around according to some dispersion parameter phi, which varies between 0 and 1. And in the literature before and for our last paper, we used phi of 0.5, which you would think would be an average level of noise, but in fact, it doesn't permute the ground truth all that much, and reviewers don't tend to make that many mistakes. So now we looked at what happens when we push phi to 1 and even beyond. So for example, at phi 0.9, we see that the individual ranking that an agent can receive is much more noisy, hence they will most likely make many more errors. But under these high levels of noise, we saw that peer nomination actually suffers a lot, and especially because it tends to output many fewer agents than we want. So what we did to rectify this is to introduce trust weights to the reviewers. Basically, we look at the reviewers and we look at how much they disagree with other reviewers for the same papers. And if they disagree a lot, we can weight them down, and accordingly, their nominations will not be as valuable, for example, as those of good reviewers. So we don't have that much data to base these weighting schemes on, but we have a few approaches. So firstly, we can literally look at every single disagreement an agent has, a reviewer has with other reviewers. So if you nominate someone, someone doesn't for the same paper, we count this as a small disagreement and add it to your total. We can be a bit more forgiving and only count an error in your review only if you're in minority opinion for a paper. So say the consensus that the paper should be selected, but you don't nominate it, we count this as an error on your part. And we can even discretize this even further by setting the weight to say 0.5 if you committed some critical number of errors, or even to 0 if you committed too many errors. So a quick illustration to make things clear. Say we have some reviewer I that reviews 6 agents, J1 to J6. We can see that J1 to J3, they receive more nominations than non-nominations, so they should be selected under our algorithm. However, our reviewer I doesn't nominate J2 and J3. So we mark this as an error on their part because they're not in majority in the consensus here, right? And similarly for J6, they nominate them, but the consensus is that they shouldn't be selected. So that's an error too. And correspondingly, the average disagreement with other reviewers is quite high. So basically, we see that this reviewer cannot be trusted very much, so we can reduce their weight, say from 1 to 0.5. So what this means is that the nominations will now count only half as much as those of good reviewers with weight of 1. So I won't go into detail into how exactly we convert this data into the weights, but even with simple weighting schemes, we have shown that we can improve our performance quite a lot. So here we see we have a population of agents. Some of them are accurate and some are simply random. And the x-axis shows the proportion of accurate reviewers. So we see that as this drops, our original algorithm, which is the red bar here, really drops in performance and in the accepting size. But when we introduce our weighting schemes, especially the distance weighting scheme, it manages to rectify the output size quite a lot. It keeps it very close to the target of 40. And similarly, because of that, it corrects the accuracy or the recall accurately of the algorithm quite a lot. Even in the setting with adversarial reviewers, where we assume reviewers to go against the ground truth, we still see that, especially the distance weighting scheme does quite well to rectify the initial shortcoming of peer nomination. So I want to close with a few remarks. We have a lot of work to do next. We can try using weights with other peer selection algorithms. So there are obvious ways that it can be adapted to those algorithms. We need to try out other noise models to make sure we're not simply overfitting everything to the malus noise. There are a lot of parameters to tune in the weighting schemes and in the algorithm itself. So there is a bit of a optimization problem in there. And a big question as well is how do we force truthfulness rather than simply strategy proofness in the reviews? Because notion of strategy proofness as is usually used in peer selection is actually quite weak. It only discourages people to manipulate if they don't benefit themselves, but it doesn't encourage them directly to report an honest review. Thank you for listening, and I'm happy to take any questions if you have any time.
Right, so this quite a lot of discussion in the chat regarding the reweighting or the downweighting. Somebody wants to, Vance, Amy, do you want to speak up?
Okay, let me stop sharing because otherwise I can't access the chat.
Okay, so one concern that was raised was that whether it affects strategy proofness. Obviously, you have an argument for that, but in general, I have a concern that it sort of maybe strategy proofness is not, or impartiality is not compromised, but it incentivizes conservative reviewers who don't differ in their opinion. I think that's the point which Vince also raised. So it's a different kind of incentive issue, but it's still a
so is the
valid
concern that the weighting schemes will break strategy proofness?
No, not strategy proofness, but it still incentivizes people to sort of conform, not give differing opinions.
Yeah, so
so that they don't get downweighted. Yeah?
Like I'm not gonna lie, like with this algorithm and with most of the previous algorithms in peer selection, the agents are not really incentivized to give their honest opinion. They could give a random opinion, and as long as it doesn't benefit them directly, it will count as strategy proof, basically. This is why I raised this point towards the end, that it would be interesting to look at what we can do to actually incentivize truthfulness directly.
Right. Okay, I believe that answers Amy's question. Amy, are you fine with that?
Well, I just wanted to make the point. I mean, the question was about strategy proofness and breaking that because of the example that Vince cited, or that he invented there, where you would, I don't know, you're interested in getting your opinion really valued on one particular paper, so therefore you conform on all the others deliberately.
Okay, so yeah. If you're talking about the weighting schemes, they can actually break strategy proofness. So we actually need a small adaptation in how we generate the assignment. So we need to basically avoid a certain scenario where you are reviewing a paper that your reviewer is reviewing. So basically, you don't want to be able to weigh down someone who's reviewing you. And if you have some papers that you review in common, you could do that, but we can generate an assignment that avoids this scenario. So, because of that, we do keep strategy proofness with the weights.
Okay, Evie has managed to share her screen, so thanks for your talk.
Okay, thank you.
Okay, so the next presentation we get back into order by having this presentation. So it's Evie is going to speak on two-sided matching.
All right, thank you very much. I'm sorry for the inconvenience before. So this talk is about how notions that derive from fair division can be very naturally applied in a many-to-many matching setting. This is a joint work with Rupert Freeman and my advisor Nisar Khan. And let me first introduce what is a many-to-many matching problem. So here it is assumed that we have a disjoint set of agents, which from now on I will refer as the agents on the left and the agents on the right. And each agent on the left has preferences over the agents on the right, and respectively, each agent on the right has preferences over the agents on the left. And these preferences can be either cardinal utilities or ordinal preferences. And each agent can be matched up to a specific number of agents from the other side. So there are some degree constraints. And the task here is to find a matching among the different sets that satisfy some nice properties. So this problem is quite general and captures many real-life applications. And let's see, for example, the following. Here we can assume that we have a set of students and a set of courses. Each student can take up to a specific number of courses, and each course has a capacity which indicates how many students can concurrently attend this course. So students in general have preferences over the courses, but now we can also imagine that behind each course there is a teacher which is in charge of this course. And it is very natural to assume that also the teachers have preferences over the students. For example, teachers prefer students with the highest CPAs to take their courses. And so another way to see this problem is as a many-to-many matching problem between the students and the teachers. And as I said, there are some degree constraints, which is then the number of courses that student can take and the capacity of each course. And so we want to find the matching. For example, in this particular case, we assume that each teacher can have up to each course can host up to 2 students, and each student can take up to 2 courses. And in general, in the literature, desirable solutions consider the one that satisfy some notion of stability, where stability means that if we have an agent I on the left and an agent J on the right, which are unmatched, they don't prefer each other rather than some of their current matches. And very similar is the notion of justified envy, which means that if an agent I envies an agent I prime for its connection for agent J, for example, from the right side, then this envy is justified if also J prefers I. And so desirable solutions here are the ones that satisfy either stability or there are no justified envies for the current matching. And so let's go back to the previous example and let's consider the specific instance in which all the students prefer the first 2 teachers, and particularly they have utility equal to 10 for teachers 1 and 2, and they have utility equal to 0 for the 2 remaining teachers. And also the teachers prefer, all the teachers prefer students A and B, and they have utility equal to 10 for each of them, while they have utility equal to 0 for students C and D. So in this particular example, the only stable matching or the only matching that does not have any justified envy is the one that students A and B are matched with teachers 1 and 2, while students C and D are matched with teachers 3 and 4. And to convince you about this, let's, for the sake of contradiction, assume that teacher 1 is not connected with student B. Then we can see that because B prefers teacher 1 to teacher 3, and also teacher 3 prefers student B to student C, they can deviate and they can form their own coalition. And another way to see that, and regarding justified envy, we can see that B envies C for its connection with teacher 1, and this envy is justified because also teacher 1 prefers student B to student C. So in a high-level idea, we can see that here, the entitlement of each student, for example, to take its favorite course depends on what the teachers believe for the student. So it depends to the preferences that teachers have for the students, and respectively, the entitlement of each teacher to has the best students in its course depends on what the students believe for this teacher. However, if we focus only to the students, for example, we can see that all of them pay the same fees. So somehow all of them, they should be treated equally, independently of what the teachers believe. They should have the same right to the same opportunity to attend their favorite course. Respectively, all the students should have the same opportunity, the best students, to be in their course. So there are applications in which we need to satisfy a notion of fairness on both sides, independently of what agents of the other side believe for these agents. And this is exactly the point that we use notions of fairness that derive from the resource allocation problem. So in the resource allocation problem, it is assumed that there is a set of agents and there is a set of indivisible items. And the agents have preferences over these indivisible items. And so here we want to find the partition of these items among the different agents in a fair way. And a very common assumption is that these evaluations are additive, which means that the utility for an agent I for a set of items X is equal to the sum of the utilities that this agent has for each of the items that belongs in this set. And the very famous notion of fairness in this context is envy-freeness, which means that no agent I prefers the bundle of an agent I prime. And because envy-freeness it's not always possible to be satisfied. A relaxation of this is envy-freeness up to one good, which means that if an agent I envies an agent I prime, then this envy can be eliminated by removing just one item from the bundle of agent I prime. Which means that if I ignore just one item from the items that have been assigned to agent I prime, then this agent does not envy agent I prime. And so now we can go back to the many-to-many matching problem, and we can see this as a two-sided resource allocation problem, which means that in one side, we have a set of agents, the agents on the left, and all of them have this degree constraint equal to DL. So here we assume that all the agents on the left have the same degree constraint. And on the other hand, now we don't have items, but again, we have agents. And again, these agents, all these agents have the same degree constraint, which is equal to DR. And now each agent on the left has preferences over the agents on the right, and also the agents on the right have preferences over the agents on the left. So another way to see that is that not only the agents have preferences over the items, but also the items have preferences over the agents. And here we're looking for a matching, which matches a set each agent I on the left with a set of agents MI on the right, and also each agent on the right is matched with a set of agents on the left. And again, we make the assumption that the evaluations are additive, which means that if an agent I is matched with a set of agents MI, its utility for this set is equal to the sum of the utility that each agent has for each agent J that belongs in this set. And so now we define that the matching is envy-free up to one match over the agents on the left, when if an agent I envies an agent I prime, then this envy can be eliminated by removing one match from agent I prime. And similarly now, we can define that the matching is envy-free over the agents on the right, if every envy can be eliminated by removing just one match from the envied agent. And now in this work, we ask for doubly envy-free matchings up to one match, which means that a matching is doubly envy-free if it is concurrently envy-free over the agents envy-free up to one match over the agents on the left, and envy-free up to one match over the agents on the right. So let's go back to the previous example. We have exactly the same utilities again, and as I said before, stable matching is the one that matches A and B with teachers 1 and 2, and students C and D with teachers 3 and 4. But now we can see that, for example, if we focus to the students, that this matching is because, for example, C envies A, because the utilities, because C has value equal to 20 for the matches of agent A, while it has only 0 for its own her own matches. And also we can see that this envy cannot be eliminated by removing just one match from agent A. For example, if we remove its her match with teacher 1, then still C has utility 10 for the matches of agent I and 0 for its own matches. And similarly, if we remove her match with teacher 2, again agent C envies student A. So in this particular case, we can see that a matching that satisfies double envy-freeness is the one that all the students are matched with teachers 1 and 2, which are their favorite teachers for all the students, and also all the teachers are matched with students A and B, which are their top preferences. So in general, in this work, we saw that double envy-free up to one matching always exists when agents on each side have identical preferences, which means that all the agents on the right have exactly the same preferences for the agents on the left, and all the agents on the left have exactly the same preferences for the agents on the right. And particularly, these results holds for even stronger notion of Dublin freeness for stochastic dominance and freeness, Dublin freeness, which means that we don't need to have access to the exact cardinal utilities, but only if we have access to the rankings that derive from cardinal utilities, then we can achieve this result. And then we saw that when just in one side the preferences are different, then Dublin free matching does not always exist. And again, this falls for the stronger notion of Dublin freeness. And moreover, we look for a different notion of fairness that derives again from the fair division literature, which is MMS. I don't want to go into detail what exactly this notion is, but the high-level idea is that captures the idea of proportionality in the setting of indivisible goods. And we saw that in this case, even if the agents on both sides have identical preferences, then it's not possible to have a double MMS matching. Double again means that we satisfy the MMS properties of property over the agents on the left and concurrently over the agents on the right. And we saw that even if we want to approximate this, this is not possible. So this 0.89 shows a multiplicative approximation. And moreover, we saw that in general, if we want to achieve DMMS and the DF1, it's not possible. These two notions are incompatible in this setting. And just to mention that there are many interesting questions in this work, and probably the most interesting one is how we define. So as I said before, in this case we assume that the degree constraint is equal among the agents of the same side. So when two agents belong to the same side, then they have the same degree constraint. However, it would be interesting how we define this notion of fairness when each agent can have a different number of matches. For example, what does it mean if an agent can be matched with 100 agents from the other side, while another agent can be matched only with 2 agents from the other side? How exactly we can define a freeness in this case? And let me stop here. Thank you very much.
Thank you. We have time for maybe 1 or 2 quick questions.
Okay, I can see some questions on the chat.
Well, I had a follow-up comment on this last remark you made about agents with different capacities. So Arel Segal-Halevi, I don't know if he's still in the room. He had a recent paper where he's looking at fair allocation with various feasibility constraints. I think that kind of framework or that definition applies for your concern.
Yeah, probably if we assume that, I think that there is a literature regarding that different agents have different weights, which means different entitlement for taking different items. Yes, I think this is very interesting that if we assume that the entitlement is defined as the degree capacity, then for sure we can define a freeness using this notion. And yes, I think this is a great point.
Yeah, so that paper doesn't talk about entitlements, but it talks about agents having different feasibility constraints, for example, capacities.
Yeah, I agree.
All right, thank you for your, okay, thank you. So we're now back on track. So we have another presentation, which is on peer review. So if the next speaker among, hi.
Let me know if the audio or video isn't working in any way. I'll go ahead and get started.
Everything is working. So
okay, great.
Let's start.
Okay. So hello, everyone. I'm Stephen Jackman, and I'm here to present some work on mitigating manipulation in peer review, which was done with colleagues at Carnegie Mellon and Duke. So the setting that we're dealing with is one that probably everyone here is familiar with. Where in conference peer review, we want to assign papers to reviewers, and we want to do so in such a way that all of the reviewers have enough expertise and interest in the papers that they're reviewing. So to get a good assignment, we want to somehow solicit information from each reviewer about which papers they would be good with reviewing. So we might do this by asking reviewers to bid on papers and provide a list of the papers that they want to review and don't want to review. Or we might look at their past work, ask them for their subject area, etc. And so the standard framework that encompasses all of these methods is to first construct a similarity matrix where each entry of the similarity matrix corresponds to a score indicating how good of a match that reviewer is for that paper, which can incorporate all sorts of information. And then you solve this optimization problem where you find an assignment that maximizes the total similarity, subject to constraints that no reviewer has too many papers and every paper has the right number of reviewers. And you can solve this as a linear program, so you can do this efficiently. And this sort of framework is used by a variety of conferences and conference management systems. And note that this assignment is deterministic. So barring any tie-breaking issues, if you input the same similarities, you'll get the same assignment. So there are some issues that can arise in the standard setting. And one of them might occur if you have some malicious reviewer who is working together with the author of one of the papers submitted. So this reviewer might say, I'll make a deal with you. And as part of this deal, I will change my bids and perhaps change other aspects of my reviewer profile with the purpose of getting assigned your paper. And then once I'm assigned to it, I can give it a good review and maybe you can do something for me in a different conference. So this sort of issue is taken seriously. Notably, last year, there was an ACM IEEE investigation that uncovered some collusion of this sort in an architecture conference. And more than just these sorts of collusion rings, you can just do this with your friends or colleagues, where people could bid for each other's papers and then give them positive reviews to help each other out. And this problem does extend beyond just bidding, because reviewers could manipulate other aspects of their profile as well. So this is issue number one, which we'll call untruthful favorable reviews. And another very similar issue that can arise, rather than having a malicious reviewer working with some author, there might be some paper in the submission pool that some reviewer just doesn't like for an unfair reason. And so they say, I'll specifically try to get assigned to this paper that I hate and give it a negative review to block it from publication. So like the first issue, this has been taken seriously. And important problem with this is that just a few people can repeatedly do this and indefinitely prevent publication of some paper that they don't like. And maybe this paper isn't liked because it threatens the reviewer's research, contradicts their beliefs, or something like that. So this issue we call torpedo reviewing. And before we get on to the solution, there's one more issue that I'll discuss with the standard peer review setting. And this issue here, we are depicting after the reviews have been done and some papers have been accepted and rejected. And one author is upset that their paper was rejected. And so they say, I'll just rerun the assignment algorithm and figure out which reviewers rejected my paper so that I can maybe retaliate in some way. Now, currently, this isn't possible because conferences generally keep the similarities secret. But conferences might want to release these details either for transparency or for research purposes, but doing so would break reviewer anonymity. And so this third issue is reviewer de-anonymization. So we talked about three issues here: untruthful favorable reviews, torpedo reviewing, and reviewer de-anonymization. And how are they connected? Well, we propose to address them all through randomized assignments. So what is a randomized assignment? Well, we choose some value of this matrix Q, and we want to find an assignment of papers to reviewers such that the probability any reviewer is assigned to any paper is capped at QRP. So what is Q here? Well, this is just a parameter that the program chairs can specify. So one simple thing to do would be to set all entries of Q to be the same constant value. Or if they have more specific information about certain reviewers and papers, they could set it differently. And as we'll discuss in a second, this addresses all three issues. And notably, it does so without requiring any additional assumptions about the specific things that reviewers are trying to do. So in the first case of untruthful favorable reviews, well, reviewers and authors might be trying to make deals like this, but these deals can't really be upheld with any with high probability. And similarly, in the torpedo reviewing case, the plan to torpedo review only works with some probability, and this notably will prevent the issue of indefinitely blocking a paper from publication. And of course, in the reviewer de-anonymization case, now the conference can feel free to release the similarities because even if an author reruns the assignment algorithm, any reviewer will have plausible deniability about reviewing the paper because there was some limited probability that they actually reviewed it. So let's say that we do want to find a randomized assignment. How do we actually go about doing this? Well, there are two steps to the algorithm we propose. The first step is to find the optimal marginal assignment probabilities. So you can do this in an optimization problem like the following, which is essentially a modification of the standard linear program that you use to find a deterministic assignment. But rather than looking for fixed assignments of reviewers to papers, we're now optimizing the probability that reviewers are assigned to papers. So our objective here is the expected total similarity of the assignment. And then we again have constraints on the reviewer loads and paper loads, and additionally constrain the probabilities by QRP, which is exactly what we want. So we can solve this linear program here and find the optimal marginal assignment probabilities. But then we need to actually find the assignment that we're going to use for the conference. So step 2 is to sample an assignment at random that satisfies these marginal probabilities. So our sampling algorithm is based on an algorithm from past work. And essentially what we do is we sample from the Birkhoff-von Neumann decomposition of this probability matrix. So to go into a bit more detail, I'll run through this simple example. And to keep things very simple, we're going to set QRP for every reviewer and paper to 0.5. So we want each pair of reviewer and paper to only be assigned with probability 0.5. And then we'll have an equal number of reviewers and papers. And let's say that we want each reviewer to review one paper and each paper to be reviewed by one reviewer. So step 1 is to find the optimal marginal assignment probabilities, which we'll call FRP here. And if we just instantiate the previous LP with the values of this example, this is what we get. So you can solve this efficiently. And I'll make the claim here that at optimum, FRP will either be 0 or 0.5 for every entry. The proof is here, the details aren't super important because this claim is not essential to the algorithm, but this just helps to simplify the explanation for this example here. So we solve this LP, we get the optimal probability for each assignment, and we now have to actually sample the assignment. So the sampling algorithm starts by constructing a bipartite graph of reviewers and papers. And since each probability is either 0.5 or 0, we can say that an edge exists if the probability is 0.5. So on the right-hand side here, we have an example of such a graph. And you'll note that because in this case, all reviewers and papers have a total load of 1, all of these vertices will have degree 2, which means that the edges can be, the edge set is the union of a number of disjoint cycles. So here we can color each cycle a different color. And we'll start by choosing some arbitrary cycle. So let's say we choose the red one on top, and we partition adjacent edges into 2 different sets. So we partition this red cycle into the dotted and dashed sets. And then we simply flip a coin to choose which of these sets of edges is in the final assignment. So we flip a coin and choose the dashed edges here, and then we do the same for all other cycles in the edge set. And the final assignment we have here, as desired, we have 1 reviewer per paper and 1 paper per reviewer. And each of these pairs was chosen with probability 0.5. So some experimental results. The first thing you might ask is, as you restrict the probability of these assignments, how does the quality of the assignment drop? So here on the x-axis, we vary the value of QRP for all reviewers and papers, and we observe how the assignment quality changes as a percentage of the standard deterministic assignment. And this is done on 4 similarity matrices from real conferences, the largest being some data reconstructed from iClear 2018. So as we restrict the probabilities, the assignment quality decreases as you'd expect, but it decreases fairly gently. And on iClear, we can get 90.8% of the optimal similarity, restricting the probability of each assignment to 0.5. Another question you might ask is how well does this algorithm prevent manipulation? And so to do this, we simulate a malicious reviewer who is manipulating their bids in order to get assigned to some target paper. And on the x-axis here, we show how high the pre-bid similarity is between that reviewer and their target paper. And we see here, first of all, that when the malicious reviewer doesn't bid at all, their probabilities are generally low unless their similarity was already quite high. But if the malicious reviewer bids specifically to get assigned to a target paper, they can significantly increase their probability of being assigned to it under a standard assignment algorithm. Of course, under our randomized assignment algorithm, we can cap the probability of assignment at whatever we like. So in this case, 0.5. So in the paper, which I don't have time to get into here, we consider this more general problem of limiting the probability that pairs of reviewers are assigned to the same paper. And we show that this is NP-hard in general, but tractable in a relevant special case, which we solve with some modifications of our first algorithm. So in this work overall, we identified several issues in peer review. These are the issues of untruthful favorable reviews, of torpedo reviewing, and of reviewer de-anonymization. And we present the framework of randomized assignments to address all of them. We design algorithms that find randomized assignments that are optimal for when you constrain the assignment probabilities, as well as for certain constraints on pairs of reviewers. And some directions for future work include mainly what other sorts of constraints on the sampled assignment can be implemented, particularly constraints on the ex post assignment that's actually sampled. And I'm happy to take any questions that anyone has.
So I believe Rishiv already had a few comments and questions. Rishiv, do you want to speak up?
Yeah, so it developed into a short discussion here with Vince. So the question is how, I mean, according to your experience, how real is the problem of de-anonymization of reviewing data? Because I think it's a good thing that conferences will release the data, but we usually have the opposite problem where they're very scared to do that. So like, how justified is this concern, like even without limiting the probability like you do?
Mm-hmm. I know at least in the past we have spoken to, there was at least one conference that we were discussing the similarity data with, and they were concerned specifically about this issue. But I would say the specific answer to how concerned conferences are about this might depend on the organizers themselves. Maybe there are some organizers who aren't too concerned about this de-anonymization issue. But I think it is reasonable for organizers to be concerned about this kind of thing, because it is possible that perhaps you could figure something out about the reviewers for your paper, which would be undesirable. And so I think that's one benefit of the randomized assignment proposal, is that this issue is, this concern would be much less of an issue.
Okay. Thanks.
All right, if there are no other questions, then we have the final contributor talk of this session. So it's Jonathan or Rishiv. Okay, we can start. Jonathan, we can't hear you.
Okay, and now you can?
Yes.
Okay, so hello again, everybody. Thanks for having me here. I'll be presenting my joint work with Reshef here, my PhD supervisor. And we're talking about divisible participatory budgeting model that is unique in the sense that we're not only letting voters decide what should be the allocation of a given budget among different alternatives, usually called projects, but we also let them determine the volume of the available budget by saying how much tax would they rather pay to fund that budget with. Okay, so here's a first example. We have 4 voters, and we have this exogenous B0 of source of public funds. Yes, it's not in the chat. So, for example, voter 1, every voter has to submit the preferred level of tax and the preferred allocation of the resulting overall budget among these 3 different alternatives. Okay, now here in this example, it would be parking slots, street lighting, and parks. So, for example, voter 1 wishes to pay a tax of $10, meaning that she wants every citizen to pay a tax of $10, and then the resulting $240 should be spent according to a submitted allocation. On the other hand, voters might also ask for a negative tax, meaning that voter 4, for example, wants some of that 200 that are already existing to be given to them directly. Okay, so he would like every citizen to get a $5 grant in cash, and the remaining $180 should be spent according to his preferred allocation. Okay, so a mechanism should output a budget decision, meaning tax T star, that could be negative or positive, and an allocation, a partition of the resulting overall budget among the given alternatives. Okay, so any questions about the model? Right, so our contributions are first, so conceptually, as I mentioned, voters also determine the volume of the available resources. And in the technical level, we introduce a divisible PB mechanism that is truthful under additive utilities, whereas in existing literature, so far we have 2 works that introduce truthful mechanisms under L1 norm preferences. For those of you who are not familiar with it, so L1 preferences means that every voter has this ideal ideal allocation, and the disutility of an agent is the L1 distance equals the L1 distance from that ideal allocation to the allocation that is implemented in practice. So here we offer a truthful mechanism for a more explicit, more detailed utility model. And in fact, if you try to apply these mechanisms on additive utilities agents, they would no longer be truthful. Okay. In addition to that, we have the work of Fein and Associates that they were mainly focused on the core notion, but they also introduced a mechanism that is approximately truthful. Okay, so incentives to manipulate could occur, but they are bounded by some additive context, a constant. Okay. Moreover, unlike these mentioned mechanisms and unlike VCG mechanisms in general, truthfulness in our case is obtained in strictly dominant strategies. While that is not enough to formally satisfy the group strategy proofness by definition, it does imply some improvement in that direction. And that is because if truthfulness is strictly a dominant strategy, well, even if some coalition is formed and they all can benefit from some coordinated misreport, any member in that coalition always has a strict incentive to like betray his fellow manipulators and deviate back to being truthful. So, because they are not indifferent, they are never indifferent between report truly or untruly, as a lot of times happens in VCG mechanisms, and you mentioned mechanisms as well. Questions? Okay, so getting into more details, we have the utility function for an agent. So the utility of agent I in a budget decision xt, okay, a consistent budget decision means that the sum of this xj must equal the b0 plus nt. Okay, so the utility is the first part. This sum is the standard additive utility. Okay, we have the theta functions for each alternative j that are increasing, and we assume also, as very commonly assumed, strictly concave functions. Okay, so theta j is a function of the amount spent on alternative j, and we also additionally introduce this f, that is the utility or disutility from money gains or losses. Okay, so in the budget decision xt, agent I gains utility from consuming the public products that are funded, and yes, this utility, in case t is positive, from paying the tax t. Okay, now in the paper we formalize f as the value function from prospect theory, but for our main result of the truthfulness, it shouldn't matter, the choice of f. I just want to point out that here for the purpose of our talk, we will assume that the alpha ij's are normalized so that the sum from j that on alpha ij's come from 1 to n is 1, and that is a very common assumption in various utility models, but it should not be taken for granted here. Okay, so I won't get into it now, but in the paper we actually do not assume that, but we show that if the mechanism treats the utilities as if they are normalized, well, then the incentives are not harmed. Okay, so for our purposes, consider them as normalized. Okay, so what our mechanism that we call the PB-VCG mechanism does is basically VCG mechanism, okay, that selects the social welfare maximizing budget decision. Okay, so x star t star will be the optimum with respect to this sum, the sum of utilities of all agents, and then we have to charge voters with the VCG payment. Okay, but now we have to, and that is in fact a point that much of our technical effort in the paper is dedicated to. We have to somehow generalize these VCG payments in such a way that they suit non-quasi-linear utilities. Okay, and that is not straightforward. I mean, if you will try to like naively define the payments as in the classic VCG definition, you will end up with something meaningless. I'm not sure about the time, but maybe we'll come back to that. I think I still have. How much time do I have left?
Five more minutes.
5 more minutes. Okay, so maybe we'll skip on that. Okay, and also note that payments are charged on top of the tax T. Okay, so the tax is a part of the decision, the outcome, and payments, as usual, are charged on top. Okay, so the result that we achieve in this mechanism is, as I mentioned before, truthfulness and strictly dominant strategies. That is achieved mainly because if you try to compute the utilitarian optimum, where utilities are additive themselves, then it depends eventually only on the mean of the references. So the outcome that this mechanism outputs depends on the mean, on the average of this alpha, of these coefficients, alpha ij's and alpha if's. Okay, and then what it means is that every change in any voter's vote inevitably changes the outcome. Okay, so what usually happens in VCG mechanisms where voters are indifferent between misreporting and being truthful because they are not pivotal and their vote does not actually affect the outcome, cannot happen here. And that mainly what makes the truthful strategy strictly dominant. We need a little more some additional mild assumption on the smoothness and functions, but let's omit that for now. And okay, and another important result is that, of course, beyond the technical challenge of adapting the VCG prices properly, another reason that VCG is, is not really suitable for PB process is that, well, it doesn't seem reasonable to charge participants in a democratic procedure with prices, right? It should be free to participate. So this is another main concern in our paper, to trying to minimize or vanish, if possible, the prices. And we show for now, for the special case of logarithmic utilities, and if B0 equals 0, we show that payments do vanish in large populations. Obviously, our first objective in further research would be expanding that class of utility functions for which we can control payments. So I guess that would be all. If there are any questions, I'll be happy to take.
So there are quite a few comments in the comment section. So Paulo has a comment.
Okay, let me see that. Can you elaborate on how use prospect theory to formalize? How do we use prospect theory? Well, I just take that f to be the value function that they use there. Okay, and unlike general utility functions from consuming public or private products, this function has been actually put to test a lot various times in the past research. So, but for the purpose, for the result of the truthfulness, you can choose whatever you like. I mean, as long as it's invertible, it would work.
One last question is by Vince. It's the last comment in this chat.
To redistribute some payment in SP way. What do you mean by SP?
I believe it's strategy proof.
Oh, so you mean like, well, there's a lot of literature in general for VCG, for redistribution in VCG mechanisms, and I don't see a reason why these methods cannot work here. But if you mean like that I charge the payment from voter, and then somehow it affects his weight in the process of choosing the outcome, then that could be much more complicated, okay, because that would interfere with truthfulness. I mean, at least you know, in first glance, okay, because if you do that, then the prices are not actually separated from the outcome, okay. The price you charge actually affects the final outcome and complicates everything.
All right, so we're running a bit late, but I think we should still have a short break so that people can stretch their legs or have some water. So we'll have a 5-minute break. If you want to leave and stretch your legs, that's fine. Otherwise, I'll ask Umar to divide us into some breakout rooms. And after 5 minutes, we'll be back for our invited talk. So Samina is already here. So we'll have our invited talk, which will be part of this session. So we'll have a 5-minute break right now. Umar, are you doing the breakout?
Yes, you should begin seeing people disappear from your view.
Ah, I see.
As they join the breakout rooms.
Are we not invited to breakout rooms?
I think because we're co-hosts, we're not.
I see. Okay.
I was also wondering about that myself. Yeah, but it seems that people are joining. He does it randomly, but for some reason, some rooms there are 0 joiners and some people have joined. Anyway, where's Nick? He's the next session.
I haven't seen him at all. Actually, wasn't he supposed to be in this?
It's 8 in the morning for him, right? Close to 9.
Well, Hadi is also here, so that's fine.
Yeah.
I may have to disappear for half an hour for another meeting,
Thanks, Sophia.
but I will be back.
Great.
I asked to move the meeting. I'm not sure if the message reached the person in time. So if I disappear, I will be back in 45 minutes or so.
This is definitely my last session because it's 11 p.m. here.
Haris, if you need to go, then we can take over for like Simina's talk. If you need to rush, like tired.
It's fine. I'll introduce her and then I'll be around.
I was saying we need to also understand if session 4 starts with the first paper or not, because there was an issue of a swapping, but we didn't manage to properly arrange the swap.
I mean, well, we do need one less talk to get back on time.
I mean, if they're there, great. If not, we move on.
Is Samina here or is she in one of the breakout rooms?
She's here. She's here. I saw her. Oh, yeah, she's here. Samina, do you want to share your slides? See that everything works?
Hello.
Hey.
Sorry,
Hi.
just one moment. I'm still polishing something in my slides that I didn't go to the breakout room. Let me. Hello.
Hey.
Hi.
Can I'll be back in a moment. Sorry, I still have something to do on my computer. I'll share my slides in a moment.
Okay. Well, it's a good thing Haris, where everyone's in a breakout room, so they keep on interacting, and we'll call them back when Simina's ready.
Exactly. I think it's been quite smooth.
Yeah.
It's almost like a pre-AAMAS conference before the AAMAS conference.
Yes. I actually don't know how much time I'll have to actually participate at AAMAS. This is like, I think, my main participation. My papers are presented by colleagues, so I can.
I see.
Yeah. Nisarg, you're talking, but we're not hearing you.
Yeah, I just wanted to say thanks to all the organizers for organizing this. This has been really awesome.
Yeah, it's been fun.
I think most credit goes to Hadi, who hasn't shared anything yet, but he will.
Yeah.
And everybody, Yair was doing a lot of the easy chair.
All right, yeah.
Work.
Yeah.
Hey, everybody.
Hey.
Hi.
Hey. It's going really smoothly. I like that.
I mean, we're about 15 minutes off schedule, but like there's nothing like stopping us from going 15 minutes onwards in the last session.
That's not bad at all. Like I was expecting, in fact, last night I was dreaming that I wake up and we are like an hour off the schedule or something like that. Because the schedule is very packed, right? It's like back-to-back talks.
Yeah.
Well, it's been interactive, so people were discussing and asking questions, so I didn't want to stop them.
Yeah.
I think people are very used. I don't know if just the Comstock seminar, but the culture of writing your questions in the chat and some co-authors answering it there if they're present is very much from what was established there, and people are just going with it.
I'm even using Ule's advice and writing question with a caps lock.
I'm even doing that in my classes when I teach. I tell my students, you have to put your questions like that, because otherwise I don't know if it's a comment or, I mean, I'm not going to check them one by one.
I mean, I did that when I was teaching from home, but we just started now teaching these hybrid classes where you're teaching in front of a class, but some are on Zoom, and then you can't see their chat. So I tell them, I know I previously told you to, like, if you have a question, put it on the chat, I'll see it, but I can't because there's a class in front of you. You have to unmute yourself and ask the question.
So Samina, if you share your slide, we can then start inviting people back from the breakout room.
Yes. Let me see how I do that.
You were making me very nervous when I couldn't see you.
Oh, I'm sorry. Can you hear?
I couldn't hear you at the end.
Now, in the picture.
Uh-oh.
I mean, we see yourself, but by the way, hi.
Hello.
How are you doing?
Oh, you're talking by
not so good right now. So you cannot hear me?
We can hear you.
Wait, we can hear you, but you're mute. It's very interesting.
No, there are two.
No, she's also joined through the other.
Sharing.
There is another seminar.
Sorry, so I have a yeah. Sorry, there is a bit of a technology issue right now on my end, and this is the best solution I can come up with.
Yep,
okay,
this works.
Do you want to share your slides to see if we can see them?
Yes, I can share my slides.
So which seminar would be giving the talk?
The one that doesn't have the, I don't know, I should call that a different thing. I'm sorry, my computer is having an issue.
Let's verify that we can see your slides, and then I can call everyone for the back from the big rooms.
Okay. Can you see my slides?
All good. Yes.
Okay, so I'm calling everyone back, Harris?
Yes.
I can try to log in from, I don't know, I have another computer that I can try to log in from if you want me to.
I think you're good, and we can try to pin your, I think it's possible to pin you at the top. I'm not the host. The host can maybe do that so that we can see, because the sounds
I'll make you the host.
Okay, thanks. Maybe I can.
So
I can log in from a different computer if you.
No, it's
Okay.
We can hear you
Yeah.
fine.
So I
Yeah,
made
yeah,
you
yeah.
on spotlight. You should be, everyone should be able to see you. It's okay. You'll be completely fine. Your sound coming from a different one.
Everyone's seeing you.
Oh yeah.
Yeah, everyone sees you. Now you're
Oh,
spotlight.
okay.
Yeah.
So what were the numbers before? About 50, right?
So I logged in from. I have a computer. I fixed this problem, but I don't know. Maybe it's too late. So
It's working fine, so
you can.
don't worry.
It's fine as it is.
Yeah.
Okay. So you tell me when to start.
Sure, I'll introduce you. Don't worry.
Okay.
Omar, are we at full strength? Or?
I think everyone's back.
Timina, can you make your screen full screen? Because we only, maybe you can, it would be better if you can make it full screen.
Yeah, you can try Control L or Command L.
Yeah.
Yes. Is it
There you
working
go.
now?
Perfect. Yes.
Okay.
All right. Okay. Great. Everything's working. So it's a great pleasure to welcome Ximena. Ximena is an assistant professor at Purdue University. She got her PhD in Aarhus University, but she has traveled quite a bit. So she has had positions at Simon Institute, Hebrew University. And one less recent fact is that Ximena also had an AAMAS paper as an undergrad. That's when I first met her at a conference. So it's a pleasure to have you here. It's all yours.
Thank you very much for inviting me, and thanks for being here at my talk. So I'll talk about a problem in a market, and it's going to be about a distributed production market. And basically we'll be interested in growth dynamics. So before I say that, I should specify what I mean by growth dynamics. One thing that such dynamics can mean is when we look at the interaction of animal species, like we have on the left, and cells in the bottom pictures, they can interact in a resource-rich environment, and different species can help or destroy each other. And there are other notions where growth makes place, so that takes place where if we measure magnetic data storage, or DNA sequence data, there is an increasing trend. Or if we look at life expectancy, or the mechanization and agriculture and people living in nicer houses, or in particular the global scientific output, which is estimated to double every 9 years. So these are some ways in which we can think of growth at a high level. And von Neumann studied this question in a mathematical model. So in his model, there is a set of players labeled from 1 to n, and each player can make one type of good. So player I can make good I, which could mean, player I could make cars or computers or I don't know, produce bitcoins anyway, various things. So they can be also digital goods like music. And the player has some production function that is intrinsic to it. So it has the following form. If player I gets his input an amount y1 of good 1, y2 of good 2, and so on up to yn of good n, then what it will make from it is an amount given by the sum overall j of aij times yj of good I. So basically the player has a recipe, and this is like a linear conversion ratio. So player I, if it is given 1 unit of good j, then it can make from it aij units of good I. So this is the amount that player I makes from the bundle y1 to yn. And this, actually one other example that is captured by this is if you have a set of n currencies, each player has a currency, and then they look at at the conversion ratio. So like this could be if you want to exploit the market and make some money from fluctuations. And roughly we'll be looking at the amounts that the players have, of goods that the players have. So in this very simple model, a basic decision that the economy needs to make is how to allocate the resources and how to basically split the goods that are produced at time t, like if we think about it as a process that takes place over time. So we have some goods, and then these goods will be input for production time t+1. And the question is, how should this be done? Like, one way in which it could be done is that someone looks at all the data, at how the efficiency of each agent and the value that it has for each good, and then decides how this should be done. Probably the agents would like to have some freedom so that they decide for themselves how to use the resources, what to buy, what to sell, and so on. This is a simple example with two agents. So we have player 1 and 2. Player 1, if he gets, so what this graph means is if player 1 gets 1 unit of good 1, which is the good that player 1 makes, then this gets converted to 0.99 units of good 1. So it means basically if the player keeps the good kind of vanishes. It's like food that he will eat. On the other hand, if player 1 gets as input 1 unit of good 2, then it will make from it 0.1 units of good 1. So here the conversion ratio is not very high. He can make a little bit of good 1 using the input of player 2. However, the player 2 finds the input of player 1 very useful. So given 1 unit of good 1, player 2 makes 10.2 units of good 2. So here, if we think about this taking place over time, we can already notice that if each good is consumed by its producer, so player 1 in every round, player 1 gets the entire amount of good 1, and he will produce from it. So basically, he's not really producing his consuming his good. And then the total amount of the goods will become very small over time. They will eventually go to 0. However, if the players cooperate in some sense, and if the whole quantity of each good is allocated to the other player and vice versa, then we'll notice that their amount will be increasing. We'll look at mechanisms for allocating the goods, basically, and we'll be interested, if possible, in mechanisms where players take individual decisions, where there isn't like a central authority that tells them, when you go to the market, you have to buy this much of this good, this much of this other good. So the players themselves will decide, but we will study some specific allocation rule. And we'll say that an exchange mechanism is universal if it enables growth of the economies whenever growth is possible. So roughly, we would like a mechanism that if the economy can grow, then it could take us from the world on the left to the one on the right. And a basic problem here is that even if the players can be productive in principle, on a daily basis, they can take myopic decisions that can lead to them becoming very poor in the long run because they don't have foresight. And so this is a kind of phenomenon that can appear in this type of market. So I would like to explain a market mechanism that will be the basis of the system we study, and this is known as the Shapley-Shubik game or trading posts. So here we'll have Alice and Bob, our two players. Alice comes to the market. She brings some meat that she wants to sell. Maybe she will try to keep some of. She will keep some of it, but and Bob brings wheat, which is his product. And also each player will also bring some money. So Alice has $4 and Bob brings $8. And they would like to, basically when they go home, Alice would like to have both some wheat and meat, and similarly for Bob. And the mechanism for allocating the goods is that is through a contest. So each player will bid for each good. And I'm going to give an example with some specific numbers. So let's say that Alice bids, so she has $4. Let's say that she bids $3 on the meat and $1 on wheat. And Bob bids $6 on meat and $2 on wheat. So then Alice will get, so each player will get a fraction of each good that is proportional to their bid. So Alice will get 3, which is her bid, divided by 3 plus 6, which is the sum of their bids, which is 3/9 of the meat. So if we think like the fraction of meat that she gets, or if it's a kilogram, that would be 3/9 of a kilogram. And the amount that she gets from the wheat is 1 divided by 1 plus 2, which is 1/3. And then we can similarly calculate for Bob. Bob gets 3/4 of the meat and 2/3 of the wheat. So you can notice that this sums up to 1. So this is a mechanism where basically when agents go to the market, they have some product, they have some money, and they will bid on different goods. They place bids, like let's say the players have a basket on which the bids are placed, and then the seller of each good allocates that good in proportion to the bid amount of each player. And then the seller collects the money that they made from selling. So in this case, Alice gets $9 and Bob gets $3. So the dynamic that we study will have each producer start with some amount of its good and some budget, which will be understood as a virtual currency that can be used to acquire goods. And in each time unit, the players will bring the goods to the market. They will bid, and then every good will be allocated in proportion to the bid amount, as in trading post, as I just explained. And basically, the seller of each good will collect the money from selling, and then it will go home and produce from the bundles purchased. So after Alice acquired the wheat and the meat, she takes her basket with these products and the money, and she goes home and she will work for the next period, and then the next period she will bring some more meat. So she's a meat producer, and Bob produces wheat. And now there's a question of how will the players bid next time? Like depending, because when they go to the market, they notice the competition that is on every good. And the rule for updating that we study is a proportional updating rule. So where in each time unit, every player will split the money that it has into bids in a way that is proportional to the contribution of each good in its production in the last round. So roughly, if a good was if there was a lot of utility that the player got from a good, then it will want to bid more on that compared to something that gave it less utility. This is the formal definition of the dynamical system we study. So each producer I will start with some amount of good I, which will be denoted by xi. So it's xi 0 is the amount at time 0, and the budget bi of 0 that can be used to acquire goods. And at each time t, each player I will basically bid on the goods and get an allocation. Then it will go home and work on producing for the next round, and then it will update its bids. Oh, sorry, there's a question. Can you tell me the question, or I'm sharing screen and I don't quite see the chat, or what am I? How should
I can read the question for you. So I think Amy is asking clarification questions. What are the prices at which these goods are traded? And then later she's again asking same price for all, or do players pay what they bid? So essentially, what are the price schemes?
So this is okay. So here is so yes, they pay what they bid. So the trading post mechanism was proposed by Shapley and Shubik to explain the formation of prices in an exchange economy, where so each player comes with some good and with some money that is like a virtual currency, and then they bid on the goods, and then the sum of bids at a good represent the price of that good, can be understood as the price. And okay, so basically here, so I think it will be clear once you see the formal definition. So in the allocation, basically, so the players submit bids bij at t, at time t. So this is for each player I at time t. So it bids on the goods, it submits the bids bij of t, and then the amount that it gets from good j is by yij of t. So it's bij of t divided by the sum of bkj of t. This is the sum of bids at that good, and so this is the fraction that it gets from the good, and then that's multiplied by the amount of the good, which is xj of t. And this is if there are any bids at that good whatsoever. If not, it gets 0. So the sum of bids is the price in some sense. and then the players produce, so with they have their production function, so this is not going to change. So the amount that player I can produce from a bundle acquired, yi is the sum of aij times yij of t. So yij of t is how much player I got from good j, time t, like when he goes home with his product. And aij is given a unit of good j, player I can make aij units of good I from it. And then the players update their bids, so the sellers collects the money from selling, which is expressed through the budget of player I around t plus 1 is the sum of bids at it's good, so it's the sum of bki of t. And then the player will update its bids in a way that is proportional to its production, basically. So this bracket here, so it's the aij times yij of t. This is how much player I made from good j. And it divides this by its whole production, which is xi of t plus 1. So this is the fraction that of its money that it will bid on good j in the next round. And that's multiplied by the money it will have in the next round. Are there any questions about the model or any other questions? No? Okay, so basically, so some remarks. This is a non-linear dynamical system, and the players interact with their direct neighbors. So basically, we have a graph that is given by the edges aij. So if an edge aij is 0, then there is no player I will not buy the good of player j. And players will interact with their neighbors on in this network, which is directed, and they will continuously adapt their bids based on what happened in the previous round. So, a few remarks. So this model, the static model, was first studied and modeled by von Neumann, and initially it was focused for the ONTF. And the analysis focused on analyzing equilibrium-like states where the economy expands by the same factor as time goes, and also at what rate that happens, which processes will take place, and so on. And the additive model, which is the one we study, which captures substitutes, these are goods that can replace each other in production, was studied by GAIW, among others. So there are also several books that talk about these, and the work is also related to various works on market dynamics, learning how to bid in auctions and markets. And one particular line of work is on learning dynamics in blockchain mining. So there's a paper by Chong, Leonardos, and Piliras. So in the blockchain, the miners will also bid, and they get, in the sense that they invest and they get a fraction that is proportional to their investment. So there are some similarities to this type of market. And it's also related to a growth model by Lotka and Volterra, which is used to describe the dynamics of biological systems, so it captures the interactions of species and how they help or destroy each other. So for example, if we have the interaction between wolves and rabbits, and wolves reduce the population of rabbits. So there you also have a matrix aij, which if it's less than 1, it's so species j reduces species I, like if it's like wolves and rabbits. So this is a simulation from the system for 2 players. It's where let's say the initial states are such that each player has 1 unit of its goods and $1, and they start by bidding equally. So each bids 0.5 on each good. And this is how the amounts progress over time. Player 2 is shown in orange and player 1 in blue. And we can see that their progress, so to speak, is not monotone. So the amounts oscillate, they go down, then go up again. But here there is an increasing trend. These are the budgets. So these also have a lot of fluctuations. And this is the fraction that each player invests in the other good So in blue, basically, this is the fraction that player 1 invests on good 2, and in orange, the fraction that player 2 invests on good 1. And if we wanted that the players do have increasing amounts over time of their good, then this is what we would want, in fact. Like if we go back to this picture, so here there is one, like if player 1 keeps investing on its own stuff, it will lose in the long run. So it should invest in good 2 as long as player 2 also invests in good 1. Okay, so this is what we see in the simulation for this instance. So question is obviously what happens in the system. And our first result is that this mechanism is a universal exchange mechanism in the sense that the economy will have more and more amounts of goods. So the specific thing that we look at, so we look at what could be understood as the volume. So if we take C to be any cycle, and denote alpha the product of edges along the cycle. So it's the product of overall pairs ij of the value aij. And we multiply everything together. So we define a function f of t, which is the product overall edges ij in the cycle of bij of t times xi of t. So remember that bij of t is the bid of player I on good j at time t, and xi of t is the amount of player I at time t. Then we obtain that this is a potential function. So we have that f of t plus 1 is greater than f of t for all times t, as long as alpha is greater than 1. And if alpha is less than 1, then f of t plus 1 will be less than f of t. In fact, we get a direct formula for it that f of t is alpha to the t times f of 0. And then from this, if alpha is greater than 1, so if this is a cycle that has product greater than 1, then the limit of f of t is infinity, and that implies in particular, so implied that the limit of the amounts of the goods on the cycle also goes to infinity. So the players on the cycle, on a cycle that has product greater than 1 will become arbitrarily rich. So one example that there is some recent work that also looks at in the Bitcoin system at fluctuation of currencies and how people can buy or sell, like if the value of a currency is increasing or decreasing, and how they can make money from this. So that could be another example to have in mind. Like if each player kind of has a currency and the values, they buy and sell currencies, and they could also buy their own, but to still keep it. Sorry. Are there any questions at this point? Okay, so so this is about the long-term behavior of the amounts, and we say that a cycle is good if it has product greater than 1, and bad if it has product less than 1, and it's the best if it has the highest geometric mean. So we obtained that a corollary of the previous theorem is that every player with a good self-loop will have a growing amount over time. And also we get that the rate of growth is optimal up to some constant. So if we have C to be one of the best cycles, so one of the cycles with the highest geometric mean, then there will exist constants C and D, so that for every player I, the amount of player I at time t will be roughly alpha to the power t over the length of the cycle C. And so there are the upper and the lower bounds depend on some constants, and these constants C and D can depend on the initial matrix A and the number of players. And the upper bound is given by so the maximum growth rate is bounded by the best cycle. And for the lower bound, we use the recursion given by the potential function, and the fact that the money in the economy stays is bounded. And then we also get from it that all the players, if there is a good cycle, then all the players on the best cycle will grow. And there is a question here about, we haven't figured out everything, basically, like what happens with players that, like if a player is on a good cycle, does it mean that it will grow, that its amount will grow in the long run? So we didn't show that. So we showed that if they're on good enough cycle. So they don't need to be on the best cycle to grow. They can, all the players that are on cycle with value greater than some bound, like as a function of alpha, the mean of the best cycle, those pairs will also grow. And so this is a question that is still remaining if all the players on a good cycle are guaranteed to grow. So in some sense, these are part of the efficient economy. One thing that we also noticed is that not all growth is equal. So this is an example of an economy with 4 agents. So there is agent 4 is at the center, and everybody else trades with agent 4. So players 1, 2, and 3. And here we can notice that there is one cycle that has product greater than 1. So it's the cycle between players 2 and 4. If we multiply 0.5 by 3.125. However, player 3 also grows. So player 3 is actually not on a good cycle itself, but it's kind of well positioned in the network. So if we look at the amounts on the right, so player 3's amount is going up, but the amount of player 4 is going up much faster. And we showed formally that there is a kind of inequality effect where the producers will get differentiated over time into 2 classes, the rich and the poor. So the rich here are the ones that participate in the most efficient production cycle, and the poor are the other ones. And what happens is that the inequality ratio within the max efficiency class remains bounded by a constant. And the inequality ratio between this class and the rest grows to infinity. How much time do I have?
I think we still have 10-15 minutes.
Sorry, I couldn't hear you. Can you say again?
We started 10-15 minutes late, so you still have 10-15 minutes to go if you want.
Oh, I see. Okay. Okay, so this is what happens in if we measure the most efficient, the cycle with the highest geometric mean, so this is a plot from the previous graph that shows this effect for 2 players. These are some examples from the simulation. So here is an economy where so we have players 1 and 2 again. And what varies, so on in the plot on the left, it shows the budgets of the players over, it's actually the Gini coefficient, which is a measure of inequality for the budgets of the players. So the Gini coefficient can be defined for any for any vector, and it measures the amount of inequality in that vector. And here what happens is that on the x-axis we have it goes from 0 to 2, and it shows the self loop, the value of the self loop of agent 1. And on the y-axis, it also goes from 0 to 2, and it measures the value of the self loop of agent 2. And the region that is in blue shows, so blue here means smaller inequality. And the reason for which we are observing this is that when the value of the self loop of a player is up to roughly 1.25, then the players will cooperate. So they will work with each other. They will buy each other's good. And this way, because the best cycle in the graph with the highest geometric mean is the one that contains both players. So so their amounts will be roughly close to each other. This also happens on the diagonal if the self loops have the same value, but the value is higher than the geometric mean of the cycle that contains both players. So the geometric mean is like 1. If it's 15 times 0.1, so it's 1.5. In the yellow region, there is high inequality, and the reason there is that one of the players will have a self loop that is higher than the geometric mean of the cycle that contains both players. So that player will produce by itself. It won't invest in the good of the other player. And so the other player will fall behind. And we see a similar effect for amounts on the right picture. So these are some other plots that, from the simulation. This is also the Gini coefficient, but here the initial bids are varying. So I want to mention one more phenomenon on stars. So this is again the graph that I showed earlier with a star economy. So we have player 4 at the center, and the best cycle is the one that contains both players 2 and 4. If we look at the amount of player 3, so here it's staying in a bounded region. If we increase a little bit one of its edges of players between player 3 and 4, then the amount of player 3 starts going up, and if we decrease it a little, it starts going to 0. And what happens is that there is an effect that we show formally. So if we have a star economy, so there's a player at the center that everyone trades with, and suppose that this economy has at least one good cycle, which we denote by alpha star, the value of the cycle. And alpha I will be the value of cycle I. So it's the product of the edges between player I and the center. So it's AIN times ANI. Then for every player I, other than the center, which is denoted by player N here, the amount of player I will grow infinitely if alpha I is greater than 1 over square root of alpha star. It goes to 0 if alpha is strictly less than that, and it stays in a bounded region throughout time if alpha is 1 over square root of alpha star. So there is a phase transition taking place at 1 over square root of alpha star. And so it would be interesting to understand this also more general graphs. We haven't been able to show if exactly what happens with a player in a general network. Other than we know about the players that are on the best cycle, but we don't know exactly if there is still the question if their amount will grow or not. Okay, so to show this, so basically we can get here, because the network structure is simpler, we can actually get some recurrences for the fractions that the center invested time. T plus 3 is a function of the fractions invested time t. And then basically we show a lemma that holds in any economy, which is that the players on the best cycle will have the amount of money that they have is not vanishing. So the bid bij of t at of player I on good j at time t will be bounded from below by some delta, which is delta is a constant. So in particular, this means that the players on the best cycle will have non-negligible budgets throughout time. Okay, so here we use the recurrence and what we derived about the amount. And this is basically this shows the phase transition, because here we have the terms in red are basically bounded by some constants, and then the terms in brackets gives the long-term behavior, this alpha I times square root of alpha star. Okay, so I discussed trading posts with proportional updates in the von Neumann's model of a production economy with additive utilities. So we learned that this leads to growth of the economy whenever growth is possible. And in particular, that the players on the best cycle grow, so they have their amounts increasing arbitrarily over time. And this is also true for players that have good self loops and players that are on kind of good enough cycles. But we don't know exactly what happens if a player is on a good cycle. Is that player guaranteed to grow? We see also that the growth of players that are not on productive cycles is supported if they're well networked. So basically, depending on their position in the network. And we also observe growing inequality, that the players on the best cycle will get arbitrarily richer than the rest. This can also be seen as one of the takeaways. It can be seen as also as a simple decentralized dynamic that learns a global feature of the network, which is the optimal cycle. So in this case, that's the cycle with the highest geometric mean. And this is happening while the players communicate only locally with their direct neighbors, and basically the information flows through the network. Okay, so this is what I had. If you have any more questions for me, let me know.
Okay, thank you so much, Simina. Great talk. Let's do a round of applause for Simina. Thank you. It's open for any questions that you guys may have. So feel free to either type it in the chat, I will read it, or you can unmute yourself. So Reshef has a comment, says, so the trickle-down economics does not work. Really?
Oh. Maybe it works in a different model. I don't know.
Okay, so while people
Yeah.
are thinking, I have a question actually. So you talked about
Okay.
equality, and you started this whole talk about kind of like this, the kind of trying to create equality between different people. And it seems to me, especially towards the end of the talk, that you were talking about these different topographies. How dependent is it to a topography, like the way that you can have some rich agents or some poor agents, or are there any specific like graph models or topography models or market models that would be fairer in the with kind of keeping everybody like in an equal?
So actually the what happens is that the inequality, the growing inequality happens in, so the only basically this happens like in any graph, like even if so okay, we need the graph, we assume the graph is strongly connected, I guess. I mean, if it's not strongly connected, like if a player I bids on player J but player J doesn't bid on it, and that's
Or it can be a
then
ring, right? It can also be a ring. I feel like ring might also be a graph that be kind of, you're only connected to your neighbors.
But this can happen also in a clique. So this is not dependent on the only assumption that we make for this theorem is that there is a maximum efficiency. So there is a unique best cycle. So that means that like when you look at, so basically the parameter that determines this, there are the parameters aij, which is the value of player I for a good J. In some sense, is like given 1 unit of good J, how much can player I make of its own good, and that's something that stays fixed. It's independent of the dynamic. So that basically induces a weighted directed graph. And if that weighted directed graph has one cycle with the highest geometric mean, as opposed to having multiple ones, then you observe this inequality effect. So it's very general in that sense. For this, but it's for this dynamic. So one thing you could say, well, maybe players don't update proportionally to their investments. So this could be studied, for, I don't know, maybe they could update using other updating rules. So this particular rule has been used before in Fisher markets, like it's known as proportional response. But sorry, yeah, sorry, go ahead.
No, that's it. Thank you. I just wasn't sure how, I mean, if this result holds for, or is it dependent on specific dynamic? But you're saying it's really not dependent on the topography, it's more general.
So it's I mean, it's in the model that we study where the players, they have money, they have goods, they bid on the goods, they get it's like this trading post allocation rule, and then they update proportionally. The inequality is not dependent on the graph topology. It's the only assumption we make for inequality is that the best cycle is unique. So other than, there could be multiple ones, but basically inequality happens here even if all the amounts go to zero in the long run, you'll still see inequality because it's just a matter of how the cycles are related to each other. And this is also true, the result about the growth of the players. So the players on the best cycle will have their amounts go to infinity. And that's also independent of the topology, as long as there is such a cycle that's non-zero. But you asked something about like if inequality could be reduced. So I was actually thinking about that. I mean, one thing is like probably you'd want like a bank to print money, to give money to the players. Like if a player starts running out of money, having less and less, could there be a way to give that player some money so that they can have more buying power in the economy?
I was mostly thinking about instead of giving money, because that seems a little bit problematic of like you want to kind of give more budget to a bunch of like players. Instead of that, trying to design the topology in a way that kind of reduces the inequality.
I see.
But yeah, that's I'm not sure if it's possible. Just
yeah. So this, I
because you
think,
can enforce policies, right, to do that, but you cannot kind of give money to people. That doesn't seem very natural.
well, I mean, so this, I guess the issue is that the inequality will happen basically in all graphs that have where the best cycle, where all directed graphs with weights, where the cycle, the highest geometric mean is unique. So, but I think it is the case that I mean, I don't know, when there are economic problems, I thought governments do give money to people, like, so that's a way of reducing inequality, basically. But I'm not saying it's very elegant to study. I just
yeah, definitely an issue here in America. But let's see if there are any other questions. Actually, Reshef is asking or commenting on interesting things like about breaking the evil circles. Do you have any thoughts on that? Like, is it possible to somehow break some of these cycles? Like,
well, I think one thing that is maybe that I thought would happen is that if a player sees, like, if a player brings some good that the other players are not investing in, I think in reality what the player would do is that he would produce another good, or he would like change his good. You know, maybe if it's a phone, he would add a feature to the phone, or like he would improve the software or the hardware so that buyers are more likely to buy it. So here we don't allow that kind of evolution where the agents can improve their products, or so maybe that could then, you know, then that could create, the cycles could be more short-lived, like if the production of the agents changes. But we didn't study that. But yeah, that's a good point. I mean, the thing is, it is at the same time like the cycles are also what kind of drives the production in a way. But it also creates some negative effects.
Mm-hmm.
So Kate, maybe just a follow up. So yeah, you're right. So if you, I mean, I was half joking when I said like the cycles, because obviously that's what kind of driving the whole economy here. But I wonder if there's a way to introduce like social mobility. So, you know, if the graph keeps on changing, then every time different people will be on the good cycle. So you will have to have this cycle. So someone will have to get rich, but if it's like different people every time, then maybe it's better.
Yeah, so so the model that we studied doesn't capture that, but I think that would be more natural to allow players to improve their products and have mobility.
So there is one more question I want to ask. That's Alan is asking, what causes the oscillation effects in the plots?
The oscillations? Or?
Yes, in the plots. So I think some of the plots that you showed, they had some oscillation factors.
They have oscillations. So I think maybe what causes it, like if we start, so like here, for example, I guess these are the fractions. So there are, yeah, these are big oscillations. I mean, eventually they converge to something and the oscillations get reduced. But I think it's the fact that, so everyone is updating at the same time. So it's a discrete time system and it's non-linear. So basically every player is updating its bidding strategy every day, and they're updating it simultaneously. So probably if you wanted to have something smoother, it might make sense like if there was a way to convert it to a continuous time system. Or another version could be where at each point in time, only one player, like you study it, like only one player is updating. So maybe that would mean like the granularity would be a little different, like you study it at hour by hour or something. And you would see exactly when a player is updating. They don't all update at the same time. Here we kind of think there are these steps, and in each step everyone is updating. So I think if either if they update one at a time, so one version is like every day you pick a random player, and that player updates its bidding strategy, and the other ones bid in the same way as they did the previous day, like they invest in the same fractions their money. Then I'm guessing that could have fewer oscillations.
Okay, thank you so much, Simina. I think for the sake of time, we have to stop here. If there are more questions, I'm sure people can find you and send you an email. So thank you. Let's do another round of applause.
Thank you.
Okay, so I'm ready to pass on the torch to Nick. I think Nick is here.
I'm here. I guess I'm taking over for the last session, so good to see everybody. I was asleep for part of this, so it sounds like it's been going well, at least what everybody tells me. So we're gonna start the fourth session, which is, there's no thematic breaking this time, but we're gonna start the fourth session. And the first up, I believe, is Scott Emmons, who's gonna talk about symmetry, equilibria, and robustness in common payoff games. Scott, are you here? I think I saw you. There you are. All right, and I will, in an effort to run a tight ship, I will do the thing that I do to my students, and I will play a 15-minute timer behind me. So when you're ready, go ahead and take it away, Scott.
Wonderful, happy to be here. So as Nick said, my name is Scott. I'm a PhD student at UC Berkeley's Center for Human Compatible Artificial Intelligence. Today I'll be talking to you about symmetry, equilibria, and robustness in common payoff games. By the end of this talk, you'll understand one mathematical theorem that gives insight into the basic structure of collaborative games. I would like to start by giving a simple hypothetical motivating example. So suppose we're the United States National Laboratories. We're interested in maximizing the scientific throughput of our nation. We're going to have the national laboratories share a centralized supercomputer for their jobs. Suppose that to use the centralized supercomputer, each individual lab has job scheduling software that they deploy locally. If any member of the lab wants to run software, they'll first send their code to the local job scheduler. This job scheduler will then decide whether the job should be forwarded to the large centralized supercomputer or whether it should be run locally. Now, think of this as a game where there's a single payoff to the National Science Foundation, just maximizing the throughput of national science. Suppose there are n players of this game, where each player is an individual job scheduling software run on one of the n national labs. So there are a few properties of this game. It has common payoff. We just want to maximize total scientific throughput. The game has symmetric strategies by construction. We're going to assume that each lab runs the same job scheduling software. They share code. Finally, this game has anonymity. From the perspective of the common payoff, the identities of these labs don't matter. All that matters is which jobs ultimately get run. Okay, so the one assumption we're going to make is that the job scheduler, whoever designed it, whether it was an AI system that designed it or a human that programmed it, has reached a local symmetric optimum. I haven't formally defined this, but you can think of it as whatever parameters there are for this job scheduling system, no slight improvement to the job scheduling system, which is deployed on in all the labs, could improve total throughput. Now, the system is running, the system is in deployment, but we would like science to progress even faster. So rather than updating rather than updating the job scheduler and deploying it in every lab at once, the National Science Foundation proposes an incremental approach. They decide to hire one supercomputing professional that's going to go into one lab and try to update that job scheduling policy however they would like in order to improve the common payoff, which is the shared output. So what we're going to do is we're going to aim for a type of best response algorithm where we just keep n-1 policies the same, and only the supercomputing expert will only first work on one lab system in order to test it out just before rolling it out globally. So the question, just to kind of probe people's intuition that I want to ask, is how much improvement to the common payoff should we expect from this procedure? Should updating one lab's policy lead to no improvement? Is it not possible at all? Or if it is possible to have improvement, what kind of scaling should we expect with this procedure? Should we expect sublinear scaling, where as there are more players, it becomes marginally harder to improve the common payoff? Should we expect linear scaling? Or should we expect superlinear scaling, where as there are more players, we think it'll be incrementally easier to improve the common payoff by just updating one policy? So I haven't formally defined all these terms, but I'd like everyone just to take a minute, take a guess, A, B, C, or D, if I didn't accidentally reveal it by skipping a slide earlier. And yeah, just please, I'll pause for maybe 10 seconds and please enter into the chat just your best guess, your first intuition here of how much improvement we're going to see is possible in a game like this. Okay, I'll give maybe 5 more seconds. It looks like so far we have a uniform distribution over the possible answers. So let's go ahead and get further into talk. It turns out that there is no improvement that's possible in this situation. And I'm going to go the rest of this talk into more detail on exactly why this is the case. So if we consider a more simple game, which is 2 children who can either do chores of laundry or washing up, we can suppose that the common payoff of this game is each child receiving a payoff of the common payoff is 1 for each chore that gets completed. So in this simple coordination game, the optimal asymmetric strategy with no constraints is for the children to coordinate to get each of the chores done. The green dots here in the plot show that the maximum payoff of 2 is achieved when the children coordinate like this. And suppose we have a constraint of symmetry, as we showed in the previous slide. In this game, what the constraint of symmetry does is requires us to only play strategies that are on the line y equals x in this plot. If we have this constraint, the best that the children can do is to flip a coin to decide which chore will get done. This would allow us to maximize the probability that both chores get done. However, note that this symmetric optimum of flipping a coin is not globally optimal. There's still a chance that the children overlap on which chore they do. So if we suppose that we're at this symmetric optimum, which we know is globally suboptimal, we can look at what the unilateral deviations from this strategy profile are, which are denoted by the blue lines here. And we note that even though these unilateral deviations can bring us closer to the global optima if we're just looking at strategy space, nonetheless, the payoff is constant. So if one child is flipping a coin to decide which chore to do, there's nothing that the other child can do to improve the chance of coordinating. And it turns out that this simple picture holds in higher dimensions and holds for arbitrary numbers of players if we have the right notion of symmetry. So in plain English, what one of the theorems of the paper shows is that any locally optimal symmetric collaboration is a global Nash equilibrium. This gives us a guarantee of a global property, even if we only have local optimality of a symmetric strategy. And a little more formally, if G is an imperfect information extensive form game in robotics, which is my field of expertise, we would call it a decentralized, partially observable Markov decision process. So in any game with common payoff, then a locally optimal P invariant strategy profile is a global Nash equilibrium. What P invariance means is it is a generalization of symmetry. So in the previous example, we had total symmetry among the players, but this is a group theoretic notion of symmetry that encompasses anonymous games, transitive games, and totally symmetric games as special cases. So whatever permutations we might have of the game symmetry of the players, P invariance captures that symmetry. And I don't have time, I decided not to focus on the details of P invariance in this talk, but the paper has more details. And it turns out that this result of requiring a symmetric, in the theorem above, I have some notion of symmetry that's required in my statement of the theorem, but it turns out that with a veil of ignorance construction, we don't need to assume anything about symmetry of the game to apply this theorem. So suppose we're going to play this matrix game here on the right behind a veil of ignorance. We don't know in advance if we'll be the row player or if we'll be the column player. This could be of interest to makers of public policy who have to write laws, not knowing which citizens will end up in which situations. It could also be of interest to computer scientists or AI developers who have to write algorithms without knowing exactly which artificial agents will be deployed in which situations in the environment. So in this case, a strategy of if we're the row player, play top, and if we're the column player, play left, is locally optimal. It's a local symmetric optimum. There's nothing that can be done locally. Any slight perturbation to the probabilities of this contingency plan here on the left will not lead to an improvement in the common payoff. Nevertheless, and we notice that this is globally suboptimal because we would really like to coordinate to reach 6. Nevertheless, the theorem guarantees that this is a Nash equilibrium. And I'm going to talk, so that's the main theorem, and that theorem is what gives us no improvement being possible in the motivating example with which I started out this talk. So to kind of conclude the talk, I'm going to spend a few minutes talking about why we might be interested in this sort of theorem. So first, this theorem assumed common payoffs. Why might we be interested in the common payoff assumption? One reason is assistance games, which is what the Center for Human Compatible AI focuses on, where we assume that robots and humans have the same payoff, even if the robot doesn't initially know what that payoff is. We might also be interested because of coordination in things such as self-driving cars, where we need to work together. Also, we have a common payoff for shared risks with existential threats such as climate change, or nuclear security, and as we know now all too well, pandemics. There are certain payoffs that there are ways in which we're all bound together. We also assume symmetric players in this work. I showed veil of ignorance construction is a way to make any game have a symmetric structure. And there are also games such as designing standard hardware or having online activity, or by construction having anonymous protocols where the actions of the agents matter, but the identities of the individual agents don't matter. And that condition of identities not matter is anonymity. And there are also more general asymmetry structures. If any sort of group theoretic symmetry that you want to consider is captured by P invariance. But finally, why might we be interested in symmetric strategies? A first example is source code, as I opened this example with. If we have the same code running on different machines, they're going to, by construction, play the same strategy. In multi-agent reinforcement learning, it's a common technique to share weights among the players. So if one example that people consider multi-agent reinforcement learning is something like a StarCraft game, where each of the individual agents in StarCraft will be running the same neural network. And again, by construction, they have to be playing the same strategy. More broadly, we can consider symmetric strategies for the purposes of optimization. If we think about a game with A actions and N players, then the number of pure strategies is going to be exponential in the number of players. But by doing an optimization with shared strategies, we can get away from this exponentially large state space. A few implications of this result are that it provides a sort of stability to unilateral deviation. This comes from the definition of a Nash equilibrium. However, in a further follow-up in the paper, we see that there's still possible instability to joint deviation. So even if we're at a local symmetric optimum that we know by the theorem is a Nash equilibrium, if multiple agents choose to deviate, so if multiple national labs were to update their job scheduler in the motivating example, we could still improve the common payoff that way. And an implication of this result for people who are doing optimization or multi-agent reinforcement learning is that iterated best response can't improve from a local symmetric optimum. In a more human-centric game, we see that individuals cannot innovate if we're at a local symmetric optimum, because no matter what an individual does, the common payoff will remain the same. I've only talked about one of the results in the paper. There are other additional questions that the paper explores. So is the theorem robust to perturbations? The answer is, for certain types of perturbations, yes, and we formally show how perturbations in the game affect the theorem. It turns out to go from a Nash equilibrium to an epsilon Nash equilibrium. When are symmetric optima also optima in possibly asymmetric strategy space? The theorem shows that under some regularity assumptions on the game, this holds if and only if the strategy is deterministic. We also show experimental results on how frequent the stability and instability is when we solve for symmetric optima in gamut games. And finally, we consider the complexity, the computational complexity of computing the symmetries of the game. So this work was not done by myself. So I would like to thank the collaborators listed here, as well as some funding sources for this talk. Thank you very much. And I'll answer a quick question. It seems I have 1 minute left. There's a question, or if the host would like to take over.
No, go ahead. I guess quickly, let's give Scott a hand real quick, and then Scott, you can answer, I think, the one question that's in the chat. So thank you very much, Scott. But yeah, go ahead. So Reshef asked, is the notion of symmetry depend on actions labels? It seems that payoffs are not symmetric.
Yes. So in this work, we assume that the actions do have labels. That was from the computer science. I was originally thinking from a robotics and computer science perspective, where we would have some global notion of what an action means if we're programming a robot. In the paper, we mentioned that you can consider, we are considered only permutations on the player indices. You could consider also permutations on the action labels. I believe that all this would do is just add some notational complexity where you have to keep track of the mapping on action labels throughout the statement of the theorem, but I don't think it should change any of the fundamental results. So I believe you could have the same results with respect to any permutation on the action labels.
All right, sounds good. Let's give the speaker a hand one more time. Thank you very much, Scott.
Thank you.
And then we're gonna roll right along, who we just saw a picture of, Casper or Vince. I'm guessing it's probably Casper because I see him in here.
Yeah,
so Casper is going to give a talk on decision scoring rules, and you've got about 13 minutes for talk, 15 minutes total. So looking forward to it. Thanks, Casper.
Great. So I hope you can all hear me. Yes. Okay. Good. Okay. So
we
yeah,
can hear you. We can't see your screen.
Oh. Okay. Yeah. Sorry.
No worries. All right. There we go.
Okay. Perfect. Yeah, so I'm Casper Osterheld, and this is joint work with my PhD advisor, Vince Kornitzer. And so here's the setup that we're considering in this paper. So we imagine that there's some principal who faces a choice from some set of actions, and actions give rise to outcomes, and the principal wants to maximize the expectation of some utility function over outcomes. And there's also an expert, and the expert actually has probabilistic beliefs about what outcomes different actions will give rise to in the usual way. And now the principal wants to take the action that is best according to her utility function and the expert's probabilistic beliefs. And to do that, we consider the following type of mechanism to get the expert to reveal some of her information. So first, the expert submits a recommendation for an action to take and a probabilistic distribution about what will happen if the recommendation is taken. Then the principal indeed always takes this recommended actions. Then some outcome is materialized, which the principal can observe. And finally, the principal pays the expert according to what we call a decision scoring rule. And this setup is inspired by the literature on proper scoring rules for eliciting predictions, which probably a lot of you have seen. So what we're interested in are decision scoring rules that set good incentives on the expert. And we call these decision scoring rules proper, in line with the literature on proper scoring rules for prediction. And so what do we mean by that? Well, basically, we assume that the expert always wants to maximize his expected score. So it's this term. It wants to give some report that maximizes his expected score. And a report consisting of a recommendation and a prediction. And for a decision scoring rule to be proper, it must be the case that regardless of what their probabilistic beliefs are, there is always like among the expected score maximizing reports, there's always one that consists of an action that is actually optimal for the principal, and the sort of correct prediction about what outcomes this action will give rise to. And of course, this is satisfied even by, for example, the constant scoring rule. So we might additionally want some strict propriety property. So I'll illustrate this on the next slide using what is perhaps the simplest kind of interesting decision scoring rule, or proper decision scoring rule. So here, basically, the principal just gives rewards the expert in proportion to the utility that is obtained after following the expert's recommendation. So you could imagine that the principal is has, for example, a company, and the utility is the value of the company. Then one very simple thing that the company could do is give the expert 3% of the company, for example. So this decision scoring rule is proper, and it is strictly proper with regard to the recommendation. So if the expert wants to maximize his expected score, he wants to maximize the principal's expected utility, which he does by giving the best possible recommendation. So that's what we mean by strictly proper with regard to recommendation. But it's not strictly proper with regard to anything else. So you can see that in the score, this prediction is completely ignored. Like this term's probabilistic prediction, P hat, A hat doesn't occur here. So obviously the expert will be indifferent between what prediction to make. Okay, so now the question is, can we set some kind of incentives on the predictions as well? And I'll start with a positive answer to this question by describing scoring rules that can elicit estimates of the expected utility of the principal. And this is a very, very simple and intuitive idea. And I'll sort of describe the intuitive idea first and then give an example of how it works as a scoring rule. So let's first imagine that we just have some number, and let's say that that number is positive. And basically, we just want the expert to tell us whether he thinks that our expected utility is greater than mu. Then one very simple thing that we can do is we offer them at a price of mu dollars, a share in our project, which pays $1 per unit of your utility obtained. And the idea is that when figuring out whether to accept this offer, the expert will basically evaluate the expected utility of the project, and the expert will buy the share if the principal's expected utility is greater than mu, and they'll be indifferent if it's exactly mu, and they'll prefer not to buy it if it's less than mu. And importantly, making this offer doesn't mess with their incentives in any problematic way. So if they accept the offer, then they still want, for example, they want even more to give us an honest recommendation. Okay, and we can get more fine-grained information about what our expected utility is by offering this type of share at different prices. So for example, we could first offer a share at 10 cents, then at 15 cents, then at 20 cents, and then we can sort of see when the principal first rejects this offer. And then from that, we can infer some range within which our expected utility must be, or the principal's expected utility must be. And you can sort of imagine that you can make this of infinitely fine-grained and offer infinitesimal shares at infinitesimal prices, and thereby get exact estimates. But now, how would we implement this as a decision scoring rule? So again, we assume that we kind of know that the expected utility of the principal is positive. Makes this slightly simpler to give an example. And so we'll define the scoring rule, but we'll define it as a function of only the predicted expected utility rather than the entire probability distribution, and only the utility that is then in fact obtained. And now the idea is that by submitting this expected utility estimate, the expert kind of consents to buying all shares, like to accept all of these offers described earlier, up to a price of mu hat per share. And one sort of concrete example of this is this kind of integral expression. So this integral is over, we can think of it as an integral over prices. So for all prices from 0 to mu hat, the expert gets a share in the project. So that's this y, and pays that price. And of course, it's sort of clear that you want, in this case, the expert would want to report mu hat, the expected utility, honestly, because they want to stop buying these shares exactly when the price is equal to the true value. And of course, we can give a closed form expression of this, but I kind of like this integral expression because it represents this intuitive mechanism. Okay, so that was the good news. Now comes the bad news. Unfortunately, we cannot strictly incentivize the expert to reveal anything else. And in particular, like the problem is that if we set strict incentive on any other aspect of the prediction, then it will give them incentives to give suboptimal recommendations. And so very roughly speaking, so obviously give this result in like formal detail in the paper. So proper decision scoring rules cannot punish an expert for misreporting this probabilistic recommendation, as long as the misreported distribution still has the correct expected utility. And then also one can also show that if and this has a couple of more caveats and sort of there's some degenerate cases where you it can actually depend on that, but that's sort of the gist. And then another thing is that if two outcomes have the same utility, they also get the same score. So actually this notation that I used on the previous slide, where decision scoring rules only take as input the reported expected utility and the true utility obtained. Basically, we can adopt this for the rest of this talk, and we adopt this for the paper because you can't set strict incentives on the other stuff. Okay, now the main result of the paper is a characterization of proper decision scoring rules. And in fact, there are many different, obviously equivalent characterizations. Here's perhaps the mathematically simplest. So you can see it's not a very complex term, and some of you might also recognize this from other work where very similar characterizations occur. So for example, there's a characterization of proper scoring rules for prediction that looks very similar, but I don't really want to talk about this formula much. And rather, I would want to talk about how we can interpret these characterizations. And I think this is sort of the main thing, like the one thing to take away, I guess, from this talk, which is that all proper decision scoring rules can be interpreted as selling shares in the principal's project at different prices. So this kind of example mechanism where you offer shares at 10 cents, 20 cents, and so on, that I described like 3 slides ago, actually all proper decision scoring rules can be interpreted as instances of that. Okay, now I want to very briefly venture into the realm of the somewhat speculative. So I mentioned that that one big inspiration for this work is the literature on proper scoring rules, and in particular characterizations of proper scoring rules. But another inspiration for us, or another thing that we were really interested in, are these prediction markets, or also just call them betting markets, which are sort of very realistic mechanism for eliciting predictions from multiple experts. And basically, we wanted to kind of get the same things for the recommendation case. So these are all for things where you only want experts to give you predictions about some event that you can't influence. And now we want to also get information from experts that tells us how to make a particular decision. And for the single expert case, I think proper decision scoring rules are really the sort of very natural analog of proper scoring rules for prediction. And I'm very happy with the result that we have on those. But now the question is there some analog of prediction markets for the case of making recommendations? And a lot of previous papers have asked these questions as well and have come up with various answers, which have various issues that I don't have the time to really discuss. I mean, some of them are well, they're definitely interesting anyway. But what I think this paper points to is that you kind of have this idea that you have to sell shares. And now in the multi-expert case, a natural thing, it seems, would be to auction off shares, perhaps iteratively, perhaps let experts sell shares to other experts, and so on. And then in the end, let people who have shares vote on what the principal should do. And I'm kind of wonder, I mean, that's not a very technical question, it's a very vague question. Like, is that a natural, realistic, useful mechanism? And I don't really know, but I'm interested to think about this more. Okay, thank you for your attention, and I look forward to questions if we have time.
All right, let's thank Casper. Thanks, Casper. We got time for one quick question if anybody's got one.
So I can't see the chat, by the way.
So nobody has put one in the chat. I can ask a quick question. So have you all built this up into some kind of deployable system yet, or is it still just sort of at the theory phase, like for the purposes of the project?
It's all at the theory phase, yeah. I mean, okay. the paper is mostly about these characterization results, and like this last part is like something I've been thinking about.
Right. I mean, that seems like where you're going to go. You know, what you're kind of shooting at. So
yeah.
But
it is something that I'm thinking about implementing. But I mean, there are many obstacles. Like you'd have to actually get people who are willing. Like it would be somewhat similar to something like predicted, but you would have to get people to actually make predictions, and using real money is probably problematic for legal reasons. So
yeah, you can figure it out. All right. Well, let's thank Casper one more time. Looks like we are running about 20 minutes behind schedule at the moment. So right now we're scheduled for a 10-minute break. So we're going to come back at 1/2 depending on your particular time zone, unless you're in Adelaide, which I don't think Mark is. So nobody's on a 1/2 time zone. And so we'll see y'all back here at 9:30 my time, or in 10 minutes. And we'll come back with Hadi, are you talking, or Fatima, or Rohit?
Fatima is talking.
All right, so we'll come back, and Fatima will be talking with us about accomplice manipulation of the deferred acceptance algorithm. Oh, Lev, thank you. Newfoundland too has a 1/2 time zone. I forgot. There's a couple 1/2 time zones. I think there's a part of Alaska that might be on a 1/2 time zone as well, or maybe the one side of Canada.
Newfoundland is one side of Canada.
Right. I thought there was one on the other side of Canada, on the west side.
I was just going to say the same thing.
I know it's part of Canada.
Come on. We took it back.
Hang on. I'm not going to get beat up on by the Canadians around here. This is not.
Can you guys put us in breakout rooms again? That was kind of nice to get to meet people that we wouldn't.
Yeah, all right. So I'll throw everybody in the breakout rooms. Let's do this randomly.
Or should I?
You can do it. I think you were doing it before. If you were doing it before.
Yeah, I will. Okay.
Okay.
They should be open.
Oh, and then Mark pointed out that the New Zealand islands have a 45-minute.
Oh, really? They're 45 one? Nice.
Yeah.
You're supposed to know everything, you know, Antipodean
Yeah. All right. I'm not going to go to my breakout room. I am going to step away to the restroom.
By the way, I think this is the first break not before keynote we just completely ran out of time.
Yeah.
Ran over all the breaks.
Oh, okay. I didn't know.
We would be 1 hour. We would be 1 hour late otherwise.
Yeah. Sorry, I didn't know if we might. I mean, I guess we could run through the next break, and then we probably actually end somewhere in the ballpark of on time.
But it's not too bad because this is the last session. Even if you go like 20 minutes or 30 minutes over, I think it's still manageable.
I might have to jump at 11 my time because I have office hours. We should be done by then, but we're.
Is it your semester, Nick?
Yeah, but their final project is due tonight at midnight because today's the last day of classes, and I'm sure that I'm going to get yelled at vociferously for.
Okay, if you want to feel better, my students are currently taking a final exam online, and I messed up somehow. The timing was wrong, so I just got flooded with emails and texts and messages. That wasn't it supposed to be 2 hours? Why do we see 30 minutes only? Like
Aren't you supposed to be online for that? We are obliged to be online. Like
I don't do that. No, I don't. I decided not to do that.
University protocol. It's not our choice. We have to be online and available for their exam. At least one faculty member.
No, I am online right now. I'm in 2 Zoom sessions. I'm online and available, and I'm chatting with them. Apparently, you can be in 2 Zooms at the same time.
I did not know that.
And my TA is also in that room, so she's handling some of the questions when I'm not. Yeah, but the funny thing is that I have like 2 of my students are also giving talk right now, so I have to be here as well.
You have 4 sessions you're in. This one, the exam, and the 2 talks they're in.
Exactly. No, the talks are happening here, so that's good.
Okay.
Yeah. I think it went well so far. It's been going well.
I'll have to away in 35 minutes for a different call, but I don't know if this will still be on when I return, but hopefully so.
What time is it for you, Omer? I mean, you started this and you've been here.
So it started for me at 9 a.m. and this is now 5:30 p.m.
Oh my God.
And yes, been churning through. And I went to bed like at 3:30 a.m., which was not the right thing to do when you need to wake up for definitely not the right choice.
You're a true AAMAS games and agents player.
I may not attend any other part of AAMAS, even though I have co-authors who are presenting, but I actually have work I need to do this week. It's for us, this isn't the end of the semester. We're like, this is week 9 of the semester. We still have about a month left to go. Yeah. I'm guessing that's not your actual apartment, Hadi, because I think I saw that picture elsewhere.
Yeah. I hope I was this tidy.
Yeah. You are at Pennsylvania. You're in Pennsylvania right now. You're not like, I don't know, in Canada.
No, I'm still in New York. Still in New York. Yeah, everything is remote. So yeah, it's not far. So yeah, I'm still in New York.
Are you planning on moving, or you're planning on staying?
No, so I'll be driving back and forth.
Oh, I see.
Yeah, so I'll probably be driving back and forth for next year. I just wing it for now.
Wait,
yeah.
Philadelphia, right? Or
sorry, I cannot hear you.
Sorry, you're in Philadelphia, right?
Me?
Yeah, the university.
No, Penn State.
Right, but physically is it?
No, it's not. No, that's UPenn. So Penn State is in State College. It's a very tiny college town.
I see.
Yep. Hey, Omer, can you ask Fatima to come back and set up? I think she's giving a slide. She set up her slides. I think she's giving a talk next, right?
I don't think I can talk to her.
We cannot pull her out of the.
No, wait. Yes, I can pull
from the breakout rooms, right? So to set up.
Should I pull her without warning? She's in that room alone with Casper, so they're probably.
Oh yeah, that's not good. That's not nice. Okay, no, don't do it. Yeah, if there are only two of them alone, you don't want to pull her out. Yeah, that doesn't seem very friendly.
Collegial, yeah.
Yeah.
Wait, sorry, I'm now eavesdropping on your conversation, I feel, but I think you can join the breakout room and ask her to come back. Maybe that's a bit more polite.
Should I assign you, Hadi, to her room?
Okay, let me just go myself. I think I can do it. So join.
Okay, she's in room
Yeah.
2.
Yeah.
Yeah. Alan, it's lovely that you're out in the snow. Is that supposed to be snow?
Oh yeah, I still have this canned background from the winter. I just never bothered changing it. I should change it to something more festive.
It was 30 degrees here today, so definitely not snowing.
That's warm, yeah. No, it's like 12 degrees, 15. I don't know. I don't go outside anymore. Outside's dangerous.
Since October.
It's
Okay,
7 degrees apparently.
I asked Fatima to come back. I think she would be back.
Okay.
Is she here yet?
I don't think I can see.
Yes, she's here.
Sorry, should I share my screen then?
I think you have the authority. You can share it as far as I can know.
Okay.
And I think we're waiting for Nick to be back, and then we'll bring folks back, right? What time did he say?
I've passed.
Oh, here he is.
You've summoned him.
Yeah, he was waiting outside for me to mention his name. Nick, what hour did you say? When should we call them back?
At the half hour, so nowish.
I'll write them in 1 minute. Okay, rooms should be closing in 15 seconds.
Do you use the rooms a lot? I mean, when you're teaching, I find some resistance to it, but maybe I just didn't stick with it long enough to like really.
I could not. It's completely. I only used it in seminars, like in the Comstock seminars, the only experience of this. In teaching, I just can't see the use. Usually, because I'm teaching more for mathematical subjects. What are they going to discuss? Like,
yeah, fair enough.
Maybe if they give an exercise, they can try to solve it together. But usually, I just teach.
Sounds good. All right, looks like we're getting everybody back in from the rooms.
They should all be back by now, according to what it's telling me. In the...
All right, so it looks like everybody's back. So welcome back to the second half of the session. So next up, we've got Fatima, who's going to talk about accomplice manipulation of the deferred acceptance algorithm. So take it away, Fatima. Thanks.
So hi everyone, today I will be presenting our research on accomplice manipulation of the deferred acceptance algorithm. This is joint work with my advisor, Hadi Husseini and Rohit Beish. So our work deals with the stable matching problem, and I'll begin by defining that. So suppose we have a two-sided market that is made up of workers and firms, and say that they each have preferences. So each worker has preferences over the firms, and each firm has preferences over the workers. Now, given the setting, the natural question that arises is how do we find a perfect matching between the two groups? So before answering that, I'll define a few terms. We say that a pair consisting of a worker and a firm who prefer each other over their assigned match is a blocking pair. In this matching here, we see that worker A prefers Microsoft over its assigned match Google, and Microsoft prefers worker A over its assigned match worker C. So A and Microsoft would be a blocking pair. So why is this a problem? Well, worker A and Microsoft can elope by leaving their assigned matches to match with each other instead. So any blocking pairs in a market of this type would cause the matching to sort of unravel, which is clearly not desirable. And so our goal then is to find stable matchings, which by definition do not contain any blocking pairs. And so how do we find stable matchings? Well, the deferred acceptance algorithm, or DA algorithm for short, was introduced by Gale and Shapley in 1962, and it's guaranteed to find a stable solution to any instance of a stable matching problem in polynomial time. So as a quick kind of high-level overview, the algorithm uses a proposal reduction structure. So it starts off with one side, and in our case, we'll assume the worker is proposing to the other. And then, so after the workers propose, the firms will respond by accepting their favorite proposers and rejecting the others. The process continues until everyone eventually is matched, and then the algorithm terminates. So moving on to some real-world applications of stable matchings. One application is school choice, where students are matched to schools in their local area. Another application is the National Residency Matching Program in the US, which uses a variant of the DA algorithm to match potential resident doctors to hospitals. And similar matching algorithms are also used to match potential donors and recipients for kidney exchange. So unfortunately, it was shown by Roth in 1982 that there is no two-sided stable matching mechanism that is strategy-proof for all agents. And actually before that, Dubbins and Friedman showed that the DA algorithm is not strategy-proof for the side being proposed to, which in our case is the firms. So let's consider a quick example where Google is looking to improve its match. So on the right, we see the original instance of the problem. And we can see that Google is currently matched to worker C, its third choice. But if Google were to submit preference list CABD in place of ABCD, then it would match with worker B instead of worker C. And according to Google's actual preferences, B is ranked higher than C. So Google is strictly better off. And we call this type of strategic behavior where firms misreport by permuting their preferences self-manipulation. So this isn't just a worst case phenomenon. We generated preference profiles uniformly at random for different numbers of workers and firms. And the plot here shows the fraction of instances for which some fixed firm is able to strictly improve through self-manipulation. The numbers are clearly non-trivial, but they're still pretty low. So what other options does a firm have if self-manipulation doesn't work out? In our work, we study a new model of strategic behavior called accomplice manipulation that was introduced by Benlin and Husseini in a previous paper. So let's consider the same example that we've been using. We again assume that Google is the strategic firm, but instead of Google submitting a misreported list itself, it asks worker D to misreport on its behalf. So worker D submits the list over here instead of the true preference list. And so the resulting outcome matches Google with its top choice, worker A. And notice that worker D is still matched with Apple, who was matched with under the true preference profile. So comparing this to self-manipulation, we can see that Google is strictly better off under the accomplice manipulated instance, right? Because Google prefers worker A over worker B, who is matched with one self-manipulating. So now to more formally state our model, under accomplice manipulation, a strategic firm teams up with a worker who we refer to as an accomplice to manipulate the DA outcome on its behalf. So the accomplice misreports, but the strategic firm remains truthful. And so there are two cases that we consider. One is the no regret case, under which the accomplice retains their original DA outcome. And then the other is the with regret case, under which the strategic firm convinces the accomplice to match with someone they less prefer, perhaps through some side payments. In this talk, I'll focus only on the no regret case, The with regret case is considerably more involved, but you can read more about it in our paper. So looking back on our previous experiment, we now show that the fraction of instances, for which a fixed firm is able to improve through accomplice manipulation compared to the fraction of instances where it's able to improve for self. So the fractions for accomplice are nearly double the fractions for self. And that was comparing the strategies against truth telling, but if we compare the strategies against each other, the results are actually even more compelling. The plot here suggests that accomplice manipulation is not only more frequent, but it's also almost always a more preferable choice. So similar model stars have been studied before. When the college optimal mechanism is used, Belinsky and Sonmez showed that the students may have an incentive to perform worse on tests or make themselves appear less preferable. Similarly, if the student optimal mechanism is used, Hatfield et al. Showed that schools may deliberately make themselves look less attractive to students they don't want. And so in both cases, the proposed two side is indirectly altering the preferences of agents on the proposing side, which is similar to our model. So there are a few natural questions that we would like to answer. One is, how do we compute an optimal accomplice manipulation strategy? And then the other is, how does that strategy affect stability? So we'll focus on the first one to start. Looking back at our example again, we see that the misreported list of worker D can be created just by moving Microsoft above the DA match Apple. So using that quick little animation, we can more clearly see that that one operation was sufficient. And we refer to this type of manipulation as inconspicuous. So more formally, an inconspicuous manipulation is one that can be achieved by promoting exactly one woman in the accomplice's true preference list. And so the main result of our paper says that if there is an optimal no-regret accomplice manipulation, then there must also be an optimal inconspicuous no-regret accomplice manipulation. And then this immediately implies a polynomial time algorithm for computing optimal no-regret strategies. All you have to do is try promoting each woman in the accomplice's list and then return the strategy that's best. So let's run through a quick proof sketch of our main theorem. So any manipulated list can be achieved through a combination of shuffling, pushing up, and pushing down. I'll define these operations as I go along. So let's first take a look at shuffling. So in this arbitrary list here, suppose the accomplice is matched with Twitter. Then what we can do is permute the part of the list to the left of Twitter in any order, and then also permute the part of the list to the right. And so from result 2 to Huang, this has no effect on the final matching. So this means that we can rule out shuffling as a needed operation. Now let's look at push up and push down operations. So with push up operations, what we're doing is we're moving a firm or even a set of firms that are to the right of the DA match above it. And then push down operations is the reverse. So here we're moving a set of firms above the DA match below it. And so in our paper, we show that any manipulation that uses a combination of push up and push down operations can actually be weakly improved by just pushing up instead. So that rules out pushing down as a needed operation. So now we're only left with push up operations, but we still can't infer the inconspicuous property yet because we may have a situation where we're pushing up multiple firms. So here we're pushing up Apple and Amazon. And so another result in our paper shows that pushing up a set of firms is actually strategically equivalent to pushing up a single firm. So instead of pushing up both Apple and Amazon, we can, in this case here, we can just push up Apple. So essentially, we've just shown that pushing up a single firm is enough to create an optimal no-regret strategy, which by definition means that it's inconspicuous, and thus we've completed our proof. Great, so now that we've shown how to compute an optimal misreport, let's take a look at what this means for stability. So the second key result from our paper says that the set of all stable matchings with respect to the manipulated preference profile of a no regret accomplice strategy is contained within the stable set of the true preference profile. So from a result due to Conway, it is known that the set of all stable matchings of an instance form a lattice. And so our result implies that the manipulated lattice is contained within the true lattice. And because we know that the DA algorithm returns a stable matching, we have that the DA outcome from an inconspicuous manipulation is stable with respect to the true preference profile. So now that we've answered all our theoretical questions, let's end with sort of an experiment. This uses a similar setup to the previous ones I described, where we're using uniform preferences. So here we additionally show that the expected improvement from an optimal accomplice manipulation strategy, assuming one exists, is greater than the expected improvement from an optimal self-manipulation strategy, again, assuming one exists. So just to quickly summarize our results, we have shown that an optimal no regret accomplice strategy can be computed in polynomial time, that an inconspicuous no regret accomplice strategy is stability preserving with respect to true preferences, and that experimentally using uniform preferences, no regret accomplice outperforms self-manipulation. So for future work, there are several few interesting directions that can be taken. In particular, one could consider a model where the strategic firm and an accomplice misreport, or perhaps one in which there are multiple firms or multiple accomplices willing to help a firm. Additionally, game theoretic properties of the accomplice manipulation game could be considered. And of course, it would be interesting to also see how the results would carry over to more general matching models. So that's it for me. Thank you all for listening, and I'd be happy to take any questions if there are any.
All right, let's thank Fatima. All right, does anybody have any questions for Fatima? You can either type them into the chat or raise your hand or just jump in. I think we're small enough to make that work. All right, I have a quick question. So do you have any, in the coalition manipulation model, it seemed, I was just kind of trying to think it through, like, because you had these three actions that you defined for the single, but it seems like you're gonna have to come up with a new set of those for coalitional, or am I thinking about that wrong? Because it seems like, you know, you could do the combinations of maybe the two, because you would give you slightly different results, but maybe I'm just not thinking about it right. Or maybe I'm just thinking too far ahead.
Yeah, no, of course. So shuffling, where we're permuting like the left and right sublists, that was shown to not have any effect. So, I mean, even if all the accomplices were to do that, that would have no effect. But pushing up and pushing down, it's not as intuitive. So you may need like actually a combination of push up and push down operations. So some firms may be pushing down, some may be pushing up. Yeah.
It seems like your decision space is, your decision space in the coalitional one is it's just gonna explode. But it's kind of cool. It's a neat idea. So I really like it. Errol, do you have a quick question?
Yeah. So are there any implications from your work to the selection of whether, for example, in school choice, in matching problems, which side should be the side that offers? Which side that, based on the possible manipulations?
Sorry, what was the last part? I didn't get that.
So the question is, based on your work, which side is more prone to manipulation?
So we showed that that the men have more of kind of an influence, or sorry, the workers. So the side proposing, they have more of an influence than the side that's being proposed to. And so you could kind of see that with our experimental results, where accomplice manipulation is more frequent and also has more of an effect on the improvement.
So it's opposite to the standard theorem that says that the mechanism is truthful for the proposing side. You say that the proposing side can manipulate more.
Manipulate more for like on behalf of the proposing side, because I mean the DA algorithm was shown to be strategy proof. So for the proposing side, so they can't improve themselves, but they may be able to help the proposing side.
And you say that this effect is stronger in the proposing side.
What was that?
So this effect is stronger in the truthful side, in the proposing side.
Right. Yeah. So the proposing side has more of an influence, sort of, on the side being proposed to.
Okay.
All right. Great. Thanks for the question, Errol, and thank you, Fatima, for a great talk.
Yep. Thank you.
Thank Fatima one more time. Woo. It's always weird to just clap by like one person. I guess everybody has adjustment. That's good. So next up, I think we have Zun Lee or Michael Wellman. Zun's here. There you are. All right. So Zun's going to talk to us about evolution strategies for approximate solution of Bayesian games. And take it away.
Yes, thanks. Hi everyone. I'm Zun Lee. I'm a third-year PhD at University of Michigan, and today I'm going to present my work, Evolution Strategies for Approximate Solution of Bayesian Games. This is a joint work with my advisor, Professor Michael Wellman. So here is one slide summary of our results. So the goal of this paper is to compute Bayesian Nash equilibria for Bayesian games, characterized by many symmetric players, high-dimensional types, actions, and only black box access to type distribution and pair of values. But we do not need to know the analytical form of these terms. And our approach is that we will represent each pure strategy as a neural network and exploit evolutionary computation and game symmetry structure to design algorithms for computing both pure equilibria and mixed equilibria. For computing pure equilibria, we will solve a minimax optimization problem. And for computing mixed equilibria, we'll adopt something called incremental strategy generation framework to implement the algorithm. So next, let me just recap the standard notion of Bayesian games. So in Bayesian games, I think the most important feature is that a pure strategy is actually a function mapping from types to actions. And here types are just defined as agent private information of the game, such as in a multi-object auction, types is just a vector defining one's valuation for sets of goods, and actions are just bits for these goods. And types are IID sampled before the game starts from some common knowledge distribution. So in this paper, we will particularly consider Bayesian games with some payoff structure. First, we'll assume that one's payoff function is only a function of agent's joint action and its own type information, but it is independent of other agents' type information. And typically, the payoff will structure in some form. For example, in an auction, it is a quasi-linear form such that the payoff is always the valuation minus the payment. And furthermore, we will consider Bayesian games with symmetry structure. First, we'll assume that the payoff is always permutation invariance with regards to other players' actions. For example, in an auction, your payoff, you only consider the highest opponent's bid instead of their respective identity bits. And we will also assume that the functional form of the utility are the same for all the agents. So in a Bayesian games, a pure strategy is a deterministic mapping from types to actions, and a mixed strategy is just a probability measure over a set of such pure strategies. So in this work, we will consider Bayesian games where both types and actions can be represented by real vectors, such that we can just represent each pure strategy as a neural network. So the solution concept of Bayesian games is just the so-called Bayesian Nash equilibrium. And we particularly seek the so-called symmetric equilibrium, which basically means that in such a profile, everyone will adopt the same strategies. And we usually have such symmetric equilibria existed for symmetric games. And to compute symmetric equilibria, it is usually beneficial to have this quantity, which is so-called deviation payoff, as I wrote here, the function u sigma prime, sigma void, which is defined as the expected payoff when one play a particular strategy sigma prime, while all the rest n-1 opponents adopt the same strategy sigma, marginalized over all the joint type realization. So by having this quantity deviation payoff, we can actually quantify the robustness of one strategy sigma by defining its unilateral maximum deviation to the pure strategy space, which I wrote here as the game theoretical regret function regret. So the goal of this work is just to develop algorithm that can minimize this loss function regret. So this is the basic setup for our problem. So next I will just dive into the methodology part. So at the core of our algorithm design is the so-called natural evolution strategies method, which is a recently popular black box optimization technique. So the goal of NES is to optimize a black box function f with regard to its parameters or the neural network with theta in our scenario. And we only have a black box point query to this function instead of first order information. So the goal of the approach is that in NES, instead of directly optimizing f, we will actually optimizing a Gaussian smooth version of f, which is actually to perturb each function value at that point by some Gaussian noise, as I wrote here in this formula. And then we will just can sample a bunch of data points and construct finite difference approximation of the gradients and do the gradient ascent on the parameter space. So that is the basic spirit of NES. So here is a visualization of to illustrate how NES work. So suppose now we are going to optimize a function over a 2D landscape. And starting from somewhere in the landscape, in each iteration of NES, it will sample a bunch of data points surrounding the current one from some normal distribution and query the function values on those points. And with those points, NES will construct a gradient direction in the landscape and do one step of gradient ascent. So just by iteratively querying the function values and doing the gradient ascent approach, it may finally reach some optimal points in the landscape. So that is basically how NES works. So by equipping NES as a strong optimization procedure, let me now introduce how we can compute symmetric pure Bayesian Nash equilibria in a symmetric Bayesian games. So let's just recall that compute PBNE is actually to minimize the regret function over the pure strategy space. The optimization problem can actually be formulated in a minimax optimization problem, as I wrote here. So now it is very straightforward, which we just to designate one different NES process to the minimization process and the maximization process, which I just call the regret minimization NES and the best response NES. So the way it works is as follows. So first, let's start with some strategy points, say S1 in the function space. In the first iteration, the outer loop Rn NES will call multiple times on those strategy points that is surrounding the current strategy point S1. And the inner loop fast response NES, using some simulation data, it will compute the fast response strategy against these strategy points and return the regret values back to the outer loop RNNES. So in the outer loop RNNES, using this information, it will construct gradient direction into in the pure strategy space. So by So using this interaction between the outer loop NES and the inner loop NES, the RMNES may finally reach a point such that by definition, it is a pure Bayesian Nash equilibria in the pure strategy space. So, so that is our algorithm for computing pure Nash equilibria, and we call it minimax NES algorithm. So just to for sanity check, we just test this algorithm on those simple games with non-analytical solutions, which we particularly consider the famous n-player single item, first prize, second prize, and third prize auction. And it is well known that for uniform distribution, uniform type distribution, the equilibrium function is for these games is always a linear function with regard to the input valuation. And there is some kind of ranking relation among these auction formats, such that for a fixed input valuation, the equilibrium bid for the first prize is always smaller than the second prize, and is always smaller than the third prize. And our results show that by combining deep learning and the evolutionary computation, our minimax NES perfectly recovered those analytical solutions in these simple games. And one thing we didn't mention in the paper is that, so just recall our previous, the previous algorithm that I just described is some kind of nested loop algorithm, which we need to have a double loop diagram to operate the algorithm. But we also test like the alternating gradient ascent descent training approach to formulate the algorithm. And I also believe it is how people today are training GAIW, for example. And we also observed that for this alternating gradient ascent descent training approach, the minimax NES algorithm also recovered this analytical solution in these simple games. So that was the part for computing pure equilibria. So next, let me introduce how we compute mixed equilibria. So just as we may encounter in many application scenarios in game theory, finding a good pure equilibrium may be very hard. And I think that is one of the reasons why it motivates people to seek for mixed equilibria. But the problem here is that since here we are consider a space of function from real vector to real vectors, or a space of a neural network, it is an infinite strategy space, which could be intractable to compute a mixed equilibria. So our approach is that we will just discretize the whole infinite strategy space into a finite strategy set and compute a finite mixture on this finite strategy set and use it as a mixed equilibrium notion. So the way we achieve this is to adopt a framework called incremental strategy generation. And as I will explain later, in ISG framework, we need two components to achieve the purpose, which is a meta solver and a best response oracle. So how does ISG work? So ISG is an iterative algorithm. And given an iteration, we have a finite strategy set S. And given such a finite strategy set S, the meta solver component will output a probability mixture over this set S. And here are some choices for this meta solver. The first choice could be self-play, which is just to put all the probability mass on the strategy that was produced by the last iteration. And we also call this self-play meta solver the iterative best response approach. And the second choice of meta solver could be what we call it fictitious play, which is just to put a uniform mixture on the finite strategy set S. And the most interesting one meta solver is that each time we compute a Nash equilibrium on the finite game defined by the strategy set S. And this type of meta solver also kind of resemble the famous double oracle algorithm. So after we say compute a mixture over the current finance strategy set S, in the next step, we will just use NES to generate a best response strategy against this mixture and put this new Q strategy into S. So by meaning generates a best response strategy, I mean, we just assuming that all n-1 opponents will adopt such mixed strategies, and we will use NES to optimize out Q strategy best response Q strategy against this mixed strategy, and then put back the new strategy into S and do the loop again. So that is just our basic method for computing mixed equilibria. So the intuition is just that we first discretize the whole infinite strategy space or the whole space of neural network and compute a finite mixture on this finite strategy set S.
Jean, you're out of time, so if you can just give us the last moment, and then we got to move on.
Yeah, sure. Let me just skip the experimental results part. So just last few comments. So first, our algorithm do not need to know the type distribution and the utility function information, but only black box samples. And both our method employ NES as a strong, powerful optimization procedure to optimize a neural network. But it actually can be replaced by other kinds of methods. And also, both of our methods explore the symmetry structure of the game. And it kind of reduces the problem of solve many-player games to solve two-player games. For example, in our pure equilibria method, we just solve a minimax optimization problem. And for the mixed equilibria computation method, it is some kind of the double oracle algorithm. So that is the end of my talk, and I will be happy to take any questions.
All right, sounds great. Everybody, let's thank Jean. All right, we're running a little behind. So Jean, you have one question in the chat from Amy, so I'll ask you to please answer that in the chat if possible. And then we're going to move on to the next talk. And I'm not sure who's going to be giving this one. I saw Vince show up, but Henry or you is going to be talking about automated mechanism design. Okay, Henry's here. Yay.
Hi, Nick.
Automated mechanism design for classification with partial verification. Should be able to share. All right.
So
take it away when you're ready.
Or... Sure.
Yep.
Okay, so this talk is about automated method design for classification with partial verification. So joint work with Yu Cheng at UIC and Vince Concert at Duke. The motivation of this work is to study incentives in classification. So in a normal classification setting, there's a principal or the entity who classifies. The principal aims to compute a classifier based on some prior knowledge or historical observations like sample data points. And once we have this classifier, the principal applies the classifier to agents who are being classified. And normally we assume these agents are all truthful or honest, which means they submit their feature combination X truthfully to the classifier. So the classifier can return the true label f of X to the agent. But if the agent cares about the label and they have preferences among the possible labels, then they start to get ideas. Like for example, if they submit their true features, they get some label. But if they submit something fake, something else like X prime, they get f of X prime, which is better, more desirable than the true label f of X. So if the agent is being strategic, they will in fact submit something else in order to get a more desirable label. And that's not in the best interest of the principal. So to model this ability to misreport, we use the partial verification framework. So the idea is that in practice, agents cannot make crazy reports. So the reports have to be reasonable, or they won't be they'll be detected, right? So we capture this using a reporting structure, and we say that a feature combination X can report X prime if an agent with features X can reasonably report X prime without being detected. So for example, let's say the feature that we care about is the amount of savings that the agent has. So there are three possible values to be reported: $0, $1,000, and $2,000. So normally it's pretty easy to underreport this value, right? Because you can just move your money out of the bank account. So you can report 1,000 from 2,000, 0 from 2,000, and 0 from 1,000, because the amount that you remove is arbitrary. But it's not as easy to overreport this value. So for example, you can try to borrow some money from a friend. And let's say the friend is willing to provide $1,000, but $2,000 seems a bit of a stretch. So in that case, you can report 1,000 from 0 or 2,000 from 1,000, but you cannot report 2,000 from 0. Right. So in that case, in that sense, the power of misreporting is limited, or equivalently, the power of verification is partial. So under this framework, again, the principal computes and commits to a classifier F, and then strategic agents observe this classifier and report their best response, which is the feature combination that maximizes their utility, subject to they have to be able to reasonably report that feature combination given their true feature combination. So here's a more concrete example of the setup. So suppose a professor is making admissions decisions, and there are three kinds of students: outstanding ones, good ones, and disappointing ones. Ideally, the professor would like to admit both outstanding and good students and to reject disappointing students. But turns out disappointing students can pretend to be good students by, let's say, temporarily working hard or whatever. So in that case, if the professor implements the ideal policy, what happens in reality is that outstanding and good students get in because they are accepted by the policy, but disappointing students also get in because they can pretend to be good students and be accepted by the policy, right? So that policy is effectively accepting everybody. And that's a disaster because the professor really doesn't want to accept disappointing students. So instead, the professor would rather implement a policy which accepts only outstanding students and reject both good and disappointing students. So that's the price of strategic behavior in this setup. The ideal policy cannot be implemented effectively. So here's the formal model. We have M types like outstanding, good, and disappointing, and outcomes like accept and reject. So we assume that all types share a common utility function over the space of outcomes. So in the context of the example, this means that everybody prefers accept to reject, and they have the same utility for accept. And the principal has a cost function for each type, a separate cost function for each type, which is CI. So that means the principal has a higher utility or lower cost for accepting a good student, but has higher cost for accepting a disappointing student. And finally, there's this reporting structure over the type space. For example, the good students can only be good students, but disappointing students can pretend to be good students. So the way that agents act is strategic or rational, which means fixing a policy or classifier F each type I agents will report their utility maximizing type that is permitted by the reporting structure. And we say that classifier or a policy if is incident compatible if this utility maximizing report is the truthful report. So the principal's goal is to find a cost optimal incident compatible policy where the cost of a policy is defined to be the sum of the cost for all types. And here we are with a loss of generality assuming a uniform prior over types. So we could instead look at non-IC policies, but turns out that optimization problem is NP hard. So in this talk, we don't consider that. We focus on IC policies. So quite something has been known about the computational problem of finding the best policy. So for example, the optimal randomized policy is known to be easy to find in polynomial time using linear programming. So in fact, we can let Pij, the probability that type I agents get outcome Oj, be the LP variables. So if we do that, the objective is just to minimize the expected cost, which is linear. And IC constraints are pretty easy too, because the expected utility of each type is linear in the LP variables. But it doesn't solve the entire problem because there are some issues with LP. So first is it doesn't scale very well. I mean, there are some good commercial LP solvers and they are pretty fast, but not that fast. So if the problem instance is really large, then the LP solvers can take a lot of time to solve them. And another issue is that the LP approach is infeasible for deterministic policies. They can only output the optimal randomized policy. So here comes our solution. We give a fast combinatorial algorithm for finding deterministic policies, optimal deterministic policies. And we also give a linear time reduction from randomized policies to deterministic policies. So we can use the same fast combinatorial algorithm for finding optimal randomized policies, which is generally much faster than LP solvers. So first, here's the algorithm for computing the optimal deterministic policy. I don't want to go into details, but the idea is to construct this grid graph where every finite capacity cut corresponds bijectively to a truthful policy. And the capacity of the cut is precisely the cost of the policy. So if we find the minimum cut of this graph, that corresponds to the optimal deterministic policy that's truthful, and we can construct this policy by looking at the cut. So that's the algorithm. And in order to apply the algorithm for computing the optimal randomized policy, we use the following reduction. So the reduction is based on the notion of convexity. We say that a cost function, Ci, is convex if the curve of Ci versus U, where Ci is the cost of the principal and U is the utility of the agent, if this curve is convex. And we say a cost function is non-convex if it's not convex. So we know that if the cost functions are all convex, then there is a deterministic policy that is globally optimal. So the proof is like you can run any randomized policy into a distribution over deterministic ones and while preserving the cost. So in the case where some cost functions are non-convex, we can still show that any optimal policy only uses points on the convex envelope of the cost functions. So that means to find globally optimal policy, which could be randomized, we can first compute the convex envelopes CI hat of the cost function CI. So we use these convex envelopes as the proxy cost functions. And then we find the optimal deterministic policy F hat for these proxy cost functions CI hat. And we know that they are, the F hat has to be globally optimal because CI hat are convex. And then we try to interpret this so-called deterministic optimal policy F hat as randomized policy F with the original cost function CI. So this can be done by interpreting every point on the cost function as a, on the proxy cost function as a convex combination of the real points on the real cost function. And finally, we have some generalization to combinatorial costs. So in that case, instead of n cost functions, CI, one for each agent, we have one modular cost function C, which maps every combination of outcomes to a real number, which is the cost for this combination. So this is taking into consideration the correlation between types of agents. So we get polynomial time algorithms for deterministic and randomized policies. And we show that deterministic optimality, deterministic policies are without loss of generality optimal when there are only two outcomes, like accept and reject. And there are more details in the paper. Okay, that's all I have. Thanks for your attention, and I'll take questions.
All right, let's thank Henry for the talk. Does anybody have any questions? I didn't see any come by in the chat.
Can I ask a clarification question? Do we have time?
Yeah, go for it.
I just missed where in the LP we had this constraint on the strategizing, right? The strategizing wasn't like you couldn't do anything, right? Somehow the players were constrained to only do things that were like nearby in some sense.
Yeah, sure. So the constraint is you only have this inequality where I1 can report to I2. So you have nothing if there's no possible misreporting between two types.
All right. Sounds good. Thank you very much, Henry. We're gonna give him a clap one more time. And then our next speaker is, I believe, going to be Jael. I thought I saw her around here somewhere. I thought I saw her earlier. Uh-oh, did I freeze? Oh no. Brent, is Jael going to do the talk?
So she's
trying to get in.
Yeah, but her
There's a thunderstorm.
It's a storm. Yeah.
Her internet is out.
Oh, all right. Okay, so do we want to, Andrea, are you okay swapping with Jael for the moment and we see if her internet comes back?
Please, perfect. Okay.
All right, so sounds good. So Andrea's we're gonna swap these two talks. So Andrea's gonna give us a talk on behavioral stable marriage problems.
Okay, can you see my screen? Hello?
It's black for me at the moment.
Let me try again. What about
there
now?
we go. Yep,
okay.
Now you're good.
Perfect.
All right, take it away.
Okay, so hi everyone. My name is Andrea Martin, and today I'm going to be presenting behavioral stable marriage problems. The authors of this paper are myself, Brent Venable, and Nicholas Matei. Okay. Oh. Okay, so we combine matching theories and a model of cognitive decision making from psychology. And also from the stable marriage point of view, our model handles preferences that are defined over multiple attributes, and a model that is also a model that is not deterministic. And this model behaves like human behaves. So this is, let me first go what are stable marriage problems. So we have two sets of agents. In this case, we have women and men. And then this is how we represent the preferences. So we have, for example, for woman one, we have that she prefers M1 over M2 over M3 and so on. And this stable marriage problem is of size 3. So 3 men and 3 women. So what is a stable marriage? So first, let me define what is a marriage. We have that each woman is assigned to a man and vice versa. What is a blocking pair? So let's say we have a man and a woman that are not matched to each other, but they actually prefer to be with each other than with the current matching that they're with. And a stable marriage is a marriage with no blocking pair. And in a stable marriage problem, everyone is matched to at the same time, and we assume there is no cost in breaking a match. This is an example of an unstable marriage. So let's assume we have this matching, women 1 with men 1, woman 2 with man 3, and woman 3 with man 2. So here, as you can see, there is a blocking pair, which is W2 with M2. So W2 prefers M2 over her current match, that is M3, and M2 prefers W3 over her current match, that is W3. I also want to show some, actually 2 examples of stable marriages. Here we have the blue one, that is the women optimal. This means that they get the best possible partner that they can hope for, and we have the men optimal in green. This is just examples. So in a stable marriage problems, it always exists a stable marriage, and there is an algorithm that is called Gale-Shapley algorithm that actually finds a stable matching. It's a proposal phase-based algorithm where men propose to women and women accept and reject the proposal, and it finds a stable matching in quadratic time. So as I mentioned before, we were combining the stable marriage problems with a cognitive model. In this case, we are using the multi-alternative decision field theory. And the idea is that we want to model the preferences that are represented in the stable marriages using a cognitive model, the MDFT. So what is the MDFT? It's a cognitive model that describes how humans deliberate. It's based on the idea that information is sequentially sampled and accumulates over time to make a decision. These are the components of MDFT. We have the M matrix, which is how we represent the preferences with different attributes. In this case, we have 3 options: salad, burrito, and vegetable pasta. And we have 2 attributes: taste and health. So we represent, for example, for salad, we have a low value for taste, but a higher level for health, and so on. Then we have the contrast matrix C, which is used to compute the advantage and disadvantage of one attribute to the other, and the attention weights that tells us who is what are we paying attention to. So in this case, we're paying attention 45% of the time to taste and 55% of the time to health. So how are the preferences calculated? So the preferences are accumulated sequentially, and there are 2 ways to find the preferences. So one is we stop after a given time of iteration. So let's say we have 50, we say the iteration 50 times. So after 50 times, we stop and we see the preferences for each object, and then we find the maximum. And then the other way is with a threshold bound. So we stop when one of the objects gets to the preference gets to certain value. And at each iteration, we pay attention to one attribute, and then we compute the advantage and disadvantage of all the options with respect to that attribute. And here the matrix S tells us how preferences are accumulated over time. So how a preference at a previous iteration influences the preference of the next iteration. So what we do is that we use MDFT to induce a probability distribution that we're then using in the stable marriage problems. So how do we do this? Let's say we have an agent. Let's say we have woman one, and then we have, and she has three options. So M1, M2, and M3. So what we do is that we take by pairs. So we take M1 and M2, and then we use their M values and we run MDFT and we pick one candidate. So let's say M1. And then we do this 100 times. So we get a distribution for these two. And we do the same for all the pairs. So for M1 and M2, for M1 and M3, and for M2 and M3, and we do this for all the agents. And at the end, we induce a choice probability. So now let me talk about behavioral stable marriage problems. So we have a behavioral profile that is a stable matching problem where every man and women represent their preferences with an MDFT, as I mentioned before. And the difference here is with the normal ones is that we don't have linear order. What we have is a pairwise probability. So the notion of locking is actually probabilistic. And we say that a matching is alpha B stable if the probability that there is no blocking pair is alpha. And the behavioral stable marriage problem is that of finding an alpha B stable with maximum alpha. Alpha B stable matching with maximum alpha. In addition to stability, we consider fairness, which tries to measure how happy the members of a group are with their partners. To measure this, we use the sex equality cost that wages the difference between the position of the partners in their orderings. Because here we are in a probabilistic setting, we extract linear orders from the MDFT, and then so this way we will have multiple linear orders with frequencies, as you can see here. And instead of the position, we consider the expected position since it's in probabilistic settings. Another thing that we considered that was important to study was some behavioral effects that humans have and that the MDFT models. One of these effects is called the similarity effect. So when we add a similar candidate to the candidates that we're considering, this reduces the probability of the similar. So we add one similar candidate to one of the candidates that we already had, and this reduces the probability of choosing this similar candidate. And if we add a compromise candidate, so someone that is in the middle of extreme ones, usually we tend to choose this compromise candidate. So what we found is that by running Gale-Shapley, Gale-Shapley was actually affected by these effects. And the solution that Gale-Shapley was returning, solutions that Gale-Shapley was returning were not maximally stable when we look at the pairwise probabilities. And here in the Gale-Shapley was a little different than the one I mentioned before. The difference is that when the men propose, we run MDFT, so to know which candidate it should propose to, and then when the women were accepting, we ran MDFT to see if they were accepting or rejecting. So because Gale-Shapley was being affected by these effects, we decided to create different algorithms so that we could find the maximally alpha B stable. So here we created two linear programming algorithms. One finds the solutions that are maximally alpha stable, and another one finds the most fair solution. And we also created a local search algorithm that actually combined fairness and stability, so that we could find something that had good stability but was also fair. So here, so we created different problems with different sizes. For example, if I have 10 men, if I have size 10, that means we have 10 men and 10 women. So as you can see, the blue one here, that's it performs the best in stability. And the red one here it always finds, always returns 0, so the most fair, always. And then we also had 3 variants of Gale-Shapley, which were suboptimal with respect to stability. And they were also very high in sex equity cost, so they were not fair. And here the FBLS is the one that combines, is the local search that combines fairness and stability. And as you can see, it's more to the left, so it's more fair, but it's still reasonably high for stability. Another thing that we studied was the execution times for these algorithms. And what we found is that, as expected, the BILP, the linear programming one, time out after 15 agents. So it didn't scale, but the local search actually scaled. And at 16 agents, it found a solution at around 900 seconds. And then for the future work, we would like to study behavioral models in a more complex setting, such as one-to-many and many-to-many matching problems, by studying their integration with matching algorithms, such as the Boston mechanism, and also to investigate further the interplay between fairness and behavioral modeling in algorithms targeting fairness, both at the matching and the procedural level. And another thing that we want to do is to study the complexity of these behavioral stable matching problems. And that's it. Thank you.
All right. Thank you, Andrea. Thank you very much. All right. We've got time for a question or two. If anybody has. All right, Hadi had a question in the chat, so I'll go ahead and ask that one. If anybody has a question, they can raise their hand. So Hadi asks, MDFT seems to be a special cognitive model for modeling probabilistic preferences. Can you elaborate on how these two are related, i.e. stability under uncertainty and MDFT model?
Wait, I didn't understand the question, and
Yeah.
I cannot see the chat. Oh, I can see it. Okay, okay.
Okay.
Seems to be.
So the Andrea, do you want to answer that one, or?
I'm not sure about that.
I mean, I can elaborate a little bit if that's
Yes, please.
so it's very the cognitive model, the MDFT model is a very interesting model, and I see the goal is to achieve stability or some approximate stability and approximate fairness there. Just wondering if I can kind of try to condense all of that model and just say, hey, let's assume, let's say in the deferred acceptance algorithm, I'm going to just, instead of going through the MDFT model, I'm just going to assume there's a black box that gives me the preferences, some probabilistically preferences that I can sample from, and then use that just to run my deferred acceptance algorithm the way that you were using it. Is there a difference between them, or is it just trying to give additional view of what is happening inside the cognitive model to create the preferences?
Okay, now I understand. Yes.
I don't know if it helped, this explanation.
Yes, yes. So, yes, you can do that, but also we wanted to use a psychological model because we want to have, as I mentioned, like the behavioral effects. Because you can just give the probabilities, but you also want it to be more realistic and see how it actually affects when humans are making these decisions. I think that's why we use the cognitive model.
And I have a follow-up question. So do you know anything about whether using this type of models to create preferences or sample preferences would help in somehow achieving sex-equal matchings? Because we know sex-equal matchings, like achieving them is intractable, or finding a sex or stable sex-equal matching is intractable. Would this help break the intractability? Give enough constraints or enough structure to the problem?
I don't know if it will help, but it can certainly, as we saw, for example, Gale-Shapley was affected by this. So maybe it can help us study further how these like behaviors can affect all of these matching, because I don't think right now no one is taking into account how the human side is affecting the matchings. I don't know if Brent wants to add something.
Yeah, if I can chime in. Yeah, so these models, depending on, if you put some constraints like you're saying on MDFT, you will have that the induced preferences are stochastically transitive. And depending on the version, you have weak, moderate, and strong stochastic transitivity. Depending on the constraints, you get these different versions, and depending on these different versions of transitivity, you move from hardness to easy. So we have some preliminary results on this based on this tie between stochastic transitivity and MDFT.
Interesting. I would be very interested to read that. So
yeah,
send me the paper as soon as it's out.
All right, sounds good. Let's thank Andrea one more time. Hadi, do you have a strong, or any of the organizers who are still here? We're running we're about a half hour behind right now. We can either take our 10-minute break if people feel like we need a break, or we can push on ahead. So we try to get this wrapped up somewhere close to time. I'm kind of ambivalent.
10 minutes maybe. I don't know if people win. I mean, I'm not sure. I mean, my class, I usually give 2-minute break. I don't know if it's enough for anybody to run to the bathroom.
Yeah.
But
Amy says we need a break. 5 minutes is enough. All right, so let's do that.
Yeah, 5 minutes would be good. Yeah.
We'll do a 5-minute break. So let's do a 7-minute break, so that way it's on a quarter hour. So let's plan to be back here on a quarter till for those of you on full hour time zones, as our last conversation had. So here for me in Central, that will be 10:45. So let's take about 7 minutes.
And do you want to send
And I will throw everybody in a breakout room.
Perfect.
Yeah, I'll do that right now.
Yeah, throw in a bigger groups. I think it's some people don't want to go, or they're not there, so it's bigger groups. Give more opportunity.
All right, welcome back, everybody, to the main event. Jael, did you get your internet? Is it back on?
I am on my phone hotspot, which seems to be working fine. So we'll see how that goes.
All right. Thanks a lot, Cox.
Yep. I don't know about you, but for me, whenever it rains, internet just dies.
It goes out a bit for me. I'm not in New Orleans right now, so I'm in Texas. It works a little bit better here for some reason. All right, so we had to swap the last two talks here. So the next talk is going to be Jael Sherman, who is going to talk to us about modeling voters in multi-winner approval voting. And so you've got about 13 minutes, Jael. Take it away.
Thank you. Let me try and share my screen.
Should be able to, hopefully.
I have to hold on, sorry. Thought I had it all ready to go. Okay, there it is. You all see it?
Yep, looking good.
Awesome. Cool. So I'm Jael. I'm going to be presenting some work that I've done with Nick, also with Brent Venable and Jason Harmon, and we're going to be looking at modeling voters in multi-winner approval voting. So approval voting is a voting rule that's commonly used in board elections and internet tools such as Doodle. It allows people to vote for as many candidates as they wish, and then the candidate or top X candidates with the most votes wins the election. Now, ideally, we hope that people would vote in an election using their true preferences, and in many situations, it's clear what a truthful or sincere vote would be. So for example, in the US, voting with your true preferences in a presidential election would be voting for your most preferred candidate. However, in approval voting elections, there's many subsets of candidates that could be considered sincere. And Stephen Brahms actually noted that a ballot is sincere if and only if, whenever he votes for some candidate, he votes for all candidates preferred to that candidate. So consider an example where we have 5 candidates, A, B, C, D, and E, and each generates some amount of utility for the user, as shown in this table. Multiple sincere ballots are possible, including voting for the highest utility candidate D, but you could also vote for BD, ABD, ABCD, or ABDE. So because multiple sincere ballots are possible, we wondered how voters choose which candidates to approve and what types of heuristics might guide their choice. So in this talk, I'm going to be exploring or talking about a study that we did on Mechanical Turk to evaluate several heuristic models from the Comstock literature in their effectiveness for predicting voter behavior. And we're also going to propose a new model that significantly improves predictive performance by accounting for the size of the winning set and human cognitive constraints. So we're going to look at 4 different heuristics in the context of approval voting. This includes complete, or voting for all candidates with positive utility, take the X best, or voting for the top X candidates, attainability utility, or considering the attainability and utility of each possible ballot, and then approve the one that maximizes these. And then finally, an attainability utility threshold, where we account for human cognitive constraints that consider the attainability and utility of each individual candidate, and then approve only those that exceed a certain threshold. So to determine how well these heuristics work to describe voting behavior, we asked 104 participants to vote in a series of hypothetical elections. For each election, they were shown a scenario similar to the one on the left, and all participants voted in single winner elections, while also 50 voted in the 2 winner elections and 54 voted in a 3 winner election. In each condition, participants voted in scenarios with either 0, 1, and 3 missing votes to introduce different levels of uncertainty. And they were shown a set of candidates, how much money they would earn if that candidate were to win, and then they could see the number of votes earned by each candidate so far. In some scenarios, they were the last to vote, and then in others, they were told the number of voters who would be voting after them. And they were also told that in the case of the tie, the winner would be chosen randomly from among the tied candidates. So each participant was asked to vote for as many candidates as they wish, or they could abstain. And after voting, they saw the outcome of the vote as well as how much they had earned. So over the course of the experiment, they were able to earn between $1 and $8, which was determined by the outcome of the scenarios. So I'll describe the 2 scenarios that we used for modeling and evaluating the heuristics. Scenario A featured a neutral candidate worth 0 cents, and that candidate was currently leading the election, but the voter could still cast a ballot that had some chance of electing a candidate that had some utility. And in this case, we expect people would be most likely to prioritize their most preferred candidate using a take the X best approach. The table in the center represents the different combinations of winners and missing votes that the participants saw throughout the experiment, and it also lists the maximum expected utility for each condition, as well as the take the X best heuristic that achieved that outcome. So for example, voting for the top 2 candidates, B and E, would achieve the maximum expected utility in the 3 winner condition. Voting for either the top 1 or 2 candidates was the optimal strategy across all of the different conditions tested. And in the table on the right, we can see a summary of the behavioral results. In the study, only 21.5% of votes were optimal, while 77.8% used the take the X best heuristic, where X was either 1, 2, or 3. And an additional 13.7% voted with a complete heuristic, that is voting for A, B, C, and E, while only 8.5% used some insincere strategy. Scenario B was very similar to the previous one, except in this case, the candidate earning 1 cent was leading the election, but there was still a possibility of electing a more preferred candidate. And here, the optimal strategy is the same take the X best strategy for each condition as it was in the previous scenario. And the behavioral results were very similar to the previous scenario as well. So in the behavioral results, we found that 90.9% of the ballots were sincere. We found that voting behavior did not change significantly between the two scenarios as the amount of uncertainty increased, but it did change significantly as the number of winners increased. The diagrams here are for scenario B, and they show how the proportions of voters using each heuristic changed as the number of winners increased. So in particular, we can see that fewer voters voted for a single candidate in the 2 and 3 winner condition, and that many people switched to voting for 3 candidates in the 3 winner condition. So using the data that we gathered from these 2 scenarios, we sought to evaluate how effective each heuristic was for predicting their behavior. One of the heuristics we considered was the attainability utility heuristic that was introduced by Fairstein in 2019. And this heuristic describes voting behavior as a trade-off between how attainable a candidate appears to be and its utility. So Fairstein's paper describes attainability utility for plurality settings, where attainability is modeled as an arctangent with the shape of the curve dependent on the proportion of the ballots cast for a candidate, the number of candidates in the election, and of beta can be seen in the graph. So lower values of beta mean the candidate seems more attainable when there's more uncertainty. And as that uncertainty decreases, the attainability continues to increase. High values of beta means that the candidates have low attainability when there's a lot of uncertainty, but quickly become more attainable as that uncertainty decreases. So note that since this model was developed for single winner plurality voting, we had to first generalize it for a multi-winner approval setting. And this led to 3 main changes. First, the proportion of votes for a candidate depends on how many candidates were approved by unknown ballots. And since the number of approvals is unknown, we find the average attainability over all possible proportions given the number of possible ballots. Next, we account for the fact that larger winning sets mean that candidates need a lower proportion of votes to appear attainable. And then finally, we calculate the attainability score for a ballot rather than a single candidate. After calculating the attainability and utility of each possible heuristic, we approve the ballot that maximizes the trade-off between them. So the parameter alpha modulates that trade-off so that if alpha is 0, then the decision is based only on attainability. And if it's set to 2, then the decision is made based on utility only. So after generalizing this attainability utility model to account for multi-winner approval voting, we explored the prediction space to see what kind of ballots the model would predict. So in the table on the left, you can see that the ballots predicted for scenario A, and then the corresponding alpha and beta values that predict them. And here we can see that the model is able to predict complete ballot, A, B, C, and E, and it also predicts ballots that include the attainable candidate D. However, it does not predict the optimal ballot, which would be E in a single winner condition with no missing votes. And it also does not predict any of the take the X best ballots that were most often observed in voting behavior. So we can see on the table on the right, the most common strategies were to vote for E, BE, or ABE, and none of these are predicted by this model. So because of this, it's clear that the attainability utility heuristic is inadequate for modeling voting behavior in approval voting settings. We believe that it doesn't well explain behavior because of the cognitive demands that are required for calculating attainability for all the different ballot combinations under uncertainty. So it'd be unrealistic to expect that our voters would be able to do this when they're trying to identify a particular ballot. So to address this, we introduce a new model that accounts for cognitive constraints. And in this model, participants are assumed to weigh the trade-off between attainability and utility for each individual candidate, and then approve those that exceed some threshold. So in the upper right, we can see the attainability utility calculated for each individual candidate in scenario B for a range of beta values where alpha is set to 1, representing an equal weighting between attainability and utility. Depending on the threshold that is chosen and the value for beta, different sets of candidates can be selected to approve. Oops, too far. We evaluated both attainability utility model, the attainability utility threshold, against several baseline methods, including optimal, complete, or voting for all candidates with positive utility, or take the K-best, where K is equal to the size of the winning set. We used a leave one out method, where we learned the parameters for each subset of 5 examples and then predicted the final one. And the percentage of ballots predicted accurately is the number reported in our evaluation results. So from these results, we can see that the attainability utility with threshold model resulted in an improvement of the prediction accuracy over the other baselines. So in conclusion, I've shared a study of approval voting that shows that people generally vote sincerely, but vary in the number of preferred candidates that they approve. We also examined how well different heuristics predicted voting behavior and found that none were very accurate. And then finally, we introduced a new model of attainability utility with threshold that is more cognitively plausible, requiring fewer mental computations. And this model provided the best predictive power over the other models we tested. Thank you.
All right, let's thank Jael. There's a couple of questions from Errol in the chat. I think the first one is, does the number of winners affect the fraction of sincere voting?
So I don't believe it would, because being a sincere vote would just be voting for your like everything preferred to the candidates that you vote for. So if you vote for a candidate with 10 cents, then you vote for all candidates that are more than 10 cents.
No, but maybe in the experiment, if I see that there is only one winner, I will try to be more strategic. I don't know. It's an empirical question, not a theoretical.
Mm-hmm.
I don't think we ran the Sankey diagrams for those. That's a good question. It's a good question, we should go find out.
Yes.
So Alan asks quickly, and then we'll have to move on. Sorry, Errol, I'm skipping your other question. So Alan asks quickly, do you know what the demographics of the Turkers were? Do you think the behavior would vary by region? Some places making use of multi-winner approval political systems, for example.
So we do have that information. I haven't looked into it in depth, but I think that definitely would be interesting, particularly thinking about where they came from and the voting systems that they use in those places.
Excellent. Yeah, that's something we should definitely dig into as well. So, all right, thank you all. Let's thank Jael one more time. All right, our next speaker is, I'm not quite sure who's going to speak, Annalise or Hamming? Okay. So Hamming's going to speak. So we're going to do classification with strategically withheld data.
Thank you, Nick.
Take it away.
This is a joint work with my wonderful co-authors at Duke, titled Classification with Strategically Withheld Data. The context of what we're studying here is strategic classification. That is, given access to truthful training data, we want to obtain a classifier that performs well when the test data can modify its feature values in order to be classified as a positive. So the timing of the game is exactly that. There are truthful data. The principal have access to samples of it. The principal wants to train a classifier knowing that the test data would like to be accepted, and the test data modifies feature knowing the classifier. So this problem loosely happens in real life in job application, credit approval, online dating, etc. For example, I would prefer I have a nice profile picture, possibly altered version of myself on an online dating website so that I look more attractive to the ladies. the nature of this problem is summarized really well in this paper in 2021, and I quote, strategic classification introduces a form of distribution fit, but with a unique property that the shift is determined by the predictive model itself, albeit indirectly through the effect on user responses. But what's clear, hopefully by now, is that we are quite hopeless if the modification is unconstrained. That is, if everyone can submit a profile picture of Nicolas Page, then the ladies have nothing better to do. So how about we introduce some constraint here? There's a long line of work that are making this assumption that modification incurs a transformation cost, and the test data wants to maximize its prediction minus the transformation cost. This is sort of the data point can misreport around within a ball around it kind of interpretation. What about this one? We assume that agent can withhold features at no cost. This would be applicable when the feature that the agent can withhold can be missing by nature. And this will be the setting of our paper. And we're going to present 3 algorithms that address this problem and their empirical evaluation. To give an example of what we're talking about, consider college applications when at least I had to submit at least one of SAT and ACT. I could take SAT multiple times, but I had to submit at least one. And let's say the scores for each of the 2 sets are binary, and the college has full information of the prior distribution. That is, they know how many types there are and how likely are each of the type deserving to be accepted. Based on the data, the college learns a classifier, and in real life, this is somewhat true. That the classifier the college uses is known to the applicant, and if that's the case, applicants might want to strategically withhold some of the scores to obtain a better result. So the challenge presented to the principal here is that it's impossible to distinguish between an applicant that takes both tests and report only one, and an applicant that takes only one test for non-strategic reasons. Let's go through the example here and see what a good classifier looks like. Ideally, we want to predict the above. That is, for every type, if more of them are good students, we want to accept. If more of them are bad students, we want to reject. However, this classifier is not optimal because of the strategic reporting. Those who get a low score in the first test, let's say ACT, would report only their SAT score and get accepted. And if you do the math here, that will not be the optimal classifier. In essence, this missing high score cannot be assigned a prediction accept unless low high score also gets the same prediction. To make it optimal, we either have to reject both, accept both, or accept only low high and reject missing high. Now, compared to 3, this would be the optimal classifier. That is to reject all 3, reject both. With that, we're ready to introduce our Minka classifier. That is essentially visualizing the sort of rationale that I described. If the true distribution is known, that is, if the principal is given a table like that, computing the optimal, the problem of computing the optimal classifier reduces to min cut. It looks like this. If we have a node for every type, nodes are connected to source and sink with weighted edges representing how many how many of those type are have positive label or negative label, and the key here is to connect these misreporting structures by edges of infinite way, so that when we get a min cut, we can make sure that if a classifier, we can make sure that a type is accepted only if one of the score is missing, it is also accepted. So in the language of machine learning, the mechanism design that what we just did is merely the training process. Knowing the prior distribution is essentially given a training set. Constructing a classifier is basically training on the training set. The issue is, how does it perform on a test set? And I think it's clear by now that the discrete nature of min cut classifier greatly constrain what it can do. Because with many numerical features, you can't have every node for every possible value of the numerical feature. Even though there's some way to mitigate that, and we'll come back to that later, we hope that we can do better. So what else can we do? Nicely enough, revelation principle holds in our setting. So we can focus on finding truthful classifier without loss of generality. So perhaps we can find inspiration from knowing what truthful classifiers look like in this case. So let's say we have 3 features, and x1, x2, x3 are possible values of the 3 features. We can represent combinations of features in a hierarchy like this. And let's say we have an agent with naturally missing first feature and has a value x2 for the second feature and value x3 for the third feature. We know that this agent, by dropping 1 or more features, can report any other combination that is reachable, that is below it. So here's an idea for constructing a truthful classifier. We associate a subclassifier with each node in the hierarchy, like such, and we can accept an agent if it is accepted by one of the classifier that it can access. So in the language of ensemble learning, we are using a max ensemble. Good news is that a classifier is truthful even only if it takes this form. With that, we're ready to introduce our second classifier, the hill climbing classifier. That look exactly like this. It can obtain using an iterative hill climbing training procedure. In each iteration, we go over each subclassifier and retrain it using the data point rejected by other subclassifier. And this procedure converges. The shortcoming of this is also pretty clear. There are combinatorially many classifiers to train. Even if every subclassifier is a logistic regression, it's still too much work to do. Even though we can do better, as we'll see later, we want to hopefully have a different approach when we have many features, or reasonably many features. We look for inspiration from the literature on handling missing data naively. There's 2 classic approaches: min mode imputation and reduced feature modeling. So imputation is simply filling in the missing values, and in this case, the min mode of each features, and then using it out of the box classifier. However, as you would imagine, it doesn't do well when the test data are strategic. Reduced feature modeling is essentially train an ensemble classifier so that when a test data point comes, I have exactly a classifier for that combination of feature that he has available. And this will not do well when the test data is strategic either. And as you saw, the hill climbing classifier is sort of an analogous of reduced feature modeling in the strategic setting. So what can we do about min mode imputation? Can we impute such that an imputed value always give a non-positive signal? Here's an idea. If we can encode all features as non-negative, learn coefficients which are non-negative, then there are no incentive to drop features, since doing so can only hurt the logic function. We can train a classifier like this by using projected gradient descent. That is, say we are here we're training a logistic regression, but after each gradient step, we apply a projection. That is, if some coefficients are negative, we project them to 0. Here's how the three classifier stack up in real-world data. So we have 4 credit approval data. We'll randomly remove a fraction of feature values to simulate the data missing by nature. And we compare with baselines, the two previous naive baselines for handling missing data. And I'm not going to go over the numbers here, but our methods perform better than out-of-the-box methods when strategic behavior is at play. Yeah, I'm not going to go over these details. In summary, we address these research questions. If the true input distribution is known, can we compute the optimal classifier? The answer is affirmative. That is the min-cut classifier, but due to the discrete nature, it is prone to overfitting. Are there simple classifiers that are robust to strategic withholding? We characterize the structure of truthful classifier, and from that we devise the hill climbing classifier. However, it doesn't work when there's too many features. So we devised incentive compatible logistic regression. We tested our methods on credit approval data sets and saw positive results. In conclusion, we study the problem of binary classification when each agent at prediction time can strategically withhold some of its features to obtain a more favorable outcome. We devised 3 classification methods that are robust to this behavior. And in future work, we hopefully explore more on the dynamic of what happens when truthful data is unavailable, and develop a broader theory for this sort of robustness. Thank you.
Awesome. Thank you so much, Humming. Oops. Does everybody give him a hand? Yay. Sorry. You guys hear me? Yeah. All right. Sorry, I had to open up my students' office hours on the side here, but no one's there. So I'm getting a message from one Zoom that I'm muted and the other one that I'm fine. So my bad. Does anybody have a question for Humming?
I have a question. I just missed in the experiments, like you're supposed to be allowing these, everybody should be strategically withholding information. So I just missed in the experiments how they were strategizing about the information that was being withheld.
Yeah, so in the naive setup, for example, on the top right table, the row imputation with logistic regression, what happens is there's truthful test data. That's the first column for each data set. In the second column, what happens is the data will attempt all possible dropping of the features in order to get a positive classification outcome. That applies to all classifiers.
Got it.
All right. Humming, Nicholas Bishop asked a question in the chat. I'm going to ask you to answer that one in the chat so we can get to our last talk, and we'll finish up about 30 minutes behind. But let's thank Humming one more time for their great talk. Mm-hmm. Yeah, you can do it as we go. But thanks, Humming.
Bye.
All right, so with that, we've got our last talk of the session and of the day, which I believe is Andrew is going to be giving this talk. So this is guaranteeing maximum shares, some agents left behind. So I will let you take it away, Andrew, if you're here. Yeah, there you are. Okay, I believe you're on mute.
Awesome. So hi, everybody. I'm Andrew Kearns. I'm going to be presenting guaranteeing maximum shares, some agents left behind. This was joint work with Dr. Hadi Hosseini, who's also in the chat here. So the research here that I'm doing is in the problems of fair division. So how do we allocate a set of indivisible items fairly so that agents are happy with the allocation? So one way kind of a simple example here, I might have like 3 aliens and a bunch of fruit. With COVID, these fruits aren't really shareable, so they're indivisible in the setting. We may have like an allocation that gives some agents certain fruits. And the question is, well, how do we actually measure fairness? The measure that we're going to be talking about is the maximum share notion, and this generalizes the cut and choose algorithm. So the first agent is going to go through and divide items into bundles, and then assuming each other agent takes a bundle they prefer first, the last bundle, which is possibly the worst, is what the first agent is expecting to receive in any allocation. Now each agent is going to do this on their own, and the goal is that we can allocate a bundle, so all of the items, into bundles that each agent finds at least as valuable as when they do this process. So to kind of formalize this model, we have a set of agents n, a set of goods m, and we're going to assume additive valuation functions. And that just basically means that the value of a bundle is equivalent to the sum of the items in that bundle. And then our maximum share is the maximum over all possible allocations, the minimum bundle for that agent. And then again, we're trying to give each agent at least that much value. So to kind of give an example here of what that actually looks like, we have some model of our problem where we have the agents and the amount of values that they have for it. They can divide the items into bundles, and the maximum share values here is given by the smallest bundle. So there's good and bad news with maximum share. The bad news is that it doesn't always exist. And when we actually try to allocate it, it's empty, hard to find allocations that are even close to the approximation. So recently we look at approximating the actual maximum share values. So there's kind of 2 different types of approximations that have been out there. The first is fractional or beta MMS allocations. And in this setting, we can give agents 3/4 plus 1 over n of their maximum share value. If the number of agents is strictly 3, we can actually give them, improve that bound to 8/9 of their maximum share value. Alternatively, we can look at kind of an ordinal approximation. And here, what we're doing is we're saying, instead of trying to allocate a fraction of their MS, we're going to tell the agents that they have a different number of agents that they're actually competing with. So here, I have our original instance with 3 agents, but if I were to tell them that they're looking at 4 agents, their amount of value that they're expecting to receive goes down, and so they're more likely to be happy if we had a little bit looser allocation. So to this end, our research kind of tries to combine these 2 different notions, so a fractional and an ordinal approach. So here we introduce a notion called alpha beta MMS, and this notion is to say alpha if n of the agents receive at least a beta fraction of their MMS. In the instance here, we actually have 3 different values of alpha beta that are satisfied simultaneously by 1 allocation. And it may be a little weird that we're not necessarily saying anything about the other n minus, or 1 minus alpha 8 fraction of the agents, but we can think of kind of settings where this is still relevant. For example, if we have college students, we want to make sure that our seniors have priority for classes so that they actually don't have issues when it comes to graduation. They have to have a full schedule so they can get their last classes in. Our freshmen may have lower priority, and if they can't pick the in-major classes, they can at least pick their elective classes. So with this alpha beta notion, we come to the questions in our research. So the first one is, well, if we only remove 1 agent, how much value for beta? What fraction can we actually give all of the remaining agents? The next question is, how many agents can we receive full on MMS? So if we fix beta equals 1, what's the value of alpha that we can give all agents? Or what number of alpha agents can we give? And then the last question is kind of, what's the relationship between alpha beta and the traditional ordinal approximations, MMSK? So to answer the first question, we have a theorem that says we can give all but 1 agent 1/2 n plus 2 over n plus 1, which sounds a little chaotic, but basically it's a fairly straightforward algorithm. So we're going to pick all but 1 of the agents. We're going to do this procedure called normalize, and I'll go more in depth on that in a second. And then we're going to run a modified NV graph. And this modification basically works for ordered instances, which I'll get to in a minute here, and it guarantees EFX, and that directly translates to the result that we have here. So what is normalization and why do we care about it? So normalization is basically 3 or 4 different lemmas that are combined in very often in maximum share research. So here, there's kind of 3 steps that we care about. The first is scaling. We're going to assume that the sum of all items is equivalent to the number of agents. And because the maximum share value is upper bounded by proportionality, we know that this scaling assumption means that the maximum share value is going to be less than 1. The next is going to be ordering. We're going to assume that all agents are kind of maximally competing for items. That is to say that all of the items are labeled in descending order. And then at the end of the day, after we find an allocation, we can kind of unorder our allocation by letting agents pick their favorites according to the order of the items that they received. So I kind of relabel my items and just sort them. And the last one is reductions. And reductions basically allow me to say that there is no good with value more than 1, and the n and nth plus 1 goods have value less than or equal to 1. And this is important because it basically allows us to upper bound the number of high valued goods. So to kind of give an example of what a reduction might look like here, the second agent says I have 1 item with at least 1 value. So I'm going to go ahead and just allocate that item to him. Then I'll remove him and that item from the market, and we can continue this process. Notice that I can now rescale and I can continue reductions. So here, there's another reduction possible. So I'm going to take it, and then I end up with another allocation, or another instance where I can keep reducing. In this instance that I showed you, it actually is possible to give all agents their full MMS value with just reductions. But that's not always the case. And sometimes, as this example, you end up with a normalized instance that has strong properties to it, where we can still find an allocation that allows us to find an allocation for the original instance with the same guarantees. So kind of combining all those steps together, we go back to our -1 result, and that's kind of how we achieve that ratio. So the second question that we asked was, well, if we clamp beta to 1, if we say that all agents that we care about have to get their full MMS, how many agents can we actually get? We claim that we can give 2/3 of all of the agents their full MMS. And the intuition for this is using an algorithm called bag filling. And bag filling is very straightforward. We take 1 high value good and then put it in a bundle, and we just kind of keep filling with low value goods. Since we know there's only n high value goods, we can all of the remaining low value goods have value less than 1/2 by our reductions. We can kind of keep filling until the bag has value at least 1. And since the last item was a low value good, the total value of the bag is at most 3/2. So we intuitively should get about 2/3 of the agents receive their full value. The problem with this, however, is that because we're allocating more than 1 value in a bundle, it's possible that we end up with all of the low valued goods allocated and have more than 2/3 high valued goods. In this situation, our remaining value is not divisible enough to kind of keep allocating it. So what ends up happening is we end up getting forced to allocate 2 high value goods together, but this may have value more than 3/2, which kind of stops us from continuing our process. So to address a couple of problems that show up here, the first one is if different agents have different numbers of high value goods, because the preferences don't have to be the same, we're going to use a technique called lone divider. And lone divider basically just says one agent is going to do all the divisions, and then the other agents will kind of compete using a matching procedure, and we'll reduce from there. In our paper, we introduced another notion called strong normalization that allows us to make even stronger claims about the amount of value that's wasted. So strong normalization basically says that the total value of every bundle is exactly 1. So here I have my MMS partitions, and if I look at like this brown bundle, it has value more than 1. So what I'm going to do is I'm going to reduce the items in one of the maximum share bundles until they have value exactly 1. The next step here is a pairing argument. So in lone divider, we may have some items that were previously allocated. So if we have like high valued items here that were already allocated, and then the first step we want to do is we want to pair some high value goods together so that we get that worst case out of the way. We know that has to happen. So we're going to introduce another step called restricted bag filling. And the restricted bag filling is really the key to our 2/3 result. And the way restricted backfilling works, it says, well, any item corresponding to something we use during pairing, any of those low valued items, we can continue to use a little bit more greedily because we know that with strong normalization, they had exactly the value 1 minus the high valued good. And so we can use those to fill a couple bundles before we do our normal bag filling. And that allows us to get to that 2/3 one result. So the important thing in that last theorem is that strong normalization is not necessarily a polynomial transformation. Because we had to know the MS partition, we had to actually compute that first. And that can't be done in polynomial time unless P equals NP. So while we have an algorithm, it's not polynomial. It turns out that if we just kind of relax strong normalization to our previous normalization, and if we just skip the restricted backfilling step, we still achieve 2/3 one as long as there's only less than 9 agents. If there are 9 agents, that actually is possible to come up with a counterexample as shown on the screen here, where we don't fill 9 bundles, but for less than 9 agents, that actually isn't a problem. And the last question that we asked is, what's the relationship between alpha beta MMS and ordinal approximations? To that end, we say that we can prove that alpha 1 MMS implies the existence of MMSK for k greater than or equal to the ceiling of n over alpha. And so basically what that is like, if I say 1/2 1, so half the agents receive their MMS, that means that I can give all agents MMS 2n. Or in our case, we're giving 2/3 of the agents their full MMS. That implies that MMS 3/2 exists. And as we previously said, the best possible result that was known before us was MMS 2n minus 2. So we significantly improved that bound. The way we actually have this transformation is basically by just assuming from the definition of alpha beta MMS that we have a slightly stronger notion. We're saying that all subsets of alpha n agents can be guaranteed their beta MMS. And this is a little bit weird, but because of that strong assumption, we're actually able to make this claim that MMS 3/2 exists. So our 2/3 one result wasn't guaranteed to run in polynomial time and guarantee all 2/3 agents for more than 9 agents. So we actually tested that same algorithm for more than 9 agents. And here we can see up to 200 agents. And even though it's not guaranteed to give 2/3 of the agents their MMS, the worst case still showed up with only at least 2/3 of the agents receive their MMS always. So here I want to kind of point out 3 different bands. The first is this upper triangle, which states that, when the number of items is less than the number of agents, all agents have an MMS of 0. So we're just easily give them nothing and their MMS is satisfied. The kind of worst case band here, which is linear in the number between the number of agents and the number of goods, and the real worst case band where we only have 3 agents. Here, if we don't give all agents their full MMS, 2/3 of them, which cuts our lower bound. So this kind of leads into our open questions, which is, well, can we actually compute 2/3 one MMS or better in polynomial time for more than 9 agents? What happens when we try to extend our results to chores and mixtures? And is it possible to add Pareto optimality to these approximations? We know that if MMS exists, or if an alpha beta MMS exists, the alpha beta MMS plus Pareto optimality exists, but we don't necessarily know how to compute that. So I'm going to leave a summary slide up and say thank you and ask for any questions.
All right, let's thank Andrew one more time. Thanks, everybody. All right, is there any questions for Andrew? So, Andrew, do you think I can ask a question? So, do you think that moving to some of these 2 open questions that you have here, are you going to be able to reuse some of the bagging techniques that you've used before? Or do you think you're going to have to come up with another methodology to try to attack those?
So I can actually spoil one of those open questions a little bit. Because we actually just had a paper accepted to IJCAI, which gives a 2/3 one algorithm in polynomial time for any number of agents. And it does basically reuse the lone divider and bag filling techniques. For the Pareto optimality open question, though, it turns out this is a lot harder because even doing the normal reductions isn't necessarily guaranteed to be Pareto optimal. in that setting, we have to kind of, we can't take our normal assumptions that while there's no goods with value more than the MMS and there's no more than n high value goods, because we lose the reductions already. Or at least there's no obvious way to keep the reductions.
Okay. There's one quick question. Oh,
sorry, can I jump in? Just want to make a little correction. So the paper that got accepted is this one. So we don't, I mean, we have another paper under review.
Yeah, sorry.
Which kind of extends it to chores. And maybe, Andrew, you can address Rohit's question.
I was about to say, Rohit had a question about extending the chores. So Rohit asked, some of the techniques you described, ordered instances, bag filling, seem to have an analogs for chores. So what's the main challenge in obtaining similar alpha beta MMS guarantees in that setting for chores?
So the irony here is that the main challenge is actually the definition. If we wanted to look at, say, n-1 of the agents and give them all their MMS in chores, it's really easy to do that. I give n-1 of the agents nothing, and I have one agent take all of the chores. He's unsatisfied, but everybody else is very, very happy with this allocation. So, well, this is technically still works for alpha beta MMS. It's not really a nice fairness notion, and it's a little too easy to satisfy and say it's meaningful. So the question here is, well, how do we actually extend our definitions to chores so that there's still a meaningful ordinal approximation? The way we classically would do it was you say, what happens if we told people that there's like half as many agents that we actually expect? So in that situation, if there's 10 of us and we're all expecting to do work divided among 5 people, we're expecting a little more work, and so we're okay with a little better off or a little worse off allocation. So there we now ask similar questions, but the same results don't translate immediately.
Okay. Sounds good. All right. Hopefully, Rohit, that got your question answered. All right. Yes. Awesome. All right. So let's thank Andrew one more time. Yay. Thank you, Andrew. All right, and that is the end of the program. The first thing I want to say is all the papers are up on the website for the conference. If your paper is not up, it's because you did not update your paper and take off anonymous authors. So if you do that and email me, I will put it up on the website. Secondly, I would like to thank all the organizers, Harris, Sophia, John, Hadi, Omer, myself. I guess I can thank myself. Duncan and Yair, especially Omer for getting up early and running a bunch of sessions this morning, and Hadi and Sophia for running sessions as well today, and Harris, who's left us now. But there's a lot of work in the back end, and especially for Hadi for taking over some of the last minute prep here as AAMAS came through. So I'm gonna thanks all my fellow organizers for making this happen. Yay.
Special thanks to Omer. He's been awake since the beginning of it. Good job, Omer.
Yeah, Omer's pulled all.
For me, it's waking up at 8. It's not that early for me. It's just staying here the 10 hours straight. That's the.
And especially thanks to all the program committee and everybody who I know did some reviewing on tight deadlines and between ICHCAI and ComSoc and everything else this year. So we really do appreciate it from everybody. We recorded this, and we're gonna try to put it up and maybe break it up into sessions, and we'll put it all up on the website. And yeah, I think that's it. Thanks everybody for coming.
Yeah, thanks everyone.
Thank you all. Thank you. It was great.
All right.